all of you. I will now request our chief guest, Pro VC of Jadavpur University, Professor Amit sir, to come onto the dais, and the HOD of Mechanical Engineering, Professor Amit Karmagar, to come to the dais. Sir, please. I will now request Professor Nipu Modak to hand over a flower bouquet to our Pro VC sir. Professor Shuman Kallan Das to hand over a flower bouquet to our HOD sir. Thank you. We welcome you to this 2 days workshop on high performance computing methods for complex and moving geometries, jointly organized by IIT Kanpur and Nodal Center for Training in HPC and AI, IIT Kharagpur, under the aegis of the National Supercomputing Mission, Government of India. In this workshop, we shall cover fundamental and advanced computational methods for handling complex and dynamic geometries. Starting with fundamental topics of CFD, the workshop includes a dedicated session on the basics of advanced high-performance computing techniques for solving multidimensional problems. In this workshop, we have a total 39 registered participants encompassing faculty members and research scholars across various institutes. Participants will engage in hands-on exercises. They will also receive training in using open form to tackle complex issues. Additionally, the workshop will address GPU-based computing and demonstrates its capabilities. This event aligns directly with the vision and mission of the NSM challenges undertaken jointly by the Department of Science and Technology and the Department of Electronics and Information Technology. In this workshop, we have designed 8 lecture sessions and 3 hands-on lab sessions by the research persons, namely Professor Arnab Kumar De from IIT Guwahati, Professor Ashok De of IIT Kanpur, Professor Somnath Roy from IIT Kharagpur, and myself. With this short introduction, I will request the HOD of Mechanical Engineering, Professor Amit Karmagar, to share a few words with us. Please.
Honorable Pro Vice Chancellor, distinguished faculty and the participants, I welcome you to this workshop on high performance computing methods for complex and moving geometries. This is the first of its kind being organized jointly by Mechanical Engineering Department and IIT Kharagpur and IIT Kanpur. I thank Professor Sandeep Sarkar and his team for organizing such an event under the aegis of Government of India National Supercomputing Mission. Now, many of the faculties of our department are working on numerical problems. For some complicated technical problems with complex geometries and boundaries, it is extremely difficult to obtain closed-form solutions. So for that matter of fact, you need to go for numerical computation to help the designers. So to help the designer, here a major role plays the major high-performance computing techniques, and it has always been a great demand over the years. I believe through this workshop, researchers will be motivated to take up the challenges of real-life complicated problems of technical importance. We have an advantage as regional computer center. Government of India is stationed in this campus. In respect of computing facilities, its track record is very good. Let us go back to the way back in early 80s, when Professor B. Nag, who happened to be the director of IIT Bombay and happened to be the professor of electronics department, he took the initiative of installing mainframe computer centers like Cyber, whose operating system is NOS-V, along with IIT Mumbai. So we do have very good facilities right from the beginning, and our researchers and the faculties are motivated in this particular direction right from the beginning, I would say from the early 80s. And my experience with DEC 10 computer, which is the operating system, is top 10. When I was working at IIC, that was the mainframe high-speed computing system along with the IIT Kanpur. I used to work in two tape drive. One tape drive was for the input and another for the output. 2,400 feet tape drive. So, and I used to work from 11 o'clock in the night to 4 o'clock in the morning, because that time only those tape drives are freely available. So I had no other choice. So for the consecutive 6 months, I had to use those mainframe computer system to get my results. But nowadays, powerful computer has come to the market. And high performance computing technique is really essential along with the high performance computing technique. And I think our Professor Sandeep Sarkar and his teammates will induce you to high performance computing methods, and you will be motivated to work on the complicated problem so that you could face some benefit for the society. Thank you.
Thank you, sir, for these encouraging words. I will now request our Pro VC sir, Professor Amitabh Datto, to share a few words with us. Sir, please.
Good morning to all of you. Respected Professor Kormokar, Head of the Department, Mechanical Engineering, Jadavpur University, other distinguished faculty members from the department, distinguished speakers, Professor Ashok De and others, Somnath, and dear participants. I'm very happy to be here today, and sorry for being late because I had another program to attend in the morning. But indeed very happy to be here in the Mechanical Engineering Department, as it is my parent department. I graduated from this department, so I'm always very eager and happy to be here in Mechanical Engineering Department program. And I'm glad to know that Sandeep and his team is organizing this 2-day workshop on high performance computing methods for complex and moving geometries. It's a very important and interesting field nowadays. With the advent of high-end computers, high-speed computers, high-performance computing is becoming a reality, and researchers in various fields and also in the industry are using high-performance computing to solve so many different problems in different areas. Computational fluid dynamics has evolved as a major tool and supplement the cut and try experimental method in order to reduce the cost of development in various areas and help in the developmental process. If you look at any area, so to say for example, in aeronautics, for the development of aircraft engines, or in automobiles, or in other industries as well, you will find a lot of scope of applying computational fluid dynamics in order to have newer engines, newer other equipment and development of them. And in all these cases, the geometry that you have to handle is so complex that you have to use newer grid generation techniques and then apply the computational fluid dynamics with all the complicated equations. And when you have turbulent flow and you have reaction, it makes the problem more challenging and complicated. So it is very interesting to know how to take this challenge and how the modeling has to be done so that such complexities can be addressed and results can be obtained for the research and for the development. Amita was mentioning about his experience in RCC lab. I can also share my experience when I was a researcher at IIT Kharagpur doing my PhD. At that time, high-end computers are not so easily available in all the laboratories, and we only had at that time one laboratory of Professor Farooqi, where we had a few high-end machines. And there used to have slots of 2 hours, 9 to 11, 11 to 1, 1 to 3, and 3 to 5. And 1 to 3 slot is normally used to be vacant because people used to go for lunch at that time. And I used to go to the institute by 8:30 and stand in a queue at the door of the laboratory, because as soon as the laboratory opens, I have to enter and book that 1 to 3 slot, book the 3 to 5 slot, so that I can come back from my lunch and use the 1 to 3 slot which is vacant, then the 3 to 5 slot, and then you can continue, because after 5 there is no such slot. So if you book the 3 to 5 slot, you will have chance to work from 1 o'clock till late in the evening. But now it is not so. Now the researchers having access to high performance computers in almost every laboratory and in every institute. So you have ample scope to work on your problems, and there are so many other tools, CFD tools, either open form or commercial packages which you can use. So I hope that this workshop, this 2-day workshop, will give you ample knowledge and exposure, so that you can use them in order to carry out your own research and move forward and develop good results on difficult and different problems. I wish this program a very grand success, and hope that you will enjoy your 2 days here, not only in terms of knowledge, but otherwise as well, in company with others. And with these few words, I would like to conclude and hope that you enjoy the program very much. Thank you.
Thank you, sir, for your kind words, and hope with these encouraging words we will make our workshop a grand success. With this, we shall conclude our inaugurational program. Now we shall move ahead with our scheduled sessions shortly. Thank you, sir. Thank you very much for being here. Thank you.
Idea here is that in this particular session, I'll just get you through quickly what HPC and how HPC is connected with CFD and things like that. Then slowly we'll move on to your actual details of those things. So what I'm planning to do that, just quickly give you an idea about HPC stuff and what HPC is meant for, how this has been evolved, and then try to connect towards the end with some HPC application, but not getting into the details. So that probably we will try to catch up during the hands-on session and things like that. So then you will get some idea. So how many of you are here HPC user? I mean hardcore HPC user. So you know how to hardcore HPC user, not submitting a dot out or a serial mode job there in the HPC. Barely. See, the thing is that this is something very, very crucial, because in the name of HPC, if you submit serial jobs or jobs which require less number of processors and things like that, it's not going to be helpful. Okay. So that probably give you an idea what we started off. So when you talk about HPC, what is HPC? Essentially, you think about the abbreviation as it stands for high performance computing. So which is a collection of a segregated set of computers, or call it a supercomputer. Now somebody might have let's say Apple M2 processor, which comes with 8 or 10 CPU nodes, then also 8 and 10 GPU nodes. So like that, more and more high-end laptops, even they are more powerful. Okay. So laptop can do certain things, then you go to your terminals or essentially the desktop computers, which can serve certain purposes, but even these days desktop computers are quite powerful, because the i7 and the generation of the i9, they are quite powerful. That can do also heavy task. Okay. So So essentially those machines where, okay, terminal is something you can go for. After that what? So I can have a collection of terminals, I can use that. That's probably one of the back-end concept of the HPC. So something that you cannot do with your available system, you try to do, that is what HPC is meant for. So when you talk about this high performance computing, so the supercomputers are now very much there in the system. What it does give you, because I want to do large scale systems calculations. It's not something, okay, I have a small job to run, then I will try to do that. So large scale computing. And how do you kind of classify that? It's classifying that, okay, I'm pumping in more and more number of jobs. That's now how you want to classify. You want to classify how many instructions that you want to give. So essentially the flops, which is very, very important parameter. That means when I'm sending the set of commands, so the floating point operation that I can do. So that's how you want to kind of measure the performance, not only the million instructions per second or MPI. So then what is the key feature of this kind of things when you try to use them in the HPC system or the supercomputer when try to solve a large scale problem? Obviously, when I talk about a large scale problem, it's literally large scale. Maybe you are doing high end atmospheric modeling, you may do a gas turbine modeling, you may do a furnace modeling. It's a large scale systems where you kind of give you an idea where it's a multidimensional or millions or billion points calculations where it's going to be. So obviously one of the key component is the parallelization, which again going to be discussed later on. That's the key component, how you span over all your processes over that. So how you do that over internet or Ethernet, that's a different aspect of it. So typically if you look at how the supercomputer cluster looks like, this is a nice picture, IBM Blue Gene. So you are as an end user who are sitting right now, I think probably in the lab session they are going to do that. You connect to the computers through some sort of an internet network or Ethernet, ideally LAN or Wi-Fi, whatever. So you need some connectivity to get to a first layer of this computing platform where you connect, and then you have set of small computers where you actually submit your job, okay, which is going to span in multiple processors, or if you use GPUs, then multiple GPU accelerators. So these units are going to do the job for you. Then you get back and then bring back the data to your local terminal. Again, that's a catch here. It depends on the size of the data, how you want to post-process. Okay. So that's how, but now when it started all long back. It's in the 1943 when the supercomputer used to be look like that. Okay. So now the evolution has gone. So I will quickly run through this. So it was started for designing the actually nuclear weapons, and then the next era came in the 1964 when the CDC computer came up, where you started having some clock speed of the processor, and so it's a one step further where but the thing looks different. Then there is a change where you got a 1975 to 90 where you got a different level of computer, which you had higher number of vector processors, and obviously the flops, when it talks about that, means you can do multiple higher end of floating point calculation. So that slowly, if you see over the time or the decades, things are changing rapidly, and then you got Cray in somewhere early 80s, and the Cray machines became quite powerful. Obviously these machines all initial days came up in mostly in United States, but now also we have some, I'll come to that. And then moving to the another set of one, which is the Intel systems, hypercube based system. Then you see a concept that, okay, now I have this desktop or multiple desktop, which I can even connect through, let's say LAN cables, and use them as a kind of a processor and can do the multiprocessing computing. That's the era where you started using that kind of things. Before around early 90s or late 90s, you started getting these big hybrid computers, which has a multi-core CPUs and threads and things like that, where the connectivity has gone in different level. Instead of connecting things with the internet, you start doing that with the InfiniBand or MUNET band. So there is a site which is actually give you an idea about, this is the latest one in November 2023, the top 500 list, and this is the kind of a segregation of which are the countries having different kind of computers, and this is the country's performance here. Obviously, we don't feature there. We have some computers rightly said there. It's a wide spectrum of calculations that you do, all these computers. So these are the, it's not something, so some top 5, 6 computer you can see this peak performance, the petaflops. That means that many floating point operation that one can do, and how you measure that, you see the performance, how things got changed. So that shows you essentially with the year and the floating point operations, and now see the rising curve where things are moving ahead, and if you see where we are actually heading, so that means more and more power that you have, so probably the performance factor is getting increased, really doubling up in every 2 to 3 years. So this is where and why that is happening, obviously the computers, the architecture, so electronics communications or the technology, that has been evolving. So that happens, that can give you the computer, but are we ready to use that? That's the bigger question. So we may say that I am doing HPC, but in the name of HPC we may do all sort of things, okay, but literally we are not doing that. So the architectures, the engineers are giving you the architectures. Architecture development is going at a rapid pace. So we as an engineer, we have to also cope up with that, so that our tool is ready to kind of utilize that architecture. So that is what the projection is going, and this is where Indian scenario, we have this, this is now ranked 90 in the worldwide list, we have 163, so these are, and couple of them are in the Indian metrology where they have, and obviously we have this now NASA supercomputing missions. Under that we have the machines which are obviously when the whole plan got kind of envisaged, that time we are in the top 500 list, but right now today we are not featuring in the list. So, but these are the computers which are there in the top 500. Obviously what HPC does, so essentially it increases, it's just an example to give you that if you have a particular machine with some number of processors, so how much time you actually can save. So you do something at your laptop, something you can do to your desktop. From desktop, if I go to multiple processors, then how fast I can run a same job. But yes, when I'm talking about that, for example, let's say I have a job of 1000 by 1000 points, two-dimensional problem, which is let's say 10,000 points, something like that. I would be probably happy to do it in my laptop. As soon as I go to a terminal which has a, let's say 4 cores or 8 core processor, even more than that, not necessarily it is going to increase your, decrease your runtime or performance is going to be increased, because that's another wrong concept, because they are not like that. So it has to be scalable at the same time. So the size of the job and the number of processors that you use, that is also very, very important too. So how does that increase the performance? Obviously one way to look at it, what I was talking about, that you try to increase the processor, but increasing the processor blindly won't help. If my size of the problem or the scale of the problem is not that much. So that's what I was talking about, the floating point operation. See, the floating point operations could be faster, but where is that? So when you do parallelization, that means what you want, let's say I have 2 different computers doing the same task at the same time. So I want them to do parallelly. That is where the parallelization comes into the process. So they are doing that or executing that task parallelly, then they might be doing those floating point operations because of their clock speed very fast. But then finally, they need to talk to each other. So once they start talking to each other, that is where it starts falling down. So there are computation, then there are communication. So the time where you are going to actually lose, if you increase more number of computers like this, then you have to talk to each other. So the communication also become a big factor, which most of the time we are very, very reluctant to think about it. we have a 100 million points, okay, we'll fire 100 processor. Probably it will slow down the whole business. Because your communications is going to be the killer the time you are doing the computation. So there has to be some optimized process. So there's optimization, it depends on other factors. Obviously one of the key ingredient to that is their architecture, but another key important factor is your tool that you are using. The CFD tool you talk about or the solid mechanics tool, whatever. So what important thing is that how you parallelize. So essentially you need to thinking parallel. So you have to start thinking whole process in parallel way. So one important aspect is that the concurrency. That means, as I said, that you have these multiple systems which are connected to give you a sort of an HPC system, same set of instruction, how quickly individual computers can do, that is one aspect of it, then they come back to the talking. So it's definitely it differs from your serial programming paradigm to a parallel programming paradigm where you can actually execute that thing. So one, as I said, if I have a scale problem, I fire in multiple system, they are going to work in a scale. It's not. So scalability is one factor which probably again going to be talked in more details during your parallel programming session and the last session. So then comes the speed up, how you kind of tackle them things. So essentially your programming wall clock time to the parallel programming time. So parallel overhead time, all this comes into the together, that how much you are doing the floating point operation, how much you are doing the communications and talking like that. Obviously again goes back to the situation, the size of the problem that you have. It goes back to the situation of you have this, these things, the number of processors that you intend to use. So now let's say you take an example, there is a numerical integration that you would like to do. So you have this function and you have number of points to do that, so integral values could be like that. So how do this computation in parallel? So either I can kind of cut down into multiple segments and then solve the problem so that I can get the solution quickly, provided I do that thing efficiently. Okay. So then similarly I can skip this. This is another one. Yeah, important thing is that every mathematical problem that you are dealing with, that requires some strategy. So that means when you talk about the parallelisms, when you talk about the other things, so flexibility is one way to look at that, the problem to be solved, which is you have the parallel algorithm that is in place that you can solve that, and one has to be a little bit creative in doing that. So before doing that, one has to understand which portion of the problem you can parallelize, which portion. I mean, for example, let's say you take a pressure force in a system which is a local, but when you talk about the gravitational force, which is a global phenomenon. So very important to know which part I can parallelize efficiently, which part I cannot. So you may try to impose something forcefully, but then it's not going to serve your purpose. So obviously, when you design these things, what is important, that computation is always fast. That means your operation. Your communication is always slow. And more importantly is your input and output, that is the I/O. That means when I write the data and when you write it in a serial mode and when you go to parallel mode, they are going to be totally different. So these factors are very, very important when you devise a algorithm or program which is highly parallel, can be used in HPC system where you can actually best use of the resources to get the proper output. Obviously there are other issues like, apart from your, these are the things which, as I said, these are going to be taught again in the parallel session. So now quickly I will just try to connect with that because most of the things that we are going to do with the HPC. So some example of HPC where, so what HPC I mean, CFD is essentially is a part of your all computer aided tool, and now today you have the banner of your high performance computing platform. You have different tools which in terms of software, in-house codes and things like that. I mean, unfortunate to say that everybody is doing HPC, okay, or in another way everybody is doing CFD. But what CFD essentially designed for? It should be kind of giving you a solution in the field of fluid mechanics heat transfer, where you can compensate the experimental process. I mean, obviously CFD has matured enough. It got started long back, few decades ago, but it got matured enough. Today it has been used as a design tool in the industry. But initial design probably done using CFD, but then you cannot really bypass the fabrication of the process and doing the testing. It's not like, I mean, when you do things with the CFD or talk about CFD, again a wrong notion is that, okay, you are competing with the experimentalists. It's not the case. You are trying to complement each other. I mean, the ideology should be clear, or the idea should be clear. Obviously, when you try to do, you have three different stages. Again, these are something that one has to again understand. So pre-processing stage, which is mostly, and then computation, where we are going to use the HPC. So when you talk about HPC and the use of HPC, mostly in this stage. Pre-processing stage, you can partially use it, and then the post-processing again you can use HPC. But mostly the use of HPC by and large 99% is in here. But problem here is that, you know, this in these three major segments, when again you do HPC and things like that, or you do CFD, oh, I am doing the computation, maybe using something, some solver, whatever is that. You tend to forget the pre-processing and post-processing. See, you may get a data. When for doing that, if I have a tool ready, if I have a computer ready, computer is a bull for you. You send a set of instructions, that's what it's going to do. You set wrong set of instructions, it's going to give you junk, nothing else. So I can have a 10th pass guy, put him in the desk, I said, okay, you do this. But that for that you don't need to be graduated. The problem here in the pre-processing stage, when you have a problem, actually physical problem, how you try to do that, and the post-processing, very, very important component, because your interpretation of the data. Computer is going to chunk numbers. Numbers could be totally junk, number could be totally meaningful. And how you try to interpret that, that is where you as an engineer or scientist need to spend time, because that's what actually it encloses the complete circle. If I say that, oh, I am doing large computation, you are not doing CFD, or neither you are doing HPC. Unless you do the complete thing, unless your data you are interpreting, unless you are doing the pre-processing, you are not doing anything. So obviously this we have talked about. The advantage is that, as I said, we try to kind of compensate the, I mean, obviously it should have been a design tool where the industry can use it, but you cannot completely ignore the manufacturing process or the experiment. So how you solve an engineering problem? Just quickly, you have a problem which is essentially a physical problem. For example, you want to see the other corner of the room, how much air conditioning is going there. It's a diffusion process. Your air conditioning here, you have the fan which are running. So essentially, you have this, the forced convection process, so you can see that. That's a problem. Then you try to identify that, and obviously through some governing equation, you modify that in a mathematical problem, and then you try to model that, and finally you send it to the system where you can solve it. Finally the result, as I said. So this includes everything there what you have. Okay. As I said, it requires your brain to be used, not to be idle. Okay, so that you can properly do things. Again, as this is, I mean, when you set up a problem, these are the steps that one has to follow, kind of setting the things. I mean, this is where we send it to HPC to solve the problem. Again, here you can use HPC. These days, even large scale problem that you can use the parallel system to do the. So quickly, I mean, this is your system that you have, you do discretization, so the other session they are going to talk about this process. So finally you have a system where the computer understands in its way. Okay, obviously through programming, so there are different methods. So here I think we are going to touch upon the finite difference, and then probably you go to the finite volume, and later on you will be given the GPU accelerated parallel programming. So yes, I mean, lot of these commercial packages they are in your hand, and you can always use that very nicely and blindly, and you can claim that you are a CFD user and using CFD and HPC and get the results, but the results could be totally junk unless you interpret them. There is no harm using those, but those packages, whatever you see in your click in some set of buttons clicking in your GUI interface, it's always user-friendly interface. Everybody wants the path of least resistance, human tendency, absolutely fair enough, but those softwares also back-end solving set of mathematical equations. So there is no harm using something, but you need to understand what it is solving. If you don't do that, then whatever parameter you set, they could be totally ad hoc. You may get a very, very good result, very, very fantastic, encouraging result, but that could be completely by fluke. Okay, and if you are not lucky enough, you may end up with. So be careful when you use that. Obviously, there are advantages. We have talked about some. Just quickly, where we can use CFD. I mean, see the spectrum where CFD can be used with the under the. I mean, these are all not a system there you can solve with a single computer. So you need HPC application. These are only some pictures I have picked up from the internet. These are not all. You go to the HVAC applications or the appliances design and things like that. You go to automotive, external aerodynamics, engine, internal aerodynamics, air conditioning. You go to biomedical. Now this has been picked up big time, where the medical practitioner, they want to have their system, or they want to design something so that the healthcare facility can be improved. So where a lot of CFD can be done, and a lot of initiative has been taken up. Chemical processing industry, you do mixings, these things. So then you go to hydraulics, where the shipyards, dock, marine industry, oil and gas, power generations. So everywhere, and then finally the sports aerodynamics. So I might miss some of the other application area, but the idea here is to just give you an idea that whatever you see in the real life today, you have huge application of the CFD, and not only CFD, CFD is coupled with HPC. So you see what is the basic idea of HPC, how HPC behaves, and then when you talk about CFD and then you bring back the CFD to connect with that. So examples would give you an idea. Again, if you see at this level, they look all fancy. When it comes down to the more bottom to the layer, it's essentially a problem, which is a mathematical problem that you have to solve. That is where you need to understand the basics. Without having good command over at this stage, if you try to do something at this stage, this gap can never be bridged. So it's not I'm trying to scare you up, I'm trying to more like a bring it down to the surface to be realistic. So whenever, even today I have been doing these things for like 20 years probably or so. Still I don't think that I know everything about CFD. Every day there is a learning. Okay. So these are something which probably you should take it, because it not necessarily, especially the last line, which I like it very much. So you have to take care. Your switch, always your brain and judgment. Okay. Especially when you get results from your CFD code. So you may do a lot of things, not necessarily that's going to give you. So it's not colorful fluid dynamics. There are other scientists talked about something, their quotation, not mine. But my sincere request, don't make it a colorful fluid dynamics. It's literally a computational fluid dynamics. If you make it a colorful fluid dynamics, again, it doesn't make sense. Okay. So finally, you should look at your competence, your weakness, and you should challenge yourself. Okay. If you wait until we are ready, we'll be waiting for the rest of our life. So if it doesn't challenge you, it doesn't change you, but not by clicking button. I think that's where I would stop. And if you have any question, I would be happy to take it up with you. Any questions? Feel free. Yeah. Yeah, sure. Can you be a little louder? Yes. It's a nice comment actually. Any other comments, question, doubt, feel free. I mean, this today you should be more like take it a classroom things. Here none of us here, I mean, they are all kind of approachable, not necessarily during break time, lunch time, dinner time. So, but you can interact. Yeah. Yeah, there are a lot of noise, so be louder.
There are problems like we can solve it with several methods.
Yes.
Like K epsilon method and K omega methods. In K omega there are more complex nodes and more nodes are there. So high computing methods are required at that point. So how do we decide before getting the solutions that we need supercomputing or not?
Okay. So
Because we get
let me go a little slow here because I'm a slow learner. Okay. So I have to get your question in a bits and pieces. So first part of your question was there. There are different methods, and then immediately you jump into K epsilon. So let me answer that part. K epsilon is not a method. K epsilon is a turbulence model. So when you talk about methods, that comprises finite difference, finite volume, lattice volume, spectral. Those are methods. So K epsilon is a turbulence model which you can use for your problem, which is definitely turbulent in nature, that you want to solve. I think let's clarify for others. Now move on.
So there are different models to go through, right? So K epsilon, K omega. So in those cases, K epsilon requires less number of nodes and all as compared to K omega, where large number of nodes are there and high computing methods are required. So workstations are required in that case. But the solutions we get after applying those models. So when to use those when to switch on to supercomputing modes?
Okay, again, now you are done with it, right? Yeah, you can sit down. So again, there are two components to your question. One is that when to switch to supercomputer, let's say I am doing it in local terminal, and your K epsilon, K omega also there was an issue. So let me first address this component, K epsilon, K omega. These are turbulence model again. So whether you use K epsilon or K omega, these are two equation Ransbed turbulence model. So it's the same number of governing equations you are solving. So your degrees of freedoms are not going to be changed. So is it going to consume more computation or not? That depends on your, so probably omega calculation requires little bit more, but that's more like calculating floating point operation. So as I've been keep on emphasizing, floating point operation today is not a headache. Computers are, even the laptop is so powerful, I can do lot of floating point operation. These are not my bottlenecks. So whether I am using K epsilon or K omega, depending on the problem that you are dealing with, doing floating point operations are not the problem. Problem is that switching to a supercomputer, that again depends on the size of the problem, the physical problem. Let's say I am trying to solve the flow over this body, and I try to solve the complete room. Which is bigger in size? This one. This one probably can be done even a mobile, high-end mobile. This one I cannot, maybe my desktop is required. So switching to a different problem depends on the scale of the problem. That doesn't dictate what turbulence model you have. Let's assume this mobile where I can do this, and the terminal that I have, same clock speed. assuming that. Then it is a scale of the problem which would dictate me where to switch on. Okay, it's not the turbulence model. Turbulence model should be connected to your physical output that you are interested in, because every model has its own limitation. See, one comment was there. See, whenever you do CFD, it's a mathematical problem. So essentially, you are doing some approximation to your governing PDEs to reach to that state. As soon as you do approximation, there are hidden errors, truncation error, which you don't account for, right? Whether sometimes knowingly, sometimes being ignorant, sometimes being reluctant, sometimes intentionally. Who talks about that? But this is the killer. Okay, so that depends on that. So finally, it's the approximation. So this approximation, how good or bad, that would dictate the accuracy. So which turbulence model, good or bad, that depends on the physics that you would like to achieve. Switching to a computer depends on the scale of the problem. Now I go to the room, probably my terminal is good enough. Terminal has 4 processor, 8 processor. Now I say, no, I have access to 80 processor machine, I will go to 80 processor machine. That's a sheer wastage of this time. Because what happens is just like this. When you are in the queue in the morning for the tea table, right? The guy who is in front of you, unless he moves out, you cannot reach to the desk where you are keen to get the packet. Same thing happens in parallel processing. You have given the same set of instruction. This guy probably is fast enough, is doing that. This guy is slow. Unless there is a common platform where they talk, unless this guy completes, they would not talk. If they don't talk, process stalls. This is where you lose time. Size of the problem, if it is small, fire in multiple processors like that is going to kill these processes, not this. Today, floating point operation is not a concern. Okay. Any other question? Yeah.
Thank you, Professor. Now our next presentation will be delivered by Professor Sandeep Sarkar. So he is the professor in the Department of Mechanical Engineering, Jadavpur University. So I would like to request Professor Sandeep Sarkar, please deliver your presentation. Thank you, Professor.
Laga.
This is basically already you know, some of you who have attended CFD course. So basically this is a part of the course, those who already have attended. So here actually I will be delivering some of the introductory concepts on finite difference method. This is the typical sections I intended to cover in this lecture, starting with FDM introduction, then some numerical solution methods. So then I will be touching on some transient problems, then numerical methods for incompressible problems, so on and so forth. I do not know because I have limited time, and within this time I will try to cover the typical concept that I have already given in this slide. So let us start with the finite difference method. Already you know, basically it may be a brush of your memories, already you have known, those who have attended this CFD course. So finite difference method primarily deals with, like, it is a numerical integration of differential equation at a particular discrete points. So by approximating Taylor series expansion. So here whatever actually we are doing, we are considering the function which is smooth and continuously differentiable. For example, you can see this curve here. Here I am replacing the curve y equal to fx. Say, let us say at particular point x equal to xi, if I want to calculate the derivative at x equal to xi, what I will be doing, I will be calculating the derivative at neighboring points. So what I will be doing that, so already you know this is the typical expansion of Taylor series. Here you can see Taylor series expansion at x equal to xa, about x equal to xa, it can be represented by this form. Now let us consider, here you can see I am just planning to evaluate a derivative at x equal to xi. So what is the meaning of the derivative? Basically it is a tangent to the curve, right? Now what I am just doing, I am just making some discrete points at x equal to xi plus h and x equal to xi minus h. Some small extensions I am just going to consider. So h basically the spacing, grid spacing you call. Now if I if I do expansion of Taylor series of a function f equals y equal to fx at xi plus h, it can be represented in this form, that fx xi plus h equal to fxi plus 1 and so forth. So let us consider basically, in representing any kind of, FDM functions, we consider yi equal to fxi, basically the functional value of, that particular function at x equal to xi. So let us represent it by yi. Then similarly for yi plus 1 equal to xi plus h and yi minus 1 equal to xi minus h. So about the point I am going forward and now I am going backward. The two stage experiments I am considering here. Similarly, if I do the Taylor series expansion, what you can do, that at yi plus 1, basically what is yi plus 1? That yi xi plus h, the next grid point. Similarly, yi minus 1, that is the backward grid point. So it can be represented by this Taylor series function. H is the tensile difference, xi plus h minus xi, the difference between the two stages. So if I have this expansion, equation number 1 and equation number 2, so if I subtract these two equations, you will be getting what is the derivative at a point yi prime, that is yi plus 1 minus yi minus 1 by 2sh, and some higher order terms. Now for a typical consideration, if I consider, for example, if I consider h is very small, that is basically finally what I am getting here, that yi dy dx, yi prime dy dx at x equal to xi can be represented yi plus 1 minus yi minus 1 by 2sh. For a limiting situation when h is very, very small, then what we can do, we can basically neglect the higher order terms. So that's why in the CFD calculation, computational fluid dynamics calculation, we always consider you should have a very fine mesh so that you can capture the derivatives or you can do the integration accurately. Is it clear? So that is the expression that we have got, that yi prime, that is dy dx at x equal to xi, y plus 1 minus yn minus 1 by 2sh. Similarly, if you may recall equation number 1 and 2, if I add those two equations, finally you will be getting a second order derivative, that is yi double prime, yi plus 1 minus 2yi plus yn minus 1 h square. Basically what I am doing in the first case, I am subtracting equation number 2 to equation number 1, and the second case what I am doing, basically I am adding those two equations. Why I am adding those two equations? To evaluate the derivative at the second derivative, that is d2y by dx2. So from this actually we can see that here also we are getting the order of accuracy, or we can say the order of derivative is order of h square. If h is very small, you will be getting a derivative, that is d2y by dx2 at x equal to xy, that is yi plus 1 minus 2yi plus yi minus 1 by h square. This is a typical concept, this is the fundamental concept of evaluating any derivative at a particular point. This is the fundamental, you can say the fundamental methodology of finite difference method. With this, you can develop or you can build any other methods, any other numerical techniques to evaluate any complex differential equations, to solve industrial problems, academic problems, physical problems that you are primarily dealing with in a real situation. Okay. Then there are other methods we can also learn, that is maybe all of you may know, that is we can call it forward difference. What is the forward difference? Basically what we are considering the grid point next to the x equal to xy and the grid point which is x equal to xi. So with these two grid points, I want to calculate the derivative at x equal to xi. So what I can do, that yi plus 1, you can again write the similar Taylor series expression, yi plus 1 equal to yi plus hy prime plus h square by factorial 2 and so on and so forth. You can simply do the algebraic manipulation. Finally, you will be ending up with this expression, that is dy dx f x equal to xi for this forward difference yi plus 1 minus yi by h plus order of h. You can see in the central difference in the first case, where we have calculated dy dx at x equal to xi by considering two neighboring grid points, we have got an order of accuracy h square. But here, when we use the forward difference, we have basically lost an order of accuracy, where basically here the order of accuracy is order of h. Got it? Again, you can see if we can neglect the higher order terms, you may end up with this expression, that is dy dx at x equal to xi equal to yi plus 1 minus yi by h. So what is the second derivative? Again, what you can do the logical extension. You can take two grid points next to the x equal to xi, and finally you can end up with yi plus 2, the similar Taylor series expansion, yi plus 2 equals to yi plus 2h, so and so forth. Finally, if we subtract those two equations, the equation number 1 and multiply with equation number 2, basically the primary idea is to evaluate the second derivative. First derivative already we have obtained, so second derivative was basically I am going to obtain. So here actually we have basically what we have done here, yi prime 1 we have substituted, and finally we have obtained the second derivative as yi plus 2 minus 2yi plus 1 plus yi by h square. Again you can see the order of accuracy is order of h. So in the both cases, in the first order case, first order derivative and second order derivative, we have lost an order of accuracy in comparison to the central difference. Again, the logical extension of this problem will be the backward difference. Backward difference basically what I am doing here, I am doing the integration, not taking the stencil which is in front of the grid point, but what I am doing, I am taking a stencil which is backward to the grid point, right? So here we have considered, here you can see that we have started with yi minus 1 equals to yi minus hy prime. Finally, if we do the algebraic manipulations, we will be getting the derivative at x equal to xy with the backward difference as yi plus 1 minus yi by h. And similarly, by following the similar procedure we have considered for the forward difference, we will be ending up with the solution, or we will be ending up with the derivative. It is dy by dx2 at x equal to xi to be in this form. In both of the cases, yi prime and yi double prime, the first derivative and second derivative, will be ending up with an expression which is having a first order accuracy. So basically we are losing the first order of accuracy in comparison to the central difference. Now the question is why you are doing, basically in the both cases we are losing the order of accuracy in compared to the central difference method. So the question is why we should be using this forward difference and backward difference cases. So there are certain considerations. Basically there we do not have any other option but to apply this forward difference and backward difference cases. The first case is basically, suppose you are solving a typical numerical problem where the grid point basically ending at a point, and after that there is no grid point available. So in that case what I will be doing? I will be applying the backward difference. Similarly for the vice versa case, you have a grid point where you are not allowed to go beyond that particular point. So in that case you will be applying the forward difference. So you cannot go back in the first case, you cannot go, you cannot move forward. So in the both cases you may have to apply either forward difference or backward difference accordingly to obtain the solution for a typical numerical problem, numerical governing equations. So here in this case what you can understand, here actually what you can see, this both of the equations, forward difference and backward difference and central difference, all those combinations are typically important if we solve typical complex problems, complex numerical problems by employing the finite difference method. Similar problem may be extended for the finite volume method, which will be discussed soon by Professor Day, and also for finite element and other methods, spectral element. All those cases there is an applicability of this method to obtain the numerical solutions of typical partial differential equations. Again, there are two types of grids. One is structured grid and it is unstructured grids, and there is a uniform grid and non-uniform grid, right? So uniform mesh particularly we generally use where there is gradients are not very high. But you may have to use non-uniform mesh or fine mesh near to the situation where you may face there is a typical high velocity gradient, high temperature gradient, so on and so forth. In that case, what you have to do, you have to do the localized refinement of the mesh, so that you can capture the solutions very accurately. So in that case, what you have to do, you have to use a non-uniform grid for those typical situations. So here you can see basically the method I am discussing here, the finite differential method for the orthogonal grid, because those two grid lines are mutually perpendicular to each other. So here you can see that if the grid points are non-uniform, you can still apply this method to obtain first derivative, second derivative of any particular function when you will be encompassing regular partial differential equations. Here you can see, suppose you can see this is typical, again the same function y equal to fx, but here you can see the grid points are not uniform. In the first case, the h's are same. Above point x equal to xi, you can take, if you go forward, same stencil h. If you go backward, you also have the same stencil h. But here you can see you have two stencils, but y equal to yi minus 1, xi minus h1, where h1 and h2 are different. Under this situation, if we apply same Taylor series expansion, for the first case, if we expand y equals to fx at xi plus h and y equal to x fx at xi minus h. So xi plus h2 basically the next stencil, xi minus h1 which is the backward stencil. If you do the corresponding Taylor series expansion, you can see this is a typical expansion you may end up with. So finally, This is the first expression, this is the second expression. If we define a, you can a parameter R so that you can regularize those two equations. So the ratio H2 by H1 to be R, and again you can put the value of R in those two in the first equation, and if we do some algebraic manipulation, you will be ending up with the derivative d2y dx2 at x equal to xi. So by this typical formula, yi plus 1 minus yi 1 minus r square by minus r square yi minus 1 by r into 1 plus r and plus order of accuracy h1 square. Again you can see that if we apply, so this method is basically central difference technique, because we are doing the differentiation at a particular x point x equal to xi, and what we are doing basically we are moving ahead at a particular grid point which is h2 apart, and the grid point about the grid point which is basically h2 backward side of the grid point x equal to xi. Again what you are getting an accuracy which is basically order of h square. So both the cases, although the grid is non-uniform, we are not losing the order of accuracy, since here you have used the central difference method. Again, we can also evaluate the central difference method with the non-uniform grid by applying the similar kind of approach, and finally we will be ending up with d2y by dx2 by this typical formula, and here this is the typical formula we will be ending up with. So order of accuracy here it is order of hs1 square. There is a type of mistake. But here you can again see, if I put r equals to 1 for the non-uniform grid, you can finally ending up with the same equation that you have obtained for the first case when there is a uniform grid. So uniform grid and non-uniform grid both can match, both can both can couple together to obtain a corresponding expression for the non-uniform grid and uniform grid altogether. So whenever we write your own computer program in finite difference method, suppose you are writing a problem without using a commercial CFD package, you are writing your own code for solving a typical say lead driven gravity problem. So what you have to do, near to the wall you have to apply very fine mesh so that you can capture near wall situations. And accordingly the near wall you can apply this typical method, and in the center core of the cavity you can apply the uniform grid to obtain the solution of the entire problem. So this is a typical utility of the finite difference method. Then again see the numerical solution method. What I have done here, I intend to solve a typical problem by using a finite difference method. Let us see how one can apply finite difference method for the solving any typical problem that we may encounter in a typical industrial academic problem. So for the simplicity, what I have considered a typical one-dimensional thin problem I have considered, and I have applied finite difference method to obtain the solution of the one-dimensional free problem by using this central difference technique that I have already discussed here. So here you can see this is a typical fin. This is a typical standard problem. You can see this is a canonical problem. Everywhere whenever you solve a difficult computational program, whenever you write your own code, because why I have considered this problem, because this analytical solution to this problem is available. So what you can do, you can write your own code, you can solve this problem by numerically, you can compare the analytical solution with the numerical solution, you can check whether numerical solution is accurately predicting that analytical solution or not. If it is accurately predicting that your solution, your program is absolutely correct. Some sort of model validation you can tell. So this is a one-dimensional fin. One end is insulated, and you can see the another fin having a temperature, fixed temperature T equal to T naught, and fin is basically exposed to a convective environment where heat transfer coefficient is H and ambient temperature is T infinity. Typical canonical problem. Now let us see, if I apply the finite difference method, how one can obtain the solution for this typical problem, one-dimensional heat problem. All of you know this is the typical governing equation, because any computational fluid dynamics technique, what is the typical identification is that you have to identify the governing equation first. First you have to model the problem, because what I am doing, I am not basically performing the experiments. What I am doing, I am modeling the physical situation with some sets of governing equations. That is the methodology of computational fluid dynamics. So here actually what I am doing, I am modeling this problem. What is the how I can modeling this problem? I am modeling this problem by a governing equation. So what is the governing equation? Already you know this is a governing equation for one-dimensional fin problem. HP is the perimeter, A is the cross-section area of the fin, and these are the boundary condition at x equal to x naught T naught, T equal to T naught and x equal to s, dt dx equal to 0. This is the typical boundary condition one may encounter in any kind of one-dimensional field problem. Again, what you have to do next, you have to make this equation dimensionless form. Already you know what is the meaning of dimensionless, non-dimensionless any problem. Now why are you doing this? So what I am doing basically, I am making this problem dimensionless by this typical non-dimensional parameter. I am dividing a term m square equal to hp by ka. Accordingly, I will be getting a dimensionless form of this governing equation. That and finally the corresponding boundary condition corresponding to boundary condition 1, this is a non-dimensional form of boundary condition 1. Boundary condition 2, this is also non-dimensional form of boundary condition 2. If I have this governing equation, dimensionless form of boundary governing equation and dimensional form of boundary conditions, again you may discretize this problem. One-dimensional problem, very simply straightforward. You can do solution just like a a second within a few minutes or maybe second. So what I am doing here, actually I am discretizing the entire problem. So what I am doing here, I am discretizing the problem in number of grid points m. So here again, if I discretize number of grid points n, at typical grid point x equal to xi, I can discretize this theta I plus 1 minus 2 theta I plus theta I minus 1 minus x square minus ml whole square by theta I. Finally, I am ending up with this equation, typical algebraic equation where d is a constant term, 2 plus ml whole square delta x square. Now at x equal to m, you can see at x equal to m, we have got this form, and this is for the interior grid points. Now at x equal to m, what is happening? I am getting this kind of expression, x theta m minus 1 minus d theta m plus theta m plus 1. You can easily observe that at x equal to m, or here you can see that at particular grid point m plus 1 is not available because it is not inside the domain. So what I have to do? There are this basically you can see this theta m plus 1, this is basically representing a fictitious temperature because this temperature is not inside the domain. So how to calculate this, because we have to resolve this problem. So how to resolve it? There are two methods. Either you can use backward difference, already you know, or you can do image point technique. Some of you may know that what is image point technique. So what basically I am doing at theta m at x equal to m or I equal to m at this grid point, you can see that if I discretize the d theta dx equals to 0, theta m plus 1 minus theta m minus 1, this equal to 0, that is theta m plus 1 equal to theta m minus 1. And what is happening above this line, these are the reflection symmetry. So that means somebody is standing here, theta m minus 1 is standing here, it is basically seeing its reflection at theta m plus 1. This is called, we call it a image point technique. So if we apply image point technique, the problem of appearing the fictitious temperature theta m plus 1 is resolved. So you can simply substitute theta m plus 1 by theta m minus 1, and finally you will be obtaining this expression 2 theta m minus 1 minus d theta m equals to 0. So we have got interior grid point, we have got an equation, and the boundary point we also have got equation. The problem is closed. So we may get a corresponding solution, corresponding solution of this problem. So other method is basically higher order backward difference. Already you know. So you can apply a higher order backward difference, and finally you will be obtaining this kind of expression. So this is a higher order backward difference, and you will be obtaining this kind of expression. So here you can see, you can write for typical grid point theta I equals to 1, this is the point where the temperature is known. You know the solution. So you can put theta 1 equals to 1, temperature is known. Similarly for other grid points, you will be getting this kind of expression. And accordingly, if I write in a matrix form, you will be getting this kind of matrix. This matrix, basically A theta equals to B. So here you may getting a tridiagonal matrix. You can see this is a diagonal, this is the upper diagonal, this is the lower diagonal. So this I got a diagonal matrix. So so you have got a matrix equation here theta equals to B. So you have to solve, right? Theta equals to A inverse B. So getting inverse for this typical one-dimensional problem is very simple. But if you have a multi-dimensional problem, you have a very large number of grid points. So getting inverse may be difficult, right? So there are many methods already, you know, Gaussian elimination method, there are other methods also. But here in this typical one-dimensional heat conduction problem, here basically what I am doing, instead of storing these zero terms, we are just considering the non-zero terms. So here we can use either Gaussian elimination, Gauss-Seidel iterative method, or here in general it is recommended, if you have a tridiagonal system of equation, in general it is recommended that you should use TDA, tridiagonal matrix algorithm. Owing to the paucity of time, I am not going to discuss tridiagonal matrix, standard method, it is already available. code is also available. If you can discretize this problem, this MATLAB code for TDM algorithm is abundantly available in the internet. You can download it, you can write your own code, you can get the solution done. It is very easy. Then another thing, because if you again, so suppose you are not happy with the TDM algorithm, what I am doing that I am happy that I should write my iterative solution. That is because TDMA and Gaussian elimination is called direct solver. We are doing the direct inverse. But there is another solver called Gaussian elimination, or Gauss-Seidel method is called iterative solver. Basically, instead of directly inverting the matrix, you are iteratively solving the entire problem. So what are we doing here actually? You can solve iteratively. Gauss-Seidel method is very popular method, already you know. So here actually what you can do, you can accelerate the convergence of the Gauss-Seidel iterative method, and here you can apply some of the there's a particular technique we call relaxation. Relaxation. Basically, you can accelerate the convergence of the method. So here what you can do, that this is a typical solution except at particular iteration step. So this is the right hand side vector. Accordingly, you can write this alpha into, this is the expression into 1 minus alpha. This is the expression for the previous iteration step. You can play around with this alpha term. You can obtain the accelerated convergence of the problem. This is called over relaxation or under relaxation. In general, it is written that 0 less than 1 is called under relaxation, 1 and 2 is called over relaxation. This is a typical health formula that is followed. There are other consideration is called successive under relation, that is during the iteration step itself you are changing the alpha parameters, and successive over relaxation during the iteration step itself you are changing the relaxation parameter. Accordingly, you can control the convergence faster. So these are the summary of 3 methods. Already you know that. So Gaussian elimination is a direct solver, already I told you. TDM is also a direct solver, and Gauss-Seidel is a iterative solver. In both of the cases, Gaussian elimination and TDM, Gaussian elimination is a high round of error, and the typical number of arithmetic operations is order of n cube, is the number of elements in the matrix. Similarly, TDMA have a low round of error, Gauss-Seidel also have a low round of error. And generally, Gaussian elimination is not recommended for a large number of equations. If you have a very low number of equations, maybe for hand calculations you can use it. But primarily, it is recommended that either you should use TDMA or Gauss-Seidel iteration technique for the solution of this problem. Similarly, one can extend for the 2-dimensional problems, right? 1-dimensional already we know that. So you can extend for the 2-dimensional problem. Suppose let us consider a 2-dimensional steady-state conduction problem. It's a typical square block of length, 2-dimensional block of length, or maybe at the side length is twice L. All other, at all the sides, temperature is maintained at T equal to T infinity. If this is a typical situation, you want to understand how one can apply the finite difference method to solve this typical 2-dimensional problem. What I can do, because this is the problem here again, the analytical solution is available. So what you can do, you can solve this problem numerically by applying finite difference method, and you can compare your numerical solution with the analytical solution. Because this typical standard problem, analytical solution is straightforward. Separation variable technique, you can easily solve this problem. But here, what I am going to do that, I am going to apply a finite difference method, and one important point is that this block, there is a uniform heat generation, Q triple pi. See, this is the situation. Here again, what I am doing that, since this length is twice L, so if I consider the entire domain, because all other boundaries having the same temperature T infinity, so there is no point of considering the entire domain. Only you can consider 1/4 of the domain, because all other boundaries are symmetric boundary. So what you can do, considering the symmetry, you can consider 1/4 of the domain, and again you can apply where you have basically cut the domain here. This portion is cut and this portion is cut. You can apply the symmetry boundary condition, because del theta del x equals to 0. That is del theta del n. Why x is here? Because x is normal. So del theta del n equals to 0. And here equal del theta del n y. Del t del y equal to del t del n y. This is normal direction is y direction. So del t del n equals to 0. This is the boundary condition. Basically, we can consider the symmetric or dissolution boundary condition here. Under this situation, what you can do, you can write the common equation, because steady 2-dimensional heat conduction equation. This is the common equation with heat generation. These are the boundary condition. These are the 2 insulation boundary condition. You can see symmetric boundary condition here, this one and this one, and these are the odd Dirichlet boundary condition or temperatures are specified. Again, this problem, what you can do, again we can do the similar exercise that already we have done here. So we can make this problem dimensionless by this heat generation expression, and you can finally obtain this typical dimensionless form of the governing equation. So the corresponding dimensional form of the boundary conditions. So again, we can do the discretization. You can say typical numerical gate, discretization, typical numerical gate at x equals xij. This is a delta x, delta y, the spacings along x and y directions, and you can write this expression in finite difference, center difference method. So theta I plus 1 minus 2 theta I delta x square, this is delta y square. Finally, let us consider delta x equal to delta y equal to same to make this problem simpler, and you will be obtaining, this is the expression, this is the algebraic expression for the two-dimensional problem. And again, since there are certain cases for the boundary points where the next boundary point is not available, so theta I minus 1 equal to theta I plus 1, you can apply the image point technique and you will be obtaining this expression for the boundary point. Why I consider 1? Because starting, let us start with, this is the 1 point. Accordingly, this is the m point. So B0 point is not available. Similarly, m plus 1 point is also not available. Likewise, we use for the one-dimensional problem, right? Same technology or same methodology we have applied here to obtain this expression for the boundaries at I equal to 1. Similarly, at for the x equation, again you can apply the image point technique. You can obtain the expression, final expression for this two boundary conditions or boundary points. And for the handling the corner points, again handling corner points will be difficult. Which portion we shall choose? Generally, I am writing here like this, because you can corner point, again you can apply the image point technique. How you can apply that theta 0 1 equal to theta 2 1, already you know corner point how we can apply, because image point technique already I have discussed here. Similarly, theta 1 2 equal to theta 1 0, you can see about this point, about this grid point, and finally you can discretize this equation at the particular corner point 1 1 and 1 1, this equation, because the corner point the equation is valid, the partial differential equation is valid. Finally, if I apply these conditions, apply this condition that you have obtained from the image point technique, you finally will be obtaining this expression for the corner point. So you have the condition, you have the equation, algebraic equation for the corner point, you have algebraic equation for the boundary points, you have got the algebraic equation for the interior points, and you can write your own code for the solution of the interdifferential equation. Similarly, these are the pseudo codes. These are the equations for boundary conditions. These are the interior points. These are the two boundary points, and the corner points. And again, you can write your own code for, if you discretize this problem, number of grid points along the x and y, if you can fix, you can write your own code, write your for loop, and you can get the solution for the interior code. This is straightforward for the two-dimensional case. I have written a pseudo code, and so that you can understand how the code can be written. Or here actually what I have done here basically I have used the Gauss-Seidel iterative method. So similarly, you can write theta ij in terms of theta I minus 1, all other points. You can obtain the solution for the inter problem by writing your own numerical code. Similarly, this problem can be extended for the three-dimensional problem also. Three-dimensional problem already know this is a differential equation, and accordingly you can obtain instead of ij, you may have ij k point, and accordingly you can obtain for uniform grade, you can obtain this is the expression for three-dimensional problem. Transient problems. So far we have discussed steady state problem. The same problem can be extended for the transient problem. Transient problem is, so if there is a time dependency, how one can apply. So for the transient one-dimensional problem I have considered here. Suppose let us consider a hot infinite plate of a thickness 2L, and it is suddenly exposed to atmosphere where the local ambient temperature is T infinity, and initial temperature was Ti. Accordingly, again what we have considered, the heat transfer coefficient is very large. Under this situation, we may again this symmetry is symmetric about the central line. You can consider consideration of symmetry. You can consider only the symmetry condition here, and we can write the governing equation, that is, since there is a transient problem, so there is a time dependency. So you can write d theta del t equal to d2 to 3 by dx to 2. This is the one-dimensional transient heat condition problem. Already you know that. These are the parameters that we have used for making this equation dimensionless. So since this is a transient problem, and it should have initial and boundary conditions. Initial condition already given at t equal to 0. That is your time, your dimensionless time is 0. Theta equals to 1 for all x, which is basically the slab was, and for tau is greater than 0, that is when you are moving with the time, you may have the corresponding boundary conditions given. Again,
you can write, you can do the corresponding finite difference discretization, delta dt equals to, this is the standard difference expression, and again you can apply image point technique for this. Now the question is how to discretize this del theta del tau, right? In finite difference method, or you can say in a computational fluid dynamics method, there are three methods are available through which you can discretize del theta del tau. What are the methods? First one is called Euler method. Euler method, what is Euler method? I will be discussing soon. Then we have a canonical method. Then we have pure implicit method. So what is Euler method? Sometimes it's called explicit method. Generally, explicit method in a simple language you can say explicit method is one unknown per equation. Implicit method is more than one unknown per equation. This is basically thumb rule we can say. Very crude way of saying explicit and implicit method. So first one is we can call it Euler method. Euler method basically you can say if the temperature at the present time is say theta p, so p basically represents the present time temperature and time is tau p, you can be written as that tau p plus 1 equal to tau p plus delta tau, basically delta is the increment in time, how we are basically incrementing the time delta tau. So accordingly you can write that in Euler method, that is theta p plus 1 equals to theta p plus the gradient of del theta del tau at present time plus delta into delta tau. Basically, it's a Taylor series expression about time delta tau. So if we do this in Euler method, you will be getting this expression like this. This expression like this. So what I am doing is that is p plus 1 is the future time. That's why I am just doing the time. I am doing the time stepping. I am moving with the time. And finally, you will be getting this is the expression for this discretized equation. And accordingly, this equation has got a issue. This is called stability criteria, because this equation may not may be unstable for certain conditions. So stability, instability, I am not going to discuss all this stuff because of the paucity of time. So it is maybe unstable when this term is less than or equals to 0. And this is a typical variation of the theta versus tau. You can obtain the variation as we move ahead with the time. You can do the time stepping. So in the time domain, if you move ahead, so you will be getting this kind of typical variation. Another is called canonical method. This also it is basically sometimes called mixture of implicit and explicit method, but I will call it as the implicit method, purely implicit method. What is that? It is theta p plus 1. It can be represented as an average of del theta del tau at the time step p, present time step, plus del theta del tau at time step p plus 1. That's the next step. Okay. So if I do this, you can discretize this equation like this: del theta del tau equals to theta p plus 1 minus theta p by delta tau, this one, plus half into for discretize this term for the present time and for the p plus 1 time. That is when we are moving ahead with it. So next time. So accordingly, you can obtain this expression. If you do the algebraic manipulation, you will be getting this kind of expression. The most important for the canonical method is that this is basically unconditionally stable. That is, you may not require stability criteria for this kind of problem if the problem is not so complex. Then you have a pure implicit method. A pure implicit method is similar to this. Here, instead of having the present time, we just write the basically we are assuming the new time. So basically we are moving ahead, or we are moving with the time itself. That is theta p plus 1 equal to theta p plus delta del tau, p plus 1 is delta tau. Basically we are moving with the time itself. Similarly, we can write this discretized equation in this form: delta del tau equal to this plus, instead of having p, we are using p plus 1. That is the present time. Basically we are moving with the time itself. Accordingly, we may obtain the corresponding expression, finite difference expression for the pure implicit method. Again, this method is unconditionally stable. It may not require some certain kind of stability criteria for obtaining the solution. So there are certain stuff I should also say. What are the accuracy of the method? So Euler method is sometimes called forward time center space. It is space accuracy is second order, time accuracy is first order. Canonical method is called CTCS, center time center space. Space accuracy is second order, time accuracy is for second order. And pure implicit method is sometimes called BTCS, backward time center space. Both the cases, in the space accuracy is second order, again time accuracy is first order. So all these three methods, canonical method has got a higher accuracy. Similarly, what can extend for the two-dimensional method? I am skipping this slide because already you can logically extend the same thing for all other methods to obtain. But here one condition is that we may require stability criteria if we apply pure explicit method. or explicit method to obtain the numerical solution of this typical problem. Again, we may have a ADI method, alternative direction method, infinite difference. What is ADI method? Basically, where what I am doing basically, instead of moving ahead with the time in a single time state, we are breaking into two. So in the first, we may have intermediate temperature like this, T star. With this intermediate temperature in the next time step, we may get the final solution. So this is the thing, we may use the alternate direction. Because instead of going delta T at a step, we may break into two times. In the delta T by 2, we may have a temperature T star. With the T star using, we can get a temperature for the next delta T. So basically what I am doing, I am speeding the time step by two situations. So we may get much more accuracy, because you can see that here we have space accuracy second order. Again, we may have a time accuracy second order. Again, we may have a false transient method, because sometimes steady state problem may be modeled as a transient problem by just simply using a transient term in it, and we may use all other methods for a transient problem to obtain the numerical solution of this. Because sometimes steady state problem may face some issue, but here you can apply all those methods, Kangney-Kalshan, pure implicit and explicit method, to obtain the solution for the steady state problem, because the problem is steady state, finally you will be reaching a steady state solution. Now, numerical method for the incompressible fluid flow. So far we have discussed for the numerical method for the, you have got a temperature, steady state, unsteady state temperature, and here you can say, if I want to apply the finite difference for the incompressible fluid flow, how one can apply. In the first case, this is a typical governing equation, because all other computational fluid dynamics already I have discussed that basically you are modeling a problem. You are not experimentally solving it. What I am doing, I am seeing what is happening, and I am applying some, I am just introducing some model to represent the physical situation. That is basically the crux of CFD. So what I am doing basically is a model equation, you can call the governing equation. So already any typical governing equation for the fluid flow problem is continuity, momentum, and here for two-dimensional case we have got x momentum and y momentum. But the problem with this equation is that there is pressure, there is no equation for the pressure is available. Again, the equations are non-linear. So there are two methods through which you can solve these non-linear sets of governing differential equations. One is for two-dimensional situation is called stream function vorticity method, and for two-dimensional, three-dimensional, all other cases, all other situations, that the method is called primitive variable approach. So stream function vorticity method, I do not know because it is not so popular. It was because it cannot be used for three-dimensional situation. So because in the stream function vorticity method, what is that? Because you can see the pressure gradient term is very difficult. So stream function vorticity method, what is used basically, one may get rid of pressure gradient term by using stream function vorticity. I am giving us just some simple explanation like this. So what I have to do, I have to get rid of this pressure gradient term. In the stream function vorticity method, if I have to get rid of the pressure gradient term, what I have to do for x momentum equation, if I make a derivative del y, and y momentum equation, if I make a derivative del x, and if I add it, you will be getting an equation like this, which will be where there will be no pressure gradient term. No pressure gradient term available, because I have make a derivative of it. And finally, if you do some manipulation, you may represent del u del y and del v del s as a vorticity, and you can obtain this equation is called vorticity transport equation. So you can see the vorticity transport equation, there is no pressure gradient term available. So here you can apply this pure implicit, explicit Kangney-Kalshan method to obtain the solution for the vorticity. Similarly, we have a stream function, because in a stream function it can be written like this, and you have a vorticity something like this, and again stream function, once you obtain the stream function, you can substitute this vorticity. Once you obtain the vorticity, you can substitute this stream function expression in this equation. You can obtain this expression for the stream function equation. So you have got two equations: one equation for the stream function, one equation for the vorticity. And those two equations can be solved to obtain the stream function and vorticity for a particular flow field. Once you obtain the stream function and vorticity, you can also get what is the velocity profile, because u equal to del theta. So you know the velocity basically the gradient of stream function. If you know the gradient of stream function, you can integrate it, you can obtain the velocity field. Similarly, stream function and vorticity field can be used to obtain for the pressure field. It is simple. What you have to do, instead of doing the derivative del x, del y in the x momentum equation, you have to do the del x in the x momentum equation, del y in the y momentum equation. Do some algebraic manipulation. I am not going to detail here, going to the paucity of time. You have to apply this condition for the continuity, and finally you will be obtaining an equation for the pressure, that is grad square P equals to 2I square into those terms. Because here you know stream function, from the stream function equation you already know the expression for the stream function, and vorticity already you know. With this you can calculate or you can compute, rather you say compute, you can compute what is the pressure distribution across the flow field with this stream function vorticity method. The problem is, again, this method cannot be used for the three-dimensional situation because there is no existence of the stream function in the three dimension. That's why this method is not so popular. Similarly, there are boundary conditions for the stream function. Again, you can apply. So here you can see if a particular grid point like this, you can apply. Suppose this is a wall. What is the boundary condition for the stream function? Again, you can apply for Taylor series expansion about the point I2, about point I1, which is basically at the boundary wall, and you can do the Taylor series expression to obtain a stream function boundary condition, because at the wall your velocity is 0, and finally you may obtain what is the boundary condition for the stream function like this. And here you know the stream function, you can also corresponding extend for the boundary condition what is for the vorticity, because here you can again you can see the boundary condition what you are obtaining here is the first order accurate. Similarly, if there is a moving wall, you can also extend the similar method to obtain the boundary condition for the moving wall also. Now, these are the algorithm, step-by-step algorithm. Here you can see that you have to specify the initial condition because it's a time-dependent problem, and accordingly you can solve the first vorticity equation followed by stream function equation. Then if you are interested in obtaining the pressure, you can apply, you can solve the pressure equation to obtain the pressure field in the flow domain or in the computational domain. Now, do we require upward scheme to be discussed? Upward scheme already you know, because if there is a problem, so actually I try to discuss the upward scheme because I think upward scheme is most familiar to you, right? You know what is the upward scheme, correct? All of you know what is the upward scheme. Why it is used for convection, for the convection diffusion problem. In the convection dominance of the diffusion, there might be a numerical stability. For that, basically upward scheme is basically used. So what I have done here, basically I have explained the upward scheme, what is the need of upward scheme. If I do not use upward scheme, you may get an imaginary solution. You may get some unrealistic solution of the numerical problems. That's why I have introduced problem, and you can see what is the upward scheme basically. So what I basically have done is a typical fluid which is moving in a domain at a velocity u0, and this is the temperature boundary condition given. Inlet temperature is T0, outlet temperature is T1. There is temperature variation, and this is a typical governing equation. This is a convection diffusion problem. You can see this is the convection term and this is the diffusion term, and in the situation this problem can be extended or can be making dimensionless by Piclet number, which is basically dimensionless number which dominates, which basically tells you about the dominance of convection over diffusion. If the convection is very high, if Piclet number is very high, if you solve this problem numerically, you may get a numerical instability, or you may get a solution. That solution may be may not be realistic. You may get some solution where you can get some negative. So that's why I have shown here that this is a typical solution you will be getting here for convection diffusion problem if this Piclet number is very high. Now, if you do the corresponding numerical solution, you will be getting some solution for high Piclet number where temperature becomes negative. In reality, temperature may not be negative. Temperature should be always positive. So this is an unrealistic solution. That's why you have to apply upwarding scheme to compensate this numerical instability or compensate numerical error associated with this solution for the with the finite difference method. So here what is the upwarding scheme? If the velocity is going in this direction, theta I should be theta I plus 1. That means you are giving weightage to the upwarding terms. And suppose here velocity fluid is moving in this direction. So here what I am doing actually, you are giving weightage to the upwarding term, and similarly for the opposite case you are giving weightage to the downwarding term. Accordingly you can stabilize the problem. You may get a realistic solution if we do this. Basically everywhere you have to do this, because upwarding scheme is very important. In all many situations you may have a high Lewis number flow where the convection dominance of the diffusion, you have to apply this upwarding scheme. Then so limitation of upwarding scheme may not be very much, may not always give you a correct solution, because it may introduce a false diffusion. False diffusion means it basically introduces an additional diffusion. You can call it extra diffusion to the problem. This is called false diffusion. So that's why you have to be very careful that where to apply upwarding scheme and how to apply upwarding scheme. Upwinding scheme, basically there are many types of upwinding scheme. Here actually what I have shown is the first order upwinding scheme. You may have a second order, third order upwinding scheme. Third order upwinding scheme generally known as quick. So second order upwinding scheme is basically instead of taking one upwinding point, you have to take two upwinding points. For the quick third order upwinding scheme, you have to take two upwinding, one downwinding. So downward point. So this way you can manage the, you can obtain the solution for the numerical problems. Then we have a primitive variable problem, primitive variable approach. So far we have discussed stream function vorticity method. Now we can see what is the primitive variable approach. Here, instead of considering stream function and vorticity, we can directly solve velocity, u velocity, v velocity, pressure for the inter flow domain. Because in a stream function vorticity, there is one important issue is that it may not be applicable for the three-dimensional situation. For the three-dimensional situation, or maybe for the two-dimensional situation, you can apply this method, primitive variable method, because this is the only method that is being used everywhere. All the softwares you can see, COMSOL, ANSYS, all of the softwares, because they apply this method to obtain the numerical solution for the problem. So how it can be done? It can be done basically, let us see, you cannot apply this primitive variable method directly, because there is an issue of this primitive variable method. What is the issue? Suppose, let us consider a one-dimensional situation. This is one-dimensional Navier-Stokes equation. Sometimes it's called Burger's equation. This is a one-dimensional Navier-Stokes equation, one-dimensional steady state Navier-Stokes equation along the x direction. Suppose you have a pressure field like this, OAB pressure field, 100, 300, 100, 300 like this. Now, using the conventional grid points, if you discretize this problem, you will be getting this kind of discretization, right? Now see what is happening. You have applied central difference scheme. Now what is happening? Pi plus 1 minus Pi minus 1. That is you are getting a derivative of the pressure at the alternate grid points, this one and this one. If your pressure field is wavy, that is you will be getting a pressure field which is 0. Fluid flow is happening without having any pressure field. It is completely unrealistic. That's why it is called, similarly, you can see there is no pressure field at all. Similarly, for the two-dimensional situation, you have a checkered board of the pressure. Checkered board basically, you may see the chessboard, right? Sometimes it's called checkered board. Chessboard basically is a manifestation of checkered board. Chessboard like this. So if you have this kind of pressure distribution, 100, 300, 100, 300, you may get a velocity field or you may get a pressure field where there is no pressure field at all, but fluid flow is happening. Under this situation, if we use conventional grid, you may get an erroneous solution or sometimes no solution at all. Okay, that means pressure and velocity, they are not coupled with each other. This problem is called pressure velocity decoupling. That is, pressure is completely decoupled from the velocity. Pressure is not talking with the velocity. That is the problem. So how to mitigate this problem? The problem can be mitigated by introducing a special technique that is called staggered grid. What is the staggered grid? Staggered grid is that is a typical signature of staggered grid. Staggered grid is something like that. Vector, if it is a velocity, if it is a magnetic field, if it is electric field, vector should be specified at the cell faces. Scalars, pressure, temperature, concentration, whatever may be, it may be specified at the cell center. So you have to choose a cell, you have to write a computational cell, you have to create a computational cell. Instead of using conventional grid, you have to choose a special type of grid where vectors are specified at the cell faces, scalars are specified at the cell centers. This is the way the staggered grid is basically developed. So this is the thing. If you use this staggered grid, you may basically what will happen? You may get rid of the issue that is happening with the conventional grid. That pressure velocity decoupling issue is resolved. So how it can be done? So it can be done. There are many methods in this class basically, or in this workshop. I shall be discussing only two methods. One is first very primitive method. This is called simplified marker and cell method. SMAC. The first that is all developed. Then I will be discussing another method. It's called simple. That is semi-implicit method for the pressure link equation. You already know explicit and implicit method. SMAC is basically explicit method, and simply basically is an implicit method. Although it is called semi-implicit, but it is basically implicit method. So SMAC method, what is SMAC method? SMAC method basically, if you use this SMAC method, it considers the prediction and correction kind of stuff. So here basically it is a cyclic method where you guess the velocity, then you correct the velocity. So you guess the velocity, you obtain the guess velocity field, then you obtain a pressure correction equation, correct your corrected pressure, then you correct the velocity and keep on iterating and keep on repeating this solution continuously until and unless you get a converse solution, or until and unless if a problem is unsteady, you get a dynamic steady state solution. So what is that? So in this method, basically pressure velocity coupling is achieved. So how it is done? So let us say you have a, so in this method basically you have a predictor. First is you have to predict the velocity, then you have to correct the velocity. What is the predictor? So first is basically let us consider that you have a predicted velocity u star and v star. Now, so your x momentum equation can be written like this. Suppose p is my present time step. So this way of discretizing the equation is called pseudo discretization. It is not always to write your discretized equation in IJ form. You can also write this equation in this form. It's called pseudo discretization method. So I am writing this in pseudo discretization method. This x momentum equation can be written like this, and y momentum equation can be also written like this. Now, what is the velocity predictor equation? So we have u star minus u star is the predicted velocity for the x momentum, v star is the predicted velocity for the v momentum, p is the present time step. So I am solving this problem explicitly because only u star is unknown, all other terms are known. All other terms, how it is known? It is known by initialization. You are providing or you are prescribing some initial condition. For the initial condition, all other terms are known. So from here you can get u star, and from here you can get v star. So this is called a predictor step. You have predicted the velocity u star and v star. With the predicted velocity, what you have to do? You have to correct the velocity. How you can correct the velocity? Again, what you have to do? So let us see 1 minus 3, that is equation number 1, and if I subtract with equation number 3, you will be getting this equation up plus 1, that is the equation for the next time step, equals to u star minus del t by rho del p prime del x. What is p prime? Basically p prime is the differential between the pressure at the present time step and the next time step. We call it pressure correction. And here you can see p plus 1 equals to u star minus del t by rho del p prime del x. Similarly, if I take a derivative of it, del u del x equal to p plus 1 equals to, similarly just doing the derivative, you will be getting this equation number 4. Similarly for the v momentum equation, if you subtract it, you will be getting v plus 1 equal to p star minus del t by rho del p prime del y. Similarly, if we take a derivative, you will be getting this equation. This is a pressure correction. Now note that I have got an x momentum equation, I have got a y momentum equation, but I do not have a pressure equation. What I am getting here, I am having a pressure correction term. So how to obtain the pressure correction? Basically, you have to numerically, when you are solving a numerical problem, you have to make sure that the solution always satisfies the continuity. That is, it is continuously satisfying the continuity. Then only you can obtain solution of a numerical problem for the considering the fluid flow equations. So what is there? So you have a del u del x p plus 1, del u del y, del v del y p plus 1. So now you have a continuity equation. Note that continuity equation should be always satisfied. Without satisfying the continuity equation, your flow field is not possible. Your solution is completely absurd. So you have to satisfy the continuity equation. If we substitute it here, you will be getting same substitution. So finally you will be getting del 2 prime del x2 plus del 2 prime del y2 rho by del dt, this equation. Del u star del x del v star del y. So del u star del x del v star del y you already know from the predictor equation. Then you can solve this p prime. This basically this right hand side is already known, left hand side is unknown. That is the pressure correction. This equation is called the famous pressure correction equation. So this pressure correction basically it is nothing but a Poisson equation for the pressure correction. Boundary condition, all are Norman boundary condition. No. With this you can easily solve this equation to obtain the pressure correction. Once the pressure correction is obtained, you can correct your velocity. You can correct your velocity e plus 1, up plus 1 and vp plus 1, and finally you can get the solution for the velocity and pressure. This is the step-by-step algorithm for the math. So initialization, you have to initialize all the conditions. You can also set the boundary condition and the initial condition. Then you have to obtain the velocity prediction. Then you have to obtain the pressure correction, and finally you have to check the RMS. If it is convergence is not satisfied, you have to keep on iterating the solution until and unless you get the convergence. This is the first math. Similarly for the simple, this is called semi-implicit for the special equation that is developed by Patonkar. It is nothing but an implicit method. What you have to do is basically, here there are two inner loops. We call it inner loops. Instead of having a continuous loop, you have an inner loop. What are the inner loops? You can see in the first inner loop, this is the equation for the first inner loop. Here you can see in the momentum prediction, velocity prediction equation, here this is u is your variable, v is your coefficient. Coefficient has to be fixed at the present time step, variable you have to solve implicitly because you can see all other terms are unknown except up and vp. So here this equation can be solved implicitly till convergence to obtain the velocity prediction term u star. Got it? Similarly for the velocity prediction term v star, you can see here u is your coefficient, v is a variable. So you can solve this equation implicitly till convergence to obtain your predicted velocity v star. So you have got a predicted velocity u star, you have got a predicted velocity v star. Once you have obtained first these two inner loops, you can solve this Becher correction equation same. Then you can correct your velocity v u plus 1 v plus 1 and keep on iterating this solution. This is the method for simple, and this is the step by step algorithm for the simple. Finally your predicted velocity u star v star, then accordingly you can solve your correct the solution, and finally you can obtain your converged solution for the entire problem. So here actually computational effort is important, because for each inner loop you have to solve this equation implicitly for the variable velocity, and you can finally obtain the solution by solving the Becher correction equation. For all the computational codes, if you write your three-dimensional code or two-dimensional code, the most critical term is the Becher correction equation. Becher correction is the most difficult term. If you can solve it easily, your solution is done. So all other numerical schemes that is being developed, yes, that is being developed so far correct. So that is primarily how to tackle the Becher correction equation. If you can tackle Becher correction equation judiciously, you're solving this problem, numerical problem, with computational fluid dynamics techniques, simple or SMAC, whatever algorithm you are using, it is very, very easy and straightforward. Going to the paucity of times, I am not going to details how to discretize this equation. This basically, you can see the cell center is scalar and cell faces are vector. This is the way it has to be discretized. You can call it I. So there are three indices basically I have considered. You can I plus half, j plus half basically. You can use ij, lm, nk, whatever you can consider. You can discretize this equation. I am not going to detail. And boundary condition, all you know, simple boundary condition, Dirichlet boundary condition for known values. At the wall, your no-slip boundary condition, and pressure at outlet, your fully developed at the outlet, pressure is ambient pressure at the outlet, pressure P equal to 0. Similarly for the P prime, pressure P prime equal to 0 at the outlet. Thank you very much. This is all about the finite difference method. So if you have any question, maybe I can take maybe one question. I can take maybe one question, because we are running out of time. So if you have any questions, though it is a very simple and fundamental of finite difference method. So I may take maybe one question from if you have any. I think most of you already know this method. Yes, please. Correct. So implicit scheme, basically what I am doing here, implicit scheme, it is I am solving a matrix equation, right? So here we do not require any stability criteria. That means implicit scheme, it is always gives you the solution, which is basically solution of Ax equal to B, this kind of situation. So you do not put any conditional some criteria which will make the scheme stable. But for the for other scheme, explicit scheme, here basically you are solving the entire problem iteratively. So you require some criteria to be satisfied to get the solution, to get the solution without having any condition to be put in. Okay. Thank you very much.
Thank you, Professor Sandeep Sarkar. So basically this is a very short time, so it is very difficult to explain all of things of the CFD. So I hope all of you understand the basic concept of the CFD. So if you have any questions, so please feel free to contact me in a lunch session. So you will contact me. Okay, thank you.
Thank you.
So now next presentation will be delivered by Arnab Dey, Professor Arnab Dey. He is the associate professor in the IIT Guwahati. So I would like to request Professor Arnab Dey, so please present your presentation.
Kharagpur, these are the only two equations we need. And for problems with heat transfer, note to the energy equation is the result of first work turbine. These are the three equations. Conservation equation and informal solution. Something also explained steam function what is equivalent. Steam function what is equivalent is not exactly a physical system, it's a derived, those are derived equations. If I write those equations also separately, steam function what is equations have two equations. One is called what is the transport equation. Again, and the steam function equation. My purpose of writing this equation, except for this equation and this, all these three equations, which are basically known as transport equations, they can be cast into a simple form, which is known as convection equation. If you look into this equation, first of all, this one is conservation of momentum or transport of momentum. Here you can see there are several terms. We start with the unsteady change of momentum. This one is convection of momentum, this is diffusion of momentum, and this one acts as a source term for pressure. Source term, the pressure gradient acts as a transport of momentum in any domain. Coming back to the energy equation, this is also basically a simplified form of transport of enthalpy. This is the unsteady change of it. Again, a convection transport, diffusion transport. If you come to the velocity transport equation, again, it's a derived equation. This can be derived by taking curl of this equation. This equation again has an unsteady change, convection mechanism, diffusion mechanism, and a source term. So if you try to relate between them, all these equations have couple of common terms. One is unsteady change, convective transport, diffusive transport, and source term. It may be present, it will not be present. It is a source term, this is also a source term. So if we remove all these equations, we will find a single equation which has a close resemblance to all these equations. Generally called as generic convection diffusion equation for any property. I have written this equation. This is a generic convection diffusion equation for any property phi. This phi can be mass, density, it can be momentum, it can be enthalpy, it can be velocity also. So the idea is, if we can cast all the transport equations into a single equation, then it is better to deal with this equation instead of going into the separately momentum equation, energy equation, and so on. By doing so, actually by treating this equation, we are actually devising solution strategies or methods for all conservation equations. So we will be dealing with this equation. If you look into this equation, if you replace phi by velocity, s phi by gradient of pressure, and gamma by 1 by constant by becomes the momentum. Similarly, if you replace phi by temperature, this quantity by 1 by azimuth here, and this quantity may be a internal generation, then it becomes a constant energy equation. So this equation suffices for all the transport equations that generally we deal with. Another kind of equation that is here. This is also not so popular, but unfortunately, this type of equation creates the most computational burden on any system. This is a, and as far as classification of perceptual equations are concerned, this has, some of you already know, this has characters of parabolic type, that means time marching, while this one falls under elliptic equation. These are called Poisson equations. Simply speaking, Generally in incompressible flow, we deal with two types of equation. One is generic convection diffusion equation, second order. Diffusion term brings the second order, and the Poisson equation. So it is sufficient in incompressible flow to learn solution techniques of convection diffusion equation and Poisson equation. If you are through with the efficient solution of these two equations, you are more or less through with majority of the solution strategies, except for few minor details which is actually very typical of incompressible flow, which I will explain to you. In incompressible flow, I write the two-dimensional equation, incompressible constant harmonic equation in component form. U and V are x and y component of velocities. I am not writing. All that now. U will be x and so on. Then you have minus x to the y. This is essential to discuss incompressible flow. For isothermal flow, these three equations are sufficient. Now, when we write the equations, we should know the role of these equations. Otherwise, it is difficult for us to treat those equations in its correct context. What I mean by that, in this isothermal situation, there are three unknowns. One is velocity and pressure, two components of velocity, U, V and pressure. So there are three equations, that is sufficient. So we have three equations, three unknowns, no issue on that. But now we have to assign a proper role to each of these equations. Naturally, this is the x momentum equation per unit volume. X momentum is rho u. Rho being constant, u actually represents momentum. X momentum. Similarly, v represents y momentum. Naturally, this equation should have the role of giving us the x momentum. This similarly, this one should have the role of giving us the y momentum or v. So this equation serves as the governing equation for v u. This one serves the purpose of governing equation for v. Naturally, what is left? Pressure. So this equation has to take the lead of giving you pressure. That is what is equilibrium in incompressible flow. An equation which is supposed to be a governing equation for pressure does not contain. As you can see, this equation is the governing equation for pressure in incompressible flow, not compressible. Compressible flow is a different area. In incompressible flow, mass balance equation should serve the purpose of giving you the solution for pressure. However, in that same equation, pressure is not present. So that is a peculiarity. You are going to solve for pressure using this equation, but that equation does not contain pressure. That creates the difficulty in incompressible flow algorithms. Majority of incompressible flow algorithms thus work on the principle that somehow using these two equations, we project or we predict a velocity field, which is of course going to be wrong because we do not know pressure. With a wrong pressure field or a guess pressure field, we propose an ad hoc velocity field. If you can use that over here, probably you can generate a new equation which can serve as a governing equation for pressure. Numerically, that those are predictor character type or projection type of method. This is the peculiarity in incompressible flow, unlike compressible flows where at least the equations and their roles are pretty straightforward. In case of compressible flow, you have density, two component of velocity and temperature. You have 5 equations, and in a compressible flow, pressure is usually calculated from the equation of state. So in compressible flow, at least the role assigned to each of these equations are straightforward as compared to incompressible flow. Coming back to the, so I will briefly explain how we actually deal with a convection diffusion equation and a Poisson equation, which are actually the building blocks of incompressible flow solution. Finite volume method, already Sunil has already explained finite difference method. In a nutshell, finite difference method approximates the derivative directly on a given point. If you have points, interconnected points which we call grids, at each of these points, you directly take up the derivatives in the original equation, some call it integrated form. I prefer to call them as directly taking the derivative and approximate directly the derivative over here. You take this derivative in this and you approximate it as y plus 1 minus y minus 1 by 2 delta x. Okay, the second was interpreted. So you are directly approximating the derivative in finite difference method. Remember, in most of the methods that we generally deal with popularly, they are called local approximation. What is local approximation? You have a domain, this computational domain. You are at this location. Either you are solving an equation at this point. Local methods only use values in the neighborhood. Say for instance, if I discretize this one, we will take into account these 5 unknowns. For solving this the equation or approximating the derivative at this point, we will take help of immediate 4 neighbors. That makes a 5-point stencil, we call it popularly. You can see, to solve this point, we are not taking help of the points from here. That's why these are called local approximations. Finite difference, finite volume, even finite element also falls in this category as local methods. On the other hand, you are part of spectral methods. Spectral methods, if not all the time, many times spectral method takes help of all the values. Suppose if you have a domain of business constant y line, in several spectral methods, we take help of all values along this line to calculate that this is a global method. The difference why I mentioned local and global methods. If you consider this case, here these 5s are unknowns. So if you try to write a algebraic equation, linear algebraic equation, then you will contain a1, phi1, a2, phi2, a3, a5, phi5. It was some unknowns on the right hand side. It means if you write the equation over here, your equation contains 5 unknowns. When that equation translates into a matrix, imagine in a row how many unknowns will be there, how many entries of a matrix? 5. Because this equation only has 5 scalar to the unknown multiples. A1, A2, A3, A4, A5. There are say thousands, sometimes lakhs, infinity, there are millions of unknowns. Among them only 5 non-zero entries are present in the matrix. That's why these are called, all of you know, these type of matrices are called sparse matrices. These are called sparse matrices. What? Simply speaking, sparse matrices are those matrices where along a row only a handful number of entries are non-zero, rest all are zero. There are other properties of sparse matrices. So local approximation methods actually lead to sparse matrices finally. However, when we go into global methods, it will give you a full matrix. If the number of unknowns in a x direction is suppose 1000, all of them are participating for solving this one in that equation. Naturally, when that equation is cast into a row of a matrix, 1000 non-zero entries will be there. So that will not create a sparse matrix. Global method will lead to full matrix, while local methods will result into sparse matrices. Sparse matrices are far more easier to handle because of efficient algorithms available to us. Now I move to finite volume. In contrast to finite difference, finite volume, I saw in the slides, there are 2 words mentioned. One is any geometry, if I remember, another one was conservation in finite volume. Finite volume is basically if you have a solution domain, we fill up that domain using volumes, finite size volume of our choice. It is not necessary that all of them has to be a rectangle or all of them has to be a quadrilateral. They can well be triangles. In fact, they can well be any polygon. But that is generally not used. Why to use a polygon when you can use simpler forms as triangles? Using 3 triangles is far more better than polygons. Why? Because a polygon will create complexity. In what sense? In a sense, a polygon will have more number of faces, sides. So your bookkeeping increases. To store a polygon, you need that many face coordinates, centroids, you need outward normal, and these descriptions you have to store, so bookkeeping increases. Moreover, as I said, local approximation, we need the neighboring information. In finite difference, if you remember, ij point as I minus 1, I plus 1, j plus 1, j minus 1. Similarly, here also we need to store the neighboring information. It's quite easy that each face, to imagine, each face of a polygon will have a neighbor. Because two polygons will share a face, only a face. So if you have a polygon, then suppose we have a pentagon, then there will be 5 sides. Each 5 sides will share its face with another polygon. So that you can see the multiplicity in bookkeeping. Generally, that's why we limit ourselves up to polygon. We do not go beyond polygon. Coming back to that, a region can be filled up using known shapes, triangles, quadrilaterals, rectangles, depending upon the complexity of the problem. And we, instead of directly approximating the derivative, we integrate the equation. Integrate each and every term on that finite quantity. So simple one is a rectangle, but it can be extended to any size finite. So we actually integrate the bounding information over a given finite volume. And the one single theorem that helps in approximating those integrals is the divergence theorem. Many of you already know divergence theorem is divergence of a vector over a given volume can be cast as this is V and S is the piecewise homogeneous surfaces. This integral means you have to carry out 4 integrals along these, and this. This is divergence theorem. This is the sole theorem. This is that only one theorem which extremely helps us, which actually helps us in approximating the integral. Sometimes, if the volume integrals are difficult to execute, we take help of this and we convert it into surface integrals, vice versa. Sometimes surface integrals are not easy to calculate, we convert it into volume integrals and calculate. Finite volume method is all about approximating integrals. First term was del phi del d. We integrate that over a volume, any given volume. Simply speaking, the volume is not changing, the derivative come outside, and this is the integral. Second term, this is a convective term, unsteady convective term. Now you see this term u dot grad of f, this can either be written as this or we can write this. Some of you already know this is known as conservative form. Conservative form of the same term. This is not the conservative form. This is the conservative form. Why is it conservative? I will come to that. What is the usefulness of it? Because if you write it this way, this volume integral is very difficult to compute. Because here you cannot directly execute the divergence. Instead, if you write this form, divergence of u phi, and you can see you can directly apply the surface. U phi dot 1 into this. What is the advantage of using this? After writing this can be cast as surface u phi n ds. dot ags is mass flux. So phi u dot ags. So this is basically mass flux. Now we have a volume integral here, this surface integral. Third term, diffusion. This is mass flux. Here, Laplacian. So if you have gamma phi whole square phi d. Again, you can this is a constant. This is a divergence of grad of phi dt. That leads to again gamma phi difference of phi dot ab using the same divergence theorem. Now you can see all the terms in the convection diffusion equation, and there was a source term. You can see all four of them here already simplified using divergence theorem wherever possible. Now you can see all of these to approximate those integrals. All we need to learn is how to approximate volume of surface integral. This is an approximation of volume integral. These two are surface integral, this is a volume. So we have to learn how to approximate volume integrals. Like what we did for finite difference as approximating derivatives. Here we approximate the derivatives. Here we are trying to approximate the volume integrals. Simply speaking, it can be proved that for any separate volume, I remove this and come to the volume. If it is any separate volume, in fact any separate polygon or any volume, it can be proved that phi dv on this entire volume can be approximated as phi located at the centroid of that volume times volume of this polygon is dp surface. It can be shown that volume integral is actually can be written as this plus order of any second order term. Here suppose it is delta L, or maybe this is delta L1, or this is delta L2, this is delta L3. So you can show that this volume integral, this approximation is equal as a second order accuracy. That is the truncated terms have delta L square, delta L1 square, delta L2 square, delta L3. If I write this as a simple Cartesian rectangle, it can be shown this is the order of the truncated part is a function of delta x square and delta y square and delta x times delta y. So that's why this is a we call a second order approximation of volume. Simply, the second order approximation of volume integral is taking the integrand at the centroid of the volume times volume of the cell or the polygon. That is second order volume approximation. If you want to move to the higher order of volume approximation, then things become slightly different. You have to introduce polynomial and so on. I am not going into that. This is a simple expression for a simple approximation for volume integral. Similarly, this is a surface, a two-dimensional surface, delta L, suppose, or a three-dimensional surface in a two-dimensional volume, or a face in a two-dimensional mesh. Suppose this has delta S. Then a surface integral yes on this surface again phi at the centroid of the surface plus second order. Again, a second order approximation for surface integral is also simply taking the value of the integrand at the centroid of the surface and multiplying with the surface of that surface area, or it could be a surface is basically a line. So these are was the equation. Using the second order approximation in volume, what we get is ddt times second order approximation is pi for any volume times dt. Volume is not changing with time. That can be taken outside the table. Volume times ddt of pi. Then this term I already have mentioned that this term finally leads to summation of all the faces pi at the face center times the surface. Second order approximation for divergence of q phi times ds equals second order approximation is integral over this is pi at this location times surface plus pi at this location into the surface, pi at this location into the surface, pi at this location into the surface. So we write it as summation of all the faces for each face, cell centroid, sorry, the face center and the surface. So this is simply writing the integral, but this is not correct. Why? Because divergence of q phi dot ds means this is between phi m. Why? Because we already have seen this is surface integral is r plus u dot m. And I already mentioned this one is elemental mass flux this surface u dot m ds. So this will turn out to be phase this quantity defined at the cell center mass flux times phi defined at the cell. U dot nds to this space. U dot nds to this space is mass flux passing through this space. U dot nds to this space is mass flux passing through this space. That means summation of all phases of mass flux times the unknown at the cell center equals this quantity. Again, I have already mentioned. Then we can take it of divergence of phi dv, which is gradient of phi dot m ds, and second order approximation is taking this quantity gradient of phi at the cell face time s. Gamma phi gradient of phi f s. Second order approximation for all the faces, and this quantity is equal. You can write this one as S I T. You already have seen volume, how to approximate second order volume integral. So this is the discrete equation. Discrete integral equation after approximating the volume and surface. What are the unknowns? Twice into makes what we call as P of any cell is the cell center. This is the unknown. Likewise, this is also an unknown. In finite volume terminology, most popular way of defining them is east, west, north, south. Never. So we have east, west, north, south, never. Now you can see. This equation is the government equation or convention equation. The original convention equation has been approximated on a cell whose center is P. Likewise, this can be again carried out on any cell with any cell center. So this equation is written for a particular typical cell with P as the cell center. Phi P is unknown. Unknowns are phi P, phi P, phi A, phi S, and so on. Now you can see. Only on this term phi p is present. Elsewhere phi p has not come up yet. That means we have not written these terms, these approximated terms so far using the unknowns. So this equation is of no use unless we again further simplify or write this equation term in terms of unknown. Unknowns are phi p, phi d, phi l, phi n, that is cell center. Face center values are not unknowns. There comes in method of interpolation, both for 2D as well as for 3D. The task is, you know the neighboring values, you need this flexible. This is interpolation. These are the unknowns, but in your equation 5 appears. In Kharagpur terminology, we call this one as small e, east neighbor. East face, west face, north face, small. Now you can see at small e, that is east face, the unknown is an interpolation between P and E. While at N, it is an interpolation between P and N. At W, it is W and P. At S, it is P and S. So it doesn't matter if you want to move to a better or higher order approximation. Higher order approximation in a sense, at small e, that is at east face, if you want to go for fourth order interpolation, then you have to take two unknowns from the right and left. In that case, small e value will be calculated using E. Let's call this one as EE. From left, E and up. So you can now guess that if we limit ourselves to the second order approximation, the unknowns that is appearing finally in this equation are less. If we are limiting ourselves to second order approximation, this equation will only contain east, west, north and south. And of course, similarly this also. The difference between this and this is here you have to approximate the unknown at the face. Here you have to approximate the gradient of the unknown at this face. Either way, a second order approximation will only demand one unknown from either side. That will make it a unknown equation. If you try to go beyond second order, it will bring in this, and this. That will another 4 unknowns will be added. It will become 9 point stencil or 9 point equation. If we do that, finally, this is what we actually were doing. So finally, after doing this approximation, we verify this. They bring like this. If we apply the conservation diffusion equation over here, then we actually get AS for S, some constant into for S, beta into phi W, then AD phi plus AN phi equals to B. Right? Starting from the conservation equation and resulting this algebraic linear equation for a given step. Any one of you have any doubt at any step, quickly you can ask me now. We started from the conservation diffusion equation. We used finite volume, correct? We integrated the each and every term. Then we approximated by second order approximation the volume and surface integrals. Finally, achieve a linear algebraic. Now you ask yes.
Sir, what is this DP?
DP is the source term.
Source.
Source term. What they can suppose. You have this. Okay? In the first term, the absolute term gives you this. Now basically it's a time derivative of time. Now comes time integration. How do you use time integration? Already previous slides tells you that it is Euler explicit method you have to write phi n plus 1 minus phi n divided by delta t. Now tell me, we are writing this equation for n plus 1 because it said this equation contains time derivative, first order time derivative. That means these equations are perceived as, imagined as time marching type of So they have time marching type of solution. That means time marching in the sense we know a particular solution at a particular plane, using that we will march to the next time plane, using that we will march to the next time plane, and this process will continue. That means we will march in time. If that is so, the only way out is we know the solution at nth time scale. Using that, we will predict the solution at n plus 1. Naturally, the unknown is n plus 1. So this is the unknown, right? And this is the known. This will be able to write this. So this is one of the ingredients in the vector EP. Why I am calling it vector? So far, it is not a vector. It is a scalar. It is written at a particular scale. This is the origin of all the solutions. It may not be present, it may be present. And similarly, there can be other terms also. Say for instance, if you look at your convection equation was convective term was this. Okay? This was your convective terms for the transform equation of phi after executing the volume integral into surface integral, and further we have used second order approximation. Now this has to be approximated at consider this equation. Here dt equals some function g of a and b. Why I am writing this? This equation actually solves the purpose of time integral. There are two types of independent variables in all the equations. One is spatial, another is time. So if you approximate the spatial derivative, time is still continuous. In this equation, time is still continuous, while the spatial points are discrete. What do I mean by that? Spatial derivatives are no more continuous. They have been already approximated in terms of discrete values. That's why here, when we have written this equation in terms of phi n, all the spatial points are discretized, but the time derivatives are still intact. They are continuous. And that means if you write the equation, such an equation, they can be cast into this form. Or in other words, you can write this one as dIP dt. After the approximation of the volume and surface integral, we can write this equation as dIP dt equals a function of phi p, phi e, phi n, phi s. Is that correct? This is the form that we get after the volume and surface integral without touching the time derivative. So this equation has a closed result known as surface. Now we have to learn how to approximate a initial. This is called initial value. How to approximate this? This type of simple first order system is based to understand how to approximate time derivative. This can be written as phi n plus 1 as phi n plus delta t by 2 g function taken at n and n plus 1. This is what is your time result. This is the second order method. F n plus 1 can also be written as f n plus delta t times gn. This is what the previous teachers mentioned as explicit, purely explicit. This can also be written as phi n plus 1 equals n plus delta t gn plus 1. This is an implicit. You all are aware of what is implicit and explicit. Explicit is something which can be calculated then and there. There is no need to consider anything else. Implicit method means you cannot calculate a single variable independent. Others are also being influencing. Generally, implicit techniques, methods lead to system of linearity. So these are the approximations. Naturally, you can appreciate that understanding time integration is so easy from such a means. This is called a first order system. A at t equals 0 is given. A first order system with the integral. This is the analog or a first order time system. We generally learn time integration techniques, various time integration techniques on this. Once you learn this, applying the same over here is not a big deal. Earlier speaker also mentioned about fully inclusive. I mentioned it here. It is true that if you remember the momentum equation has time derivative in the left hand side. If you take all other terms to the right hand side, there is not only one function. There is a conversion function, there is a diffusion function, there is a source term function, there are multiple functions. So basically it has a shape as this. So if you spatially discretize it, then your final result will be like this, where before you actually touch the time derivative. This is the discretized values, spatially discretized values. This is a numerically approximated convective term, numerically approximated diffusive term, then source term. Now comes the semi-implicit, semi-explicit. Is it required that when we are approximating this in time, it is not necessary that also you know that in incompressible flow or in fluid mechanics, Reynolds number plays a very crucial role. If Reynolds number is very large, convective term becomes very highly important as compared to the diffusive term, and the nonlinear convective term gives rise to instabilities and flow complexities. Naturally, if the Reynolds number is high, convective terms being more important, we should focus more. We should try to approximate the convective terms in a better way than the diffusive terms, because if both of them are producing errors, it is the convective terms which will cause more damage than the diffusive. So we must admit that in a numerical method, all the ingredients in a particular equation, all the terms in a given equation are not of same importance. So that's why the error they are producing are also of not the same order or same importance. Thereby comes the idea of semi-implicit, semi-explicit. Maybe if we have an idea that implicitness brings in stability into the system and explicitness brings in easiness into the system, you can solve a system very easily if it is an explicit one. However, if you add some implicit form into it, then it becomes more stable. That is, at least the geometrical perspective tells us that. Then suppose G is convective term, H is diffusive term, and I is source term. At slightly higher Reynolds number, we all know beforehand that G is much more important than H and I. Naturally, the point comes, should we treat G in the same way as H and I? The answer is no. It is perhaps better if you can treat G more accurately than H and I. Or rather, if you can deal with G implicitly, then the term which is responsible for bringing in flow complexities are treated in an implicit way. That means actually you are bringing in some amount of stability in the system. Here comes the idea of semi-implicit, some calls it semi-explicit. Semi-implicit means some terms are treated implicitly, some terms are treated explicitly. Not all of them are treated implicitly. Semi-implicit and semi-explicit, these techniques are decided based on how much cost you have to finally incur. If you use this one as explicitly and this one as implicitly, definitely still your algorithm becomes a solution technique far more stable than the fully explicit method, but while doing it you are hardly adding any cost to the method. There comes the addition of other advantage of semi-implicit. Now, once we learn the time integration techniques of semi-discrete, these are called semi-discrete form. It's easy to understand why it is called semi-discrete. As I told you, there are two types of dependent variables. Independent variables. One is x, y, z spatial coordinates, another is t. So if you discretize only on spatial direction and keeping the time derivative fixed, intact, unchanged, it is better to call it as a semi-discrete form, because the form that you have now is only discrete in spatial direction. It still has continuous time derivative. So this one is a semi-discrete form. It is better to learn or analyze the time integration techniques on semi-discrete form. Once you have discretized the semi-discrete form in time also, you are likely to obtain this. Needless to mention, these are all unconstrained. If you recall what I said for higher order methods, for higher order methods, you already have noticed that in SSWW is appear. That means currently using the second order approximation, what appears as a 5-point equation. Now we become 9-point equation. Correct. Now this equation is written for this point. Now we can write the same equation for all the other points also. And we can easily say that all such points will create the same equation. How we can say that? Here comes the idea of structured and unstructured. You learn the idea of, understand the idea of structured and unstructured tree from this perspective, becomes clear. In structured tree, the neighboring information remains constant throughout the domain. What does it mean? At a particular point P, arbitrary point, what is its neighbor? East, west, north, south. There are 4 neighbors. In a structured tree, if this is a space, if we move to any point in the domain, we will always have 4 neighbors. That is what a structured tree is. A structured tree is every solution point in the domain will have the same number of neighboring points. Unlike it, in unstructured tree, it is not fixed. At some point of the domain, the number of neighbors can be 4. At some point in the domain, the number of neighbors can be other than 4. Now the difficulty is, in structured tree, once you have written one such equation like this at this point, since you know at every point the number of neighbors are like this case works out, so you can claim without actually executing the same approximation for all the points, all will have the same value, same form, but you cannot claim that the answer. In an uncertain field, as I said, there are points where the number of neighbors may not be 4. So for instance, this is an uncertain field. For this, 1, 2, 3, 4, there are 4 neighbors. So we take neighbors. For this triangular element, it has 1, 2, and the number of neighbors are not same. So naturally, you cannot write the same equation for this rectangular segment volume and for the triangular segment. The equation, that discrete equation will be different for both of them. That means you have to treat both of them separately. That is the difficulty in unstructured tree. Not only that, in structured tree, another beauty of structured tree is, you know, no matter where you are in the spatial point, who is west, who is north, and who is south, that can actually reduce or make your life easier in terms of storing the neighborhood points. You know, for every solution point you have 4 numbers of neighboring values. But for unstructured one, it is not so. Moreover, also, if it is a typically Cartesian mesh, it is a typical structure, or I say typical cylindrical mesh, there you can count them as ij. That means, you know, at point ij, the neighbors are I minus 1, I plus 1, j plus 1, j minus 1. It is because we are organized in such a way. In an unstructured grid, you cannot write it as an ij. If this is your mesh, here, you can take this typically this. This cell has I plus 1, I minus 1, j plus 1, j minus 1. What about this cell? For this cell, you cannot store it as ij or I plus 1. So in unstructured grid, the data storage is not so easy, or rather the neighboring information is not as straightforward as it is in structured grid. Now in staying in the structured grid domain, we all know that all the points, you can approximate the Conservation equation is a finite volume theorem to finally obtain an equation like this. 5 unknowns. If you start writing this equation for all the points in the domain. Suppose we start from here. This is the boundary. We first write this the equation over here. If you write the equation like this at this point, these two are unknown, that is known, but these two are not unknown. They are already known. Actually, you may ask, this point is not even in the boundary. There is no harm in that. This volume, the special treatment in finite volume that you use this volume as 0. If you use this 0 volume, then this cell actually lies on this space. That actually solves your problem. So, or this, if this is P, and if you use 0 volume over here, then south and west, these are known quantities. Agree? South and west falling on the boundaries are known quantities. That means in this equation, this term and this term are known, goes to the right. They are known, they go to the right hand side. That means if I write it in the matrix form, then I will have something like this. Three entries raised to will go to the right hand side. Here are the unknowns. For instance, suppose if you have a 100 by 100 grid cells, 100 cells in x direction, 100 cells in y direction. Total how many cells? 10,000 computing cells, 10,000 unknowns. Right? 10,000 unknowns. So if you mark them, number them, and if you try to finally write this equation for all of them in a matrix form, which will finally give you Ax equals B. The size of the vector X is 10,000 because there are 10,000 unknowns and the matrix A will have size 10,000 by 10,000, 10,000 rows, 10,000 columns. Typically, any point which is not adjacent to the boundary, this point, but not this point, not adjacent to the boundary, it will have 5 such entries. So if you move to any of these rows, there will be only 5 non-zero. That's local approximation. So 5. Also, note, when you are here, you can number in any way. In whatever way you number, like this, your number you can do like this. Your number you can do this also. Does not matter. In no matter in how you number them, if this number is 34, this can be 33, this can be 35, this cannot be 32 or this cannot be 30. So, all I am trying to say is, either way you number them, there will be difference in this, because they are not consecutive unknowns. That's why these are called banded matrices. How they look like? The main unknowns are like this. Immediate neighbor is this. Another immediate neighbor is this. Another neighbor is this. Another neighbor is this. So for this point, this is the value. This is the unknown. This point and this point belongs to this and this. However, these two are far separated from these two diagonals, because if this is 35, this is not 31. This is something else, far away from it. There are some diagonals. There are no diagonals here, but they are not immediate diagonals here. 5 diagonals. This is the essence of sparse matrix, or not sparse matrix, banded matrix. Why we call it banded matrix? Because this create a band. A band with 3 diagonals. These are also bands. Fortunately, these bands only contain only one diagonal. There can be matrices where it is sparse but not banded. The advantage of sparse banded matrix is, again, it has superior and established methods to solve very accurately and efficiently. Structure leads to sparse banded type of matrices. Now, I will again bring your notice to the higher order approximation. If we go for higher order approximation, I already have mentioned that east, north, south, south, and west, west. We bring in another 4 diagonals. That means instead of 5 unknowns here, there will be 9 unknowns. That means there will be 9 non-zero diagonals. Naturally, handling 5 non-zero diagonals is far more easier as compared to the 9 non-zero diagonals, unless the 9 non-zero diagonal method gives you significant advantage in terms of solution accuracy or something else. It is already known that in no way our common sense says that a matrix with 9 non-zero diagonals cannot have a simpler solution technique as compared to 5. Naturally, the higher order methods will give you significant advantage in terms of solution accuracy. If it does not, then common sense says there is no point using higher order. Now, we have established that all the conservation equations, when we have these methods, it was some research, some practice, some calculations also, but finally in a short time I have shown you that all the conservation equations using basically divergence theorem, then finally approximating the volume and surface integrals, forming it as semi-discrete form, then applying time integration techniques, they can be cast into a simple linear algebraic equation. And if you write all such equations at all the points, they finally form a sparse banded matrix in structured grid application. That's where finally is. Is there anything else? Because this is not a seminar on, I am not here for explaining linear solvers, how to solve system linear. Job is not done. Job is, I would say, not even 10% done from my experience. Coming to this stage, Ax equals B is not even 10%. Now starts the actual hard work. How to solve this Ax equals B. Think of it. Suppose we are handling a 3-dimensional problem. 3-dimensional problems always has more mess because addition of the third dimension. Typically 3-dimensional problems, finite difference, finite volume or finite element, number of volumes or number of solution points or elements runs into millions. Say for instance, a poor 3-dimensional simulation, 3 to 4 million, suppose 40 million unknowns. That means Ax equals B system has the size of the matrix is 40 lakh by 40 lakh. Very well. Now suppose you are doing a slightly complicated problem where it is not steady. The transient solution makes a difference. That means you need unsteady solution. That means you are time integrating delta t, 2 delta t, 3 delta t and so on. Suppose in time domain you need 10,000 time units solution. You have to integrate every time. So think about it. For one convection diffusion equation, you need to solve a 40 million by 40 million matrix 10,000. That is not the end of the story. That is the very beginning. As I already mentioned to you that all the momentum equation can be casted as a convection diffusion equation. So in 3 dimensions you have X, Y and Z. So 3 convection diffusion equations. I have not gone into the what is the pressure question equation and so on. For solving only convection diffusion equation in 3D, 3 convection diffusion equations constitute 3 systems of linear equations, each of size 40 lakh by 40 lakh and 1,000. Needless to say, you have to solve Ax equals B extremely efficient. Even you have to solve in a typical one, you have to solve Ax equals B in a blink of an eye. Unfortunately, in practice speaking, we start with SOR, possible, SOR successive over method. They are, truly speaking, they are, what should I say, they are pre-independence methods. They are not only not used, they are forbidden, they should not be used. Because that is, those are prohibitively costly. It is only good if you understand the formula where it comes from, or rather I would say Gaussian method helps you in understanding what a solution technique is, or rather a iterative method is, which probably will help you in understanding more complex solution techniques. So SOR, so you can think of it, if you have to solve a 40 lakh by 40 lakh matrix 10,000 times, SOR is just not the method to go. Because simply speaking, if you use SOR, in your lifetime you won't be able to fix it. In your entire lifetime. So that's why I mentioned that we have not even gone into the last 90%. Now starts how to solve system of linear equation very efficiently. Then comes parallels. Parallels is another something, and yes, already anyway I will be explaining some part of the parallels, but that is it is universally agreed that parallelism is a way out to multitask among different processors to speed up the calculation. Parallelism is from CFD perspective, from the acceleration of calculation. Something which is supposed to take, theoretically should take 1 year, can be brought down to maybe 5-6 days by using many core environment. I'll come to that later. Why I say all this? Just to give you a flavor that merely approximating the conservation equation into a simple set of algebraic equations is not the end form of CFD. Then starts the system of linear equations. If you start writing a code, if you develop something by yourself, reaching this stage is not going to take that much of time. With some amount of practice, understanding, and some amount of rigor, you can definitely reach this stage. But beyond this stage also, significant amount of work is there. You have to solve the system of linear equation very efficiently. I would say that is the heart of a linear. At least in incompressible flow, a linear solver is typically called a linear solver. A linear solver lies at the heart of any incompressible flow solver. Without an efficient, robust in what sense? Efficiently it does things very quick. Robust means today you solve for 1 million by 1 million, you are successful in solving that. Tomorrow if I give you 20 million by 20 million, it fails. That's not robust. So when we develop a linear solver, we also keep in mind that it should work for all possible systems, and not only you never know what kind of problems you are going to handle. For instance, there can be situations where, from practical experience, I will give you some examples. There can be situations where you will read rules like this, when the ratio of delta y by delta x is as close as possible to 1. From numerics perspective, from the iterative method perspective, that is the ideal situation. If your delta y by delta x aspect ratio of the mesh is 1, unfortunately that's not going to happen. If you use a boundary type of problems where delta y by delta x can easily go into the 10 raised minus 3 minus 4. So actually the ideal situation is 1, but you have to give it 10 raised minus 3. That's where robustness is. Because your matrix elements will be extremely poor. Matrix element, maybe some of the elements are in the range of 5 to 8, some of them are 10 raised minus 6. In a way, now comes the idea of condition. There is something which is known as preconditioning. Preconditioning means in different applications your matrix A, owing to the grid aspect ratio, Reynolds number, velocity, diffusion coefficient, and from the other perspective also, based on that your matrix is not, what should I say, it's not ideal, it's far from being ideal to solve. In those perspectives, for a robust solver, we have to condition that matrix in a state so that it can be solved very easily. That is the subject of preconditioning. Yes, sure.
There is no session after that. Yes, we have a session after this.
I don't know. Ask questions. Any doubt? What I did, I started with convection equation. Why convection equation? Because I have already showed you in incompressible flows, majority of the transport equation can be cast as a convection equation. So if you learn about one equation, that starts the purpose of all others. In finite volume, unlike in finite difference, we approximate the volume and surface. Using divergence theorem, then we approximate using second order approximation to finally reach to a semi-discrete form, and using the idea of time integration, we create discrete form, write them in the assembly into a matrix system that gives us sparse banded matrix. That's it. Nothing. If you have any doubts.
You have told about that semi-discretization. Discretization is only what not about that. But for get the solution, should we not completely discretize?
Of course, this is the complete discrete form. Semi-discrete form is, idea is you have two types of independent variables, as I said, x, y, z and t. If you start discretizing or analyzing them together, you may not be able to track the product. So the idea is first discretize x, y, z to keep the time derivative intact. There is no discussion on time derivative, only on x, y, z approximation. Once that is done, you are happy with it, you have a semi-discrete form. Now you apply your all ideas into the time integration. That actually helps you in focusing both the spatial as well as time approximation. But finally you have to definitely solve fully discrete. Anyone?
Okay, thank you for today. So we are actually in late, so we are feeling very hungry. So this is the lunch which will be placed in this just beside of this the mechanical engineering department, that is called the hydraulics building. So you go to this the hydraulics building, top floor, the lunch is arranged, and we will meet at that place at the 3 p.m. Okay.
Essentially, water will be back here, so the building adjacent to this.
Just adjacent this building, that is called the hydraulics building and top floor session. So that the session also delivered by Onlok Day, Professor Onlok Day. So I would like to request Professor Onlok Day, please you start your presentation.
বলবো না
Theme of this next 1 hour is supposed to be immerse boundary. Very popular these days for solving full flow equations in complex geometries as well as complex moving geometry. But before moving into that, quickly cover what were the conventional methods for handling complex geometries before immerse boundary came into being. I already have described finite method in typical Cartesian grids. Complex geometries, in simple words, complex geometries are those where the simple Cartesian mesh or cylindrical mesh maybe the object boundary does not necessarily follow the grid line, or it is impossible to make them follow the grid line. Those are popularly called as complex object simulation. Earlier, one of the most popular methods in the realm of structure was coordinate transformation. Coordinate transformation is, you all know, the advantage of simulation is Cartesian method, because I already have mentioned structured Cartesian grid has number 1, the matrix is sparse banded, number 1, number 2 is bookkeeping is extremely simple, number 3 mesh generation is straightforward, there is no need of any extra applications of utilities, constant x, constant y lines or constant r theta z line anyone can create with variable spacing. That's what is required in Cartesian mesh. The matrix simulation, the size of the matrix, complexity of the matrix, everything is much more straightforward and simple in case of structured Cartesian. So, if you can retain the basic calculation method in the Cartesian method, there is nothing like it. However, with complex objects which cannot be treated in a normal Cartesian grid, the method of coordinate transformation was very popular in those days. Coordinate transformation is basically Suppose the object is like this. Now, different transformation methods were thought of. Can we think of a transformation, coordinate transformation, which will make this apparently looking complex shape, can it be transformed into a line or say a circle? It is possible. And if you can convert it to a line or a circle, then perhaps we can use again structure field, if not Cartesian structure. Say for instance, if this one, this object, starting from point 1, moving to point 3 and then coming back to point 3. If we are transformed in such a way that 1 to 2 and 2 to 3, by some means, then we can only we can lay down the Cartesian. But that transformation is not that simple. All the time, such transformation is not possible using non-explicit or implicit force from algebraic expression. So there were methods to do it. One of them was elliptic transformation, elliptic regeneration technique, where the advantage of one of the property of Laplace operator is to be write down del square phi equals 0. Mathematically, this equation has infinite dimension. It is basically del square phi del x square, del square phi del y square equals 0. This means, whenever writing this equation, we are inherently making an assumption that phi has second order continuity. That if phi del x is not continuous, writing such an equation is not possible. That means the solution of phi, whatever solution of phi is, we are actually inherently assuming phi to be smooth. Smoothness means continuity of the first derivative. So if it is a second order, it has second order continuity, that means phi has smooth solution because it satisfies second order differential. This property was used in elliptic type of coordinate transformation. How it is like suppose that object. We have to create coordinate transformation using a certain complex shape. Now we had these points. Suppose the points on the 0 point on the boundary. We had these points. Now what we want is grid lines which are smooth. You can see the grid lines are basically intersection of two states of either parallel lines or nearly parallel lines. Now, where these curvilinear lines are coming? They are coming because of the shape of the object. Now, there comes the idea of using a Laplace operator, because we know that Laplace operator actually smooths out the solution. If we start with a rough estimate of any solution, and if we run phi over it, a Laplacian operator on it, it is bound to give you a smooth solution. Therefore, suppose if we start with the initial condition of coordinates, this is the geometry. We have these coordinates. And if we start with an initial case such as this, which are not modified properly. They are not going inside the object, but they are not smooth, or neither they are conformal to the body shape. It is create such an initial approximation and run on them the Laplacian operator. Suppose these coordinates are, suppose we name as psi, constant psi length and constant k. Now if you run it two generator, x plus psi equals 0 and x plus eta equals 0. What will happen is, if you solve with the initial case of psi and eta, which is not conforming to the object surface, and if you solve this equation, finally this initial condition will be smoothed out and you will get body conform on smooth mesh. Why? Because now psi and eta has second order property. Before it did not have initial condition, did not have it, and constant then in a way that they will conform to the solid surface. There were several different ways of doing it. Some used to use different type of layout, some used to use H, O, C. That's not the factor. But elliptic regeneration technique use this special property of Laplace equation. Naturally, there were two sets of coordinates. One is physical coordinate system, another is transform coordinate system. Physical coordinate system is composed of x, y, z, and transform one was psi and x. In x and y coordinates, the grid lines were conformal to the object and curvilinear. But in psi and eta, we used to use constant, not non-uniform or uniform Cartesian. We have to transform the equation which is actually described in the physical space to the transform form. Thereby, we used to get series of additional terms because of this transformation. This was the actual method of solving problems in complex geometry using coordinate transformation method. Definitely it has certain drawbacks. Number one, when such coordinate transformation is executed, we end up getting mixed derivative, which is not present in the actual equation. In the original physical equation, you only have either this or this, I1, I1. But going to the coordinate transformation, in addition to usual first derivatives and second derivatives, we used to have mixed derivative. One of the drawbacks having mixed derivative is in simple Cartesian difference form, for first and second derivative, we will only get unknowns as its immediate neighbors. As I mentioned, these two is not sure. But for approximating each derivative in second order approximation, all the common points will now come. This is one of the difficulties. Unnecessarily, the problem used to have a high diagonal setup in the matrix form, but when we transform into a transform domain, we used to have 9 diagonal. This is one of the problems. So it has severe limitations. Not all problems could be accommodated in using coordinate transformation, but that was the way out. And definitely another big alternative was unstructured grid. Also could take up unstructured data. Staying in the structured grid itself, this was one of the most popular way of solving infinite difference and both. Then inverse boundary theorem. Right? Inverse boundary actually uses plans to use. However, these days inverse boundary is also used in unstructured grid in lattice Boltzmann method also. But inverse boundary method came with the idea that no matter how complex the object is, we will stick to the Cartesian fields and we will make the object fall not on the Cartesian field. The idea is we will use only non-uniform Cartesian because we all know the advantage of using Cartesian fields in terms of set of algebraic equations, then bookkeeping and different algorithms also. It works so well for the Cartesian method. Now, inverse boundary method, any object in two dimension, any object is linearized. And shape of the object, we have to transfer the contour of shape of the object to the algorithm by choosing linearizing the object. Because the continuous object is not known to the mesh. You have to linearize it, means you have to create points on the object. Discrete set of points on the object and joining each subsequent points will give us a intercept. And these linear elements actually constitute the contour of the object. Obviously, more the number of such points, greater is the representation of the complex set. This is called linearization of the object. In two dimensions, we used to use only point, and joining those points gives us the object shape closely. In three dimensions, we have to use surface time. Because any three-dimensional shaped object can be created, the surface can be created by approximately its surface by set of triangles. So this is called linearization of the object. Either in two dimension by a set of points joining gives us linear segments, and in 3D surface triangles. Of course, when we generate linear segments or triangles, we of course know the coordinates, centroid, unit, outward, normal, and its neighboring information as well. This is the first technique, that is linearization of the object. Linearization. Once that is done, then we have a mesh. While clearly it is not necessary that we do not know beforehand how the points will turn out with respect to the mesh. Typically in immerse boundary method, this is called sharp interface. I will come to the other half also. Sharp interface means we actually describe the fluid solid interface by sharp interface between which is demarcating the solid and fluid interface. Now this interface has linear segment. Now based on the location of the cells, there are many categories of cells, but typically there are three types of cells. One is those cells which are completely outside the tree. These are tree cells. Unambiguously, we can detect such cells or points on the centroid of the cell. Such cells are going out completely outside the object. There are cells which are completely inside the solid. We call them as solid cells. And there are cells which have part of the solid and part of the usually call them immerse cells. Now, if you look at the equation, what the only the simple the boundary condition that needs to be implemented is we have to implement the boundary condition, that's no free boundary condition on the solid surface as now on the points of the centroid of this linear element is here. On these points we have to apply or execute the no free boundary condition. No free boundary condition also means that the object can move in certain direction. No free boundary condition does not always mean that velocity is zero on the. It is only a special case when the object is stationary. Only the objective is to enforce no free boundary condition on the linear element. And to do that, what we do, one category of method is called reconstruction. What is reconstruction? We can solve the Layer Stoke momentum equation as it is on the fluid cells because there is no object that is going close to it. Then there are cells which is inside the solid. There is no need to solve the equation because those cells are inside the solid. If the object is stationary. If the object is moving, things become complicated. But we start with the situation where the object is stationary. In case the object is stationary, the solid cells are completely out of computation because they do not mean anything to us. It is only the fluid cell and to the extent interface cells. In fluid cells, there is no complexity because we can directly solve the areas of momentum equation in our usual approach. But it is the interfacial cells which will now help us in enforcing the boundaries. Now, what is that? Reconstruction techniques. If I zoom the given linear segment, and now this is the S. There are several possibilities to which we can do that. First is, suppose this is the centroid of the linear phase. Here we have to implement the boundary. Now we have to, this is the interfacial cells. This is also interfacial cells. This is also interfacial cells. This is also interfacial cells. Our solution domain will contain only the fluid and interfacial cells. Will remove all the solid cells because they are of no consequence. Now one of the way out is, but that is not the only way out. One of the way out is we draw a perpendicular on the centroid or the points on the solid surface, and we identify either sides of that perpendicular. Depending upon what interpolation technique we want to use, suppose we want to use a bilinear approximation. If we want to use a two-dimensional, if we want to use a bilinear interpolation involving the cells around that interfacial cell, then we need three constants. There are three unknown constants over here. To fix such a polynomial on these interfacial cells, we need to identify three cells because we have three unknowns to calculate. To calculate these three unknowns, we have to write three equations, and those three equations will come from these three. So basically, we choose one of the ways to draw a perpendicular. We choose which are the points which are closest to this perpendicular. For this particular illustration, these and these three points. These 3 points are falling very close to the center. For doing that numerical it is not so difficult. On every point you can draw a perpendicular on it and compare the perpendicular distance. By doing so, we can identify 3 of those points which actually are coming close to the perpendicular. Then we can write this equation on these 3 points and solve these 3 equations to get these 3 constants. Now you can see those 3 equations will contain a solution from here. So now that means in the fluid cells we are having the Navier-Stokes equation, and for each such centroid of linear element we will get an equation, this matrix equation which contains 3 by 3 system for each such point which couple the fluid and interfacial cells. That means, and we solve them together. The fluid cells are being solved without the knowledge of the interfacial cells. While for on the solid surface, for each such centroid of a linear segment, we solve the 3 by 3 equations before using the bilinear system, which couple fluid and interfacial cells. That means all the fluid cells and interfacial cells, if they are solved together, then we can actually sense there is a solid object, or rather we can sense there is a point over here where this boundary condition is. Here, this is one of the ways of implementing the boundary condition. But there are a number of difficulties in doing executing this. First of all, I am ready to talk of example. Suppose this is an object. It is not so easy because we need to make a lot of compromises. Suppose this is an object. This is an object. And this is the base. There are many situations where the object shape is so that it is very, very difficult to identify such points in certain location. In this location, it is extremely difficult to find three cells. Or in other words, it is difficult to write an equation which will come to nearby 12 trillion cells. So these are the difficulties that we need to what I write a plus bx plus cy. This is supposed to give you a three-by-three matrix. In many situations, going to the complexity of the object or target of the object, these matrices turn out to be singular. So those are exceptional situations where we have to make certain compromise. Number one. Number two, it's extremely another point is extremely important. So you are not introducing parallelization, but that comes in.
Sir?
Yes.
Sorry to interrupt you.
Yeah, sure.
How you are identifying, I think whatever you have told now, it is only to identify the interface. My question is how to identify which cell is fluid, which cell is solid, and which cell is at the interface.
There are popular techniques to do that. There are two popular techniques. One is ray tracing, another is dot product. Suppose this is an object. If you are outside the solid, if you pass any ray, it will intersect the object twice, even number. If it is inside, it will intersect odd number. Either it will be 0 or even number. It does not intersect. It intersect twice. If it is outside, but if it is inside, it will only intersect only once, odd number. If the complexity of the object increases, odd even intersection will always remain. But this is not the safest one. This works. This is not the safest one. I prefer to use one. This will always work. For a linear element, you know its information, you know the outward norm. This is the solution. So you know the outward norm. Right? So if you want to find out whether a point is outside or inside, what you do is you join them and find out the position vector of it. And then you take dot product. Positive and negative dot product will automatically give you whether the point is inside or outside. This is called dot product method of finding out whether the point is inside or outside. There are other methods also. Because this does not require too much of analytical calculation. And IRC is extremely robust. There are other methods also which comes in diffusion methods, that is level set type of method. I was about to mention what are the principal difficulties in inverse complementar. To me, one of the most disadvantage in sharp interface method is the following. When we are into Cartesian grid, analysis always involves interface between two processors. That we will discuss tomorrow. That is called domain decomposition. The most popular way of executing parallelization and multitasking is domain decomposition. Means the operational domain moves between several parts. Each of these parts is assigned to a particular processor. Each processor will handle only that part. Suppose this is a part which is handled by P1, this is P2, this is P3. Simply speaking, without not considering the object right now. If you are at the cell which is adjacent to the interface, you need an information from here. Grow up, this is this. This is the interface between P1 and P2. This is the Cartesian cell. Where you are calculating. To calculate the solution over here, this never falls on P2, which is not known. That means to complete your calculation, this information has to be passed to P1. Similarly, to execute the calculation over here, this is not known. This has to be passed to P2. these are called point-to-point communication in parallel. If we have 5 points stencil, then in 2D, one layer from either side of the interface has to be passed to the left or right. One layer. If we use higher order methods, as I have already mentioned, in addition to east, if you have east, this is also required, I have already mentioned. For second order approximation, you have 5 points stencil. For higher order approximation, you have 9 points stencil. You need EE. So if you need EE, in addition to E, then 2 layers of information has to be passed to this processor. Similarly, from these 2 layers has to be passed to this. This is the way one-to-one communication on the either side of it, 2 interprocessor boundaries work. That's how parallelization goes on. Now, with the advent of introduce the image boundary, things become even more complicated. Suppose this is the object. And this is a linear element. And to enforce boundary condition here, there are, as I have already mentioned, one of the ways is to identify 3 points, 3 fluid and interfacial cells. Suppose 2 interfacial cells over here and 1 interfacial cell. That means we have to pass this information to this point. I have only given you one example. Typically, in dimension, the number of linear elements are not more than, I would say, 5 to 10,000. 5 to 10,000 is too much. Generally, it does not go beyond that. But in 3 dimension, complicated objects can have 1 lakh triangular elements also as surface condition. So think of it. For each and every such linear elements or triangles, first create its neighborhood for implementing the boundary condition. Then we have to track which of these points are in which processor, then pass it to the next processor. It's extremely complicated job. There is no doubt it can be done, but it's an extremely complex approach. So we must implement the sharp interface method, where we actually reconstruct a stencil to enforce boundary conditions. In serial calculation, when all the computing points are actually handled by a single processor, that complexity does not arise. When all the calculation is carried out simultaneously, concurrently on all processors, we must know that for each such system is a two-by-two system, which is required to be solved so that the boundary condition is enforced on a solid surface. We must know that among those 3 points, which are those points which are lying on one processor and which is not in the neighbor. It is not certain that always those 3 points will lie on the neighboring processor. It is quite possible that some of the points may lie in a processor from where otherwise there is no communication required. Communication is only required from a processor from its left and left and right neighbors. But maybe because of sharp interface method, there are points which needs to be passed to a processor. Otherwise, there is no communication required. There is no doubt from parallelization perspective in communication dealings. Image boundary method, sharp interface method creates a huge difficulty. Next, even more difficulty with image boundary method, which is the most established reason for adopting or rather modifying sharp interface method. Understand this. Suppose this is an object. If this one starts moving at a certain t, this is at this goes. Now the grid is always fixed because we never thought of moving the mesh as we do it in arbitrary Lagrangian variation. That's a different method completely. That mesh deformation, mesh is actually always body conformal and mesh is also moved with the object periodically. Remesh. That's different thing. Our starting point is mesh is always fixed. The philosophy in image boundary method handling a complicated moving object is mesh is always Euler. That means mesh is never going to be moved. Mesh will be always fixed, while the linearized points on the solid surface will keep moving according to the motion motion of the object. We call them as Lagrangian set of points. It means the Lagrangian set of points which defines the object will move, while a Eulerian set of points on the grid they will remain fixed. Now the problem is, if this is one situation, you can see this cell is completely inside the cell. But at the very next time step it is quite possible, depending upon the speed of the object, that same cell might become interfaced. Or even make it more complicated, with a higher speed of the object, that cell might become completely fluid. Now note this point. When we are approximating the semi-discrete form, if you remember, we have this I plus 1 minus phi for any variable. That means to solve a particular variable, velocity, temperature, any variable at a particular n plus 1, you need the information at n. Think of this step. If this is the n plus 1 at time level, this cell, you need to solve for this cell, phi n plus 1, and for that you need phi n. However, in the nth time step, the same cell was inside the solid. I will again repeat. A cell at n plus 1th time step can be a fluid cell, but it is quite possible that the same cell at nth time step was inside the solid. Now you have to use the condition at the nth time step. It is not proper that you use the same values from the previous time. It is not. No, actually it is not known what is the solution of the point at the nth time step. If the point is inside the solid, technically the point should have the velocity of the solid. However, if that solid was outside the solid, then that point has a different velocity. I again repeat this one. If this point at the n plus 1 time step has come out of the solid, then it should have a physical fluid velocity in order to predict a velocity. However, since that same point was inside the solid, there is no physical velocity that can be assigned to this. This is one difficulty. This is only one way of doing that. There are possibilities where at nth time step one point was outside the solid. At the n plus 1th time step it goes inside the solid. So that means this creates what is known as velocity and pressure discontinuity. Velocity, pressure discontinuity. Because velocities and pressure cannot be fully prescribed or solved at all points in time. So they are bound to have certain discontinuity in velocity and pressure. These two not only problems in convergence of the solution, but also creates a problem known as spurious process. Known as spurious process. What is that? In sample calculus method, if you solve and if you calculate the forces that is acting on an object, typically drag and release force, if you plot them, it will turn out as this in time. CD of C. It is periodic. We call spurious process. The intensity of such oscillations, these are unphysical oscillations, and it is believed that they mainly occur because of that velocity pressure. Because at some point of time, some of the computing cells which is inside the solid may come out of the solid, and some point which were fluid cells now go inside the solid. So this velocity pressure discontinuity create what is known as spurious force suspension. What is the problem of it? It is not that it looks visually it looks unacceptable. It is not. It has a far-reaching consequence. In vortex-induced vibration, what is vortex-induced vibration? Vortex-induced vibration is an object flow. When flow occurs to an object, the object experiences certain forces. That force is responsible to move the object. That is known as vortex-induced vibration. The vortex is making the object to move. So the fluid, because of its existence, creates the fluid mechanics, and the fluid mechanics on the feedback process, it actually moves the object. So if the forces are supposed to move the object, and CL are nothing but a non-dimensional form of force coefficient, then these are the variations which will make the object move in an unphysical way. Because if you zoom in, it looks like this. So basically, in layman language, if this is the variation of force, however, in a small time, the object is confused whether to go this way or this way, because every next time step is asking me to go to the other way. The object moves to this, again it experiences another negative force, again it experiences a positive force. This creates an instability in the solution also. So these are highly undesired. But it is typical of sharp interface mass computer. Mainly because of the problem that I mentioned. Then there are secondary issues. Maybe I may say secondary issues, but many believe that's not a secondary issue. That mass leakage is possible. That if you are having an object like this, linearly approximated, you have a mesh over it, you have approximately enforce the boundary condition over it. If you take a mass balance, if you take mass flux, you have this cross section, if you take a mass flux, and this cross section, they are not supposed to match. Because of the approximation that is further into your solution with the treatment of the reconstruction method. So this is called mass leakage. If the mass flux in the continuous domain does not match with the region where the object is present, definitely there is a mass leakage. So that is another cause of worry for sharp interface method also. So basically there are mass leakage, velocity pressure discontinuity leading to spurious force oscillation, and implementation issues. Implementation issues are generally not discussed because it is considered to be a problem for those who are actually developing. Because when you are discussing it, it is not a problem. When you are going to write the code and implement it, you will find the pinch of it. Because without addressing it, it's very difficult to parallelize a inverse bounding code without having a proper planning of how you are going to tackle the reconstruction paradigm. Then this is one of the inverse bounding method. There are others also. Direct forcing. I will discuss another method, which I will not say that is a complete geometry, but actually that's a reasonable compromise of this method, which is very simple. This is called diffuse interpolation. This is called diffuse interpolation. It is extremely simple, technically erroneous. What is that? If this is the object, this is the mesh. Yes.
As there is some discontinuity in things that we go for inner sound, so our normal discretization will not work, like high end.
No, of course it will work. As I told you, all discretization method, all usual conventional solution technique works on the fluid points only. Because the fluid cells are those which are actually nothing but non-uniform particulate. As far as
at a certain time, like it is in solid state, but at the next time
we are solving the Navier-Stokes equation only on the solid state. Yes, and for the interfacial cells, we are using them only to reconstruct a local matrix so that we can improve the boundary condition of the solid surface. That's it. On the many actually solve the Navier-Stokes equation on the interfacial cells also, but they implement the boundary condition using ghost cells. Those are which are solid cells not closest to the surface. As I told you, there are different types of implementation, but the basic principle is same. You solve the Navier-Stokes equation from the fluid cell, either on the interfacial cells or solid cells, you impose the boundary condition by reconstructing a local neighborhood of the linear edge. That is Sharp interface method in a nutshell. Okay. Now diffuse interface method. So Sharp interface method has the problem of reconstruction comes because we deliberately identify the sharp interface between solid and fluid. Diffuse interface method does not do it. What does it do? It defines a volume fraction. Why? It defines a volume fraction. Volume fraction is defined by how much of the portion of the solid is actually embedded inside the cell. If you zoom in, this is a computing cell. Suppose the object linear segment pass like this. We have to calculate the fraction of the solid which is inside a cell and fluid. So this is the volume fraction. D of solid is fine. Now, based on this volume fraction, we define a universal equation. Universal equation truly means a single equation which is applied to every point in the cell. How? One minus 5 times Navier-Stokes equation plus 5 times d minus d. Sorry, I am not writing the great details, but if you write the equation in this way, for every point, we have calculated the volume fraction. Volume fraction again is the fraction of solid that is lying inside a computing cell. That is the volume fraction. And we using that volume fraction, we write such a universal equation. Universal equation in the sense, this is the equation which we will solve everywhere. Fluid point, solid point, interfacial point, everywhere you will solve the same equation. Now look at this equation. Phi can be 1 where? Where is phi 1? Solid cell. Solid cell. Phi is D fluid by D solid. Total. Solid by D total fraction. Okay. So where is phi is when phi is 0? Fluid cell. If phi is 0, this equation gives you Navier-Stokes equation. Right? If phi is 1, there is a solid cell, that gives you V equals ds, velocity of the solid. And if it is between 0 and 1, it gives you a blend of both the velocities. Some part of Navier-Stokes equation, some part of the solid velocity. That means some fraction. Suppose a solid cell has 50% solid, 50% fluid, a cell. So this equation will give you 50% of the Navier-Stokes equation, 50% of the body object. So if a cell has nearly 90% mass into the object, that means it will have 99% of the solid velocity, object velocity, and 1% of the Navier-Stokes. This is the way we actually restrict the effect of the interface in a single cell. Why we call diffuse interface? If the solid object moves past this, unknowingly we are limiting the effect of the solid to diffuse inside the cell. And by doing so, we are not recognizing the actual existence of that interface. Because we are not using it. There is no use of the interface explicitly. That interface is only used to calculate the volume fraction. And through that volume fraction, we mix both the Navier-Stokes equation and the solid velocity. By doing so, of course, this method is supposed to work well when the mesh size is very fine. Because if the mesh size is very fine, we can actually eliminate all the difficulties or all the uncertainties of whether the equation should be Navier-Stokes or the equation should be only the velocity of the object. If the cells are very defined, then it actually leads to the sharp interface. So the only restriction or limitation it should carry is it should technically it should use a very defined mesh, number one. Number two, still no matter what results you get, one fact remains that you are not enforcing boundary. There is nowhere we are enforcing boundary condition. Ideally speaking, at this location we should use D equals D on the solid surface. That is no field condition. But we are not doing it unlike sharp interface method. In sharp interface method, we actually implement this, we enforce this in interface with beyond this. We rather try to achieve this in a different way. This is a compromise. Advantage is all you have to calculate is volume fraction. There is no reconstruction, and since there is no reconstruction, there is no difficulty in parallelization. Since you are using the same equation everywhere, there is no problem with the velocity equation discontinuity, which leads to Fourier process. And generally, I can give you an example how it is shown that this is the sharp interface method. Then diffuse interface method can be as this. It is not that it does not have oscillation, but it reduces significantly. It is a way better output than the sharp interface method. It is becoming popular, but it is not as popular as sharp interface method. But I personally use diffuse interface method. It is yet to be I should not call it an established method, but there are techniques which I would prefer to call ad hoc. Sharp interface method also comes with some certain ad hoc techniques which claims to remove this previous course of oscillations, but such techniques also come with certain price tag. The methods are first of all not robust, it is not universally accepted, and for that also it is not so straightforward. It may not work for very complicated. So diffuse interface method addresses most of the issues which sharp interface method suffers. As I said, that it is a self-sufficient method, it does not reconstruct velocity. So as if you are solving in a non-uniform Cartesian mesh, in parallel there is no problem. All you have to do is you have to accurately calculate the volume fraction. Geometrically. Once you have calculated the volume fraction, then it gives you a smooth result as far as both coefficients are concerned. And it works extremely well, mostly for moving on. Because for stationary object problems, still sharp interface method can be made to work. But for moving object problems, notorious problems, sharp interface method exhibits huge amount of numerical oscillations, which diffuse interface method actually work. So from that angle it is superior method, but it is not yet established. Going to the only one biggest criticism that it does not satisfy the mostly boundary condition exactly on the surface. It only does it indirectly.
But
Yes.
as far as I understand, this method, diffuse method, seems to be more scientific or more logical, because I know my volume of my object. So by doing this volume fraction, I am conserving my volume in all my computations.
It's okay that one way of argument is supposed to know one of your friend comes up with a solution, simulation, where he has not implemented the mostly boundary condition. What do you say? Is it a wrong or correct solution? Wrong. Is it not? Technically it is wrong because you are not enforcing the mostly boundary condition. Yes. But that is not a principally difficult issue. It is not that calculating the volume is the most difficult part. Diffuse interface method suffers from that point. It does not satisfy because physically the biggest criticism is you are not imposing the boundary conditions. Say for instance, problems which requires extremely refined mesh near the object. Say for instance, complete flow simulation. Complete flow simulation without achieving a direct numerical simulation, without enforcing mostly boundary conditions is considered to be crime. At least it used to be considered as a crime 10 years ago. But nowadays, since sharp interface method has failed, or people have shown the difficulties with sharp interface method in complex geometric problems, then but it has been observed, it has been shown that with certain changes in mesh, sharp interface and diffuse interface method is identically similar. You cannot guess the in numerical system there is no 0 or 1. It is either 10 raised minus 8 or it is 0.9 up to 14 decimal. So it's up to you what is acceptable to you. There are many who will not accept this method, although you have shown that the sharp interface and diffuse interface results are different to 10 raised minus 6. But here it is not acceptable because there are many who project that this might fail because you are not enforcing the mostly condition. And as he mentioned, calculating the volume fraction accurately for a complex object is not so easy. It is not very difficult.
Also, yes.
It is not a straightforward model for sure, but it is not very difficult. Anyone else? But it works like a charm. That I can tell. Sharp interface also works like a charm, but not on the moving object.
So what if there are two different fluids of two different densities?
Yes. Yes. Diffuse interface method has already been applied on multi-case change flows also. There are papers also where people have tried multi-case method using diffuse interface method. But that's slightly advanced one because there you need to discuss about the combined density.
So we can assume thickness of the diffuse interface to be some maximum, and then we can linearize the properties, like fluid property, dynamic viscosity or density. So the sharp interface won't give you that chance to do the linearization of the properties. So there will be a jump condition between.
The sharp interface is different compared to the previous previous. This is different because what was saying is interface type.
Yeah.
The sharp interface method does not track interface. It is the interface between solid and fluid. Since diffuse interface works with two different medium, since you are solving the equation inside the solid, you can consider that as if you are solving a different medium, different phase inside the solid. Thus, diffuse interface method is very close to directly applied to multi-phase method. In sharp interface method, inside the object, there is no solution technique at all. You forget about what is happening inside the solid. But in case of diffuse interface method, you are solving the equation inside the solid also. Thus, since you are solving the equation both in the solid and fluid, it is perhaps more available, more closer to applying to the multi-phase method, where these two only work. Currently, what is an object to you now will become a different phase. So, diffuse interface can be directly applied to multi-phase method. It has been done also.
Yeah, last question. This method has been applied to fractal objects also.
You give an example fractal objects.
Fractal objects like our snowflakes, those who are aerosols which are falling on in the air atmosphere.
Aerosols I have not seen. Thin plates I have seen. Complicated surface textures I have seen. But aerosols I have not seen.
It means fractal objects are very irregular objects.
Yes, irregular objects can be handled in interface method. But see, the problem is if you define, if you say that thin plate, how thin? Suppose the plate length is L, how thin? How thin? How thin even a sharp interface method can handle? Can you go L by 10? Can you go L by 100? Can any method handle L by 100? It's impossible. Because think of it, what is the mesh distribution here? If it is L by 100, so it is a subjective question that it's a thin, that how thin? You have to make a certain compromise.
Okay, so then it can handle boundary layers also very nicely.
Yes, boundary layer, there is no need for any inverse boundary because boundary layer is a body conform of solution. You have a flat plate, there is an inlet, similar. That's it.
So how can we tackle a problem? Let's say there is water And on water,
There is a
water.
uh,
On the top of water, like on the free surface of water, there is let's say 1 mm of poly thickness. So I'm not using any AMR techniques. Adaptation
is there, are you using multi-phase methods?
like multi-phase or interface.
Multi-phase method, as I told you, diffuse interface can be directly applied to multi-phase method.
Again, there is a problem with the mesh refracting, right? The cost will be too high.
This department is a different technique. You are, first of all, you have a liquid air interface that you have to track. That's a different topic as compared to immerse bounding. Immerse bounding method means handling a rigid object, rigid or rigid flexible objects. So, rigid or flexible objects, not interfaces. It is a different matter that going to the original diffuse interface method can be made to work multi-phase probe with little amount of work. That's a different thing. But it did not, immerse bounding method did not come to handle multi-phase things. That's a different, completely different area. It was introduced to efficiently handle complex objects. Then moving complex objects. Yes,
So suppose there is a deformable object.
it's loud.
So suppose there is a deformable object. The object is not rigid. So for that, how this governing equation will change?
Deformable, I
Means
never
the
worked-
solid is deformable, elastic
Yes,
kind.
yes. So on, try to understand one thing. Deformable object means you have to write the dynamical equations which governs the deformation of the object. Is it not? What deforms the object? Fluid forces along with the object's own stiffness. Right? So diffuse interface has nothing to do with the deformation of the object. Deformation equation will change the shape of the object. Think of it, and there is an object which is rigid. It does not change its shape with time. And another simulation where the object keeps on changing its shape from time to time. So there is no difference in these two situations as far as diffuse interface looks at it. It is not the diffuse interface which decides what is the shape of the object. A flexible object is, it changes its shape owing to the forces acting on it and its own stiffness. But deformable objects are difficult to handle from diffuse interface method because diffuse interface does not demarcate between solid and fluid interface. It only recognizes a cell inside which the effect of the object is diffused. So thinking and flexible object is difficult in terms of from diffuse interface perspective. Sharp interface sees it much easier. Deformable objects simulations are mostly done with sharp interface. Yes.
So is there any way to couple diffuse interface and sharp interface method? Like first we use diffuse interface to identify the boundaries and then use sharp interface and then apply boundary conditions.
You again repeat?
So is there like
No,
first,
way you said.
so first we use diffuse interface method to identify the two different boundaries and then we apply the sharp interface method and apply the boundary conditions for that particular case.
Diffuse interface method is not, it does not demarcate solid and fluid cell. That's a different thing. That is common to sharp and diffuse interface method. Diffuse interface methods bypasses the local reconstruction, as I mentioned before. This is a solid element. Here you have to enforce totally boundary conditions. Going to that, these are the three cells through which you have to enforce the boundary. That is sharp interface method. In diffuse interface method, it does not do so. It only calculates how much, what is the fraction of solid inside this cell and applies that fraction of body velocity 1 minus that fraction of velocity. It can be plain, but for different purpose. Say for instance, you can solve using diffuse interface method, but you can calculate the force coefficient using sharp interface. That is possible. That will help you in defining the deformable object. It is not being done so far. Anyone? Yes.
Instead of solid, if we use other fluids having high density.
Yes. Of course. Because as I told you, this is an object. Flow is occurring over here. Now consider this is an object with different density. That's the only difference. Because as I told you, aegis interface method also solves that the solid. Now instead of solid, now we have a fluid with different density. It can easily implemented here. But in the interface, you have to use a modified density. There are precautions. Anyone?
Thank you for the day. Now we will go to the tea break. So 15 minutes after 15 minutes we will meet here for the next presentation. Practical class it will be held in this department, second computer lab, so M3P and M39. After this class, so that will be approximately 45 minutes time. Yeah. So after this session, so we will go to this second course, room number M3P, M39.
So that's upstairs, right?
Yeah.
So you will be there or?
ऐसे 2 मिनट फोन करते हैं 2 मिनट फोन करते हैं
Okay, so now since morning has been going on a lot of things, right? So the key things to refresh, you are doing some sort of CFD for HPC application, obviously related to some sort of fundamentals. And if I connect from last couple of sessions, the final volume, that shows this is what I am going to continue now in the incompressible part, but just bringing in a slightly different figure of unstructured. But rather than going into more into the details of the equations, the derivations like what Professor Arnav did, probably I'll try to show you how open form this has been done, so that when you go to the lab session followed by this theory, so that you will have a little bit of better idea how you can do that. So when he was talking about I think just the previous session he started off showing an example of airfoil where the body fitted mesh, and then if you try to do, then there is a coordinate transformation like that. So let me start saying that if you have a complex geometry which is with more like an curvature, things like that, which is literally complicated, obviously your regular body fitted grid is going to be a challenge. I am not committing it cannot be done, it's a seriously a challenge. So how you can do that? Obviously you can, let's talk about that finite volume. One is that typical Cartesian approach. I can still use that. Then how I use that typical Cartesian one? Sorry. With the help of immerse boundary. Sorry. Okay. So one of the way to tackle those complex problems is that I can still be in the Cartesian framework where my baseline fluid mesh remain Cartesian. Then whatever the complex geometry I have, I can represent that using a immerse boundary approach. Then second way I can still do body fitted conformal mapping situation. In immerse boundary, you sort of think about that your baseline things are purely Cartesian, then you have object which you are imposing on that. So I can still do body fitted, but then I have to do transformation. So once you do transformation, the transformation goes into your equation system, so which makes things complicated. And obviously, once you do that, you bring in more and more interpolation, things like that. So, and since these are all numerical methods, more and more interpolation you bring in, there would be error which would be associated. Or thirdly, what I can do, I can solve that complex problem in an unstructured way. So this is what I am going to touch upon. So idea here is that you want to tackle a complex problem. What are the possible approaches that you can have? Obviously, these are not, I am going to, just to refresh your memory since morning. Again, you are into the 3 stages of situation, pre-processing, post-processing. But what interestingly I wanted to showcase that, so is structured grid, then these are important because what kind of geometry you are dealing with, then based on that, how you are going to handle that. So one is you can have, I mean, even the simple geometry, you can have regular structured grid, so that you can have, so these are the different grid structure, or I can have a unstructured grid like that. The aerofoil above which I can generate, and the elements could be different elements, hexahedral, tetrahedral, pyramid, prism, so depends on 2-dimensional problem or 3-dimensional problem, you could have multiple. So these are very, very important, I would say the underlying thing, that because the grid how you generate, for example, I have, let's say right now instead of going into the immerse boundary, that option you for the time being just leave it little aside. If I have a structured system where body conformal means I can solve, and I generate a grid like that, can I, my structured solver, handle it? Answer is no. How you generating grid, that also has to have a what kind of CFD solver you have. If it is a structured bed solver, this cannot handle this. But if I have an unstructured solver and I generate grid like that, definitely it can handle this. Answer is always yes. But the reverse, if I have a grid like this, can my unstructured solver handle it? What do you think? Yes, no? Yes. Because this is a some sort of a special subset of unstructured. Because I can still have a regular grid, it's how I treat it. So important thing is that how your solver has been developed, that kind of at the beginning restrict you what kind of grid you can generate. You cannot generate arbitrary grid which your solver is not capable of handling. If your solver is capable of handling any sort of grid, this is where you have an unstructured solver has the huge advantage. Obviously, there is no free meal in the market. When it can handle, that means it's more complex in terms of mathematics rigor, in terms of handling the each of these terms. So now obviously the grid terminology way, so these are one way finite volume works, staggered. Staggered means nothing and other is collocated. Collocated in a sense, each of these variables that you are solving, they are all defined in the cell center. That's collocated. So whether you talk about the momentum component, you talk about the pressure, they are all this. Staggered is you solve the scalar quantities inside the cell, and velocity component you staggered on the faces. That's called staggered. Still they are structured. There is no unstructured here. Okay? But the same thing can be extended to the unstructured situation. So now when you talk about these solvers, there are things which I think, again morning Arnab was talking, you have to identify because you have different terms. So what kind of problem you are solving, steady, unsteady, compressible, incompressible, laminar, turbulent, this will dictate what kind of mathematical equations that you are going to solve. Modeling, obviously the number of equations will go up, then the solution of the equations, especially I think he was emphasizing end of the day the mathematical problem becomes a linear system. So what kind of linear system? So there are sophisticated, okay, iterative ones, Then the direct methods, there are, this list is not, I would say, complete. There are other methods which are there. So solution of the linear system may actually play a key role in the safety. How efficient your linear solver. Also, I think he mentioned one more word which is very, very important, is the robustness. I mean, that is also. Now then once you do that, then obviously you have to post processing. So post processing can be done in multiple ways. So it's a simple data, you can use probably the simple Excel. You use different kind of post processing software. Again, these are not all. One may use, I think, one is missing is visit. I think there are other which you can use. So that means I can generate my grid. Now just quickly taking over from the same situation, this is your complete equation system. So you have the unsteady term, you have the convection term. So I am again similar way writing that it's written in a any generic variable in terms of phi. This is diffusion source term. So term 1 you can expand like that. So this is the beauty of the finite volume. So it's a conserved system. So essentially you can write the whole system in that fashion. Okay. And then general conservation equation, let's say you have a kind of a this kind of a element or cell where you have these all faces. So across the faces. So typically this term how you write, I will again come back to that little. So I have the unsteady term. This is where your open form becomes little handy. It's a syntax that uses the first term, it actually tells you how you write the unsteady term. Then the second term is your convection term. This term is your diffusion term and last term is the source term. So that's the syntax. Obviously these are some of the operator or type of data, but this is just how it writes, but essentially you are solving that whole system of equation. Obviously when you have the equation, end of the day you are getting this, which you are by this time familiar. The typical system, you have to apply boundary condition, Dirichlet boundary condition, Neumann boundary conditions and mixed boundary condition. So whichever phase you apply, so that phase, I mean it's shown in a 2D section. So that phase you take it out from that equation and apply that boundary condition. So this applies your all the boundary condition, but we try to write the whole system in terms of this same syntax, so that when you kind of convert that thing to a program, you have the similar situation. So obviously these are your equations which are I mean typical momentum and this, and where you get that pressure Poisson equation, he has shown that. So essentially a particular cell where you actually write down the mass conservation equation, from the mass conservation equation actually you get the pressure Poisson equation which you need to solve. So that becomes your continuous equations. So point here is that up to this it's fine. So I have a governing equation, then I try to do the conservation principle and then finally get that mathematical form of the discretization. How do I solve it? So obviously you have to have a solver. Now you can use different solvers, but here I am taking you little detour in direction of the open form so that your lab session would be done in open form. Obviously we can't do with commercial packages unless we have so many licensed things like that. So now what is open form, or if you are curious about open form, just to give you a little idea, I am not going into the whole bunch of details of the open form. Now open form got two different versions. So you be careful which version you take. So one version come from .com, one version come from .org. I think they were together is a similar version till 2016. Since then they got departed, and now one set of development goes in this direction, another is this. This sequence name is as the 6, 7, 8, 9, 10 like that. This goes by the year 2020, 21, 22, 2012 like that. Now immediately it may come to your mind, are they same? If you think about OpenFOAM, they are same. But if you think about the development part, they are now quite a bit of different in the way. It's all object oriented programming, but the way the whole system has been developed, the class structure, private class, public class and all these things, so they are quite different. So if you think that, okay, I have something developed in this version, can I put it here? Answer is yes, but there are a lot of challenge associated with that. It may not be that directly transferable. Similarly, the vice versa. You can do that, but definitely that requires a lot of. Now, so it uses all sort of Linux users. So if you think that, okay, I mean using Windows and all this, these days I think there is an executable which comes, but it's not recommended. So this is where you can get, I mean it's an OpenFOAM 9, but you can search in internet and go there and get it. So these are the typical directory structures. So if you once you have the OpenFOAM which is installed, you can get to see this kind of different directory structure. There are applications, bin, jock, etc, platforms, src. So these are main your solver libraries. Applications are main executables. I mean some of, also the part of them are bin and platform. Tutorials are there, a lot of tutorials. So this is how it looks like. Even once you download it looks like that, but once you compile and all these things, they will look like that. So these are the two different things, and there are a lot of some other tutorials which you can go through. I mean, yes, from I mean different YouTube videos, things like that, you can definitely learn. Other tutorials and things like that. Plenty of material is out there. So definitely in your spare time you can do that, but obviously it's very easy to get frustrated because it's not your typical way of doing commercial packages which is give you nice graphical user interface where you have everything available in drop down menu. So you have to really spend your time to get used to with that. Okay, but thing is that it's absolutely doable. Okay. Now, some of the general description, it's a freely available things. As I said, it's a object oriented programming based technique. So essentially, under the GNU public license, so you can always download. And but yes, you can use the some installed Ubuntu version is also there, you can do that. So a lot of options are there which you can compute, like I mean basic heat transfer, fluid mechanics, particle physics, molecular dynamics, then you have also rotating frame of reference. So, but yes, everything, there are some out of the box solvers or applications are there, but yes, blindly you can use pick and use. Obviously, you have to interpret your data. Then coming back to your turbulence libraries, they are there. Some rheological models are there, thermophysical models, different kind of source term modeling. But these are some of the things are there, but it's not guaranteed that this everything has been tested. Since it is built upon a public user license, so whoever build something, he can actually pose it to the repository, which is may not be tested, properly validated. So whenever you use some out of the box library, it is at your own risk and cost. Okay. So then what you can find, you find basically different, again those simple kind of or pimple kind of based solver, they are parallel. So you don't have to bother about that. So without sort of going into the details, you can do that. I mean, quote unquote, you can do all these things. So ready to use executable. Okay. and obviously there are some differences which are there with the commercial softwares. Here you essentially need to go down to the level where you need to do programming, and but the advantage here also you have is that you can develop your own module and use it. So I mean, one can look at it how you want to use this particular thing. One is that I have something readily available and I want to use it, or I use that framework which gives me a parallel platform and things like that and the data structure. Now I want to use it and develop more further sophisticated module. So it's an approach that you adopt, but if you want to take the second route, then you have to definitely get into the understanding of the basics of the whole thing. So without understanding, you can, otherwise you can use as a black box. Obviously this, I mean, you have a simple scalar transport equation. You see this unsteady term, convection term and the diffusion term. This is the syntax how you can, it is written. So now similar way I have to add a, like a, let's say, dispersion equation, which is a kind of varying between 0 and 1. I can add like that. But obviously the boundary conditions and all these things I have to implement as I want. So the implementation part or the development part makes little easier for you. So if you look, as I showed you earlier, that if you look at the different directory structure, so once you go there, you see these directories which I already shown you, applications bin, but whatever, I mean, important thing is that once you do that, so under the application or utilities, you get to see the different application solver. So we start from basic incompressible solver to compressible, some solid mechanics, all sort of different solver you have under that utilities. So also some different tutorial problems are there. Like for example, incompressible, you have that .ecoform.c, which I am going to show you in a while, and then you can set up in a. So essentially there are different solvers which gives you incompressible solver, transient solver, compressible solver, reacting solver, multiphase solver. Obviously every solver is slightly different in the context of their implementation and things like that. So you have to explore, always like that. So if you try to use OpenFOAM as also black box, then I will go back to my morning last slide. It will become colorful fluid dynamics. It will never become computational fluid dynamics. Okay. So coming back to the equation. So now you see what you got in your final equation. So this is a momentum equation in terms of any scalar variable phi that you have. So you have got all three terms, so 4 terms, unsteady term, diffusion term, convection term and the source term. So this is how, I mean, in some way you discretize the unsteady term. This is the discretization of the convection and the, so these are exactly the final equation system that you have got in the, so you try to rearrange them. So there is nothing like that. So when you solve these things, and this typically shows your .c file, so you solve the whole, I mean, you got those, I mean, 2-dimensional system which was developed like KW, 3W, AP, AS, PS, AN, PN. So you goes in a loop. So the loop starts, then you try to, since you are solving unsteady fashion, so you have to control the Courant number. So that you can control even through the user input, but how to control and all this, obviously you need to understand what are the controlling parameters of the Courant number. So without knowing you cannot control, but, and then the main equation is solved in a, that is your U equation, and then you send that whole thing to the pressure Poisson equation where you solve the pressure correction equation. And this is the rest of the loop of that algorithm. Obviously, let's focus on this side. So each of this line here where you first compute, then update, then each of these coefficients of those derived equation of that final discretized form, that you try to kind of calculate, and then finally you send the whole business to this pressure Poisson equation where you solve this pressure Poisson equation del dot, you can see that. So this is what was derived using your continuity. Right. So whatever has been derived already, so it just solved in that fashion. So it goes in a loop. So once you solve, you check your mass balance. Once that is not satisfied, you go back. So it's a iterative process. Okay, and anyway, this just to give you a quick idea where this is in the case setup that you will get to see the finite volume schemes and all these things. So these are your time discretizations where you have different variation of the time discretization scheme. What you want to use, you have to give as an input here. These are user control. Then you have this grad scheme, which is going to take care of this term. You have the divergence schemes, which is going to take care of this term. So again, these are some of them, but you have plenty of that. Then you have the Laplacian term, which takes care of your diffusion term. So the input you can control what kind of discretization that you want. Okay, and you can control that input from that. So it's written in such a fashion that once you change that, you can. Now, when you go to general case structure, so in the case name, you have one 0 folder, which will contains your essentially the boundary condition. So no problem can be solved without having a proper boundary condition. So the boundary condition you have to provide based on your. Then obviously this polymesh it contains your information about the geometry. So pieces, elements, and things like that. Okay. Then this system directory is going to control your all the numerical schemes, numerical parameters, your solution, other control parameter like start time, end time, and things like that. Okay. So now before you go, so these are your critical directory structure that you must have these directories when you try to run a problem. So like your icoform, I have already shown these are. Now when you come to the FB solution, there are the P for solution, that means your Poisson equations. So here this is your system of linear solver, this is your PCG is a conjugate gradient based solver, precondition conjugate gradient. Then for you use different solver, and then you can have other parameters which will control your algorithm of the piezo. And these are the control disk file, start time, write time, and all those factors that you kind of define. Okay. So this case setup you are going to actually, these are two problems they are going to go through in the demo. One is that this backward facing step, another one would be this oscillating cylinder, that means the moving mesh problem. So then we'll come to the other problem which would be done in the, so anyway these equations are done. So far we are talking about the single phase system. So when you go to the two phase system, so that means the multi-phase problem. Let's say you have fluid and solid, or two different fluids like that. For example, water in a air, or air bubble inside the water, like that. So obviously your basic conservation equations are going to be there, but top of that you need to kind of make that demarcation between those two fluids. So you solve another equation which is called the typically known as volume of fluid, which is where you solve that alpha equation. So alpha actually demarcates the phases. Either it phases in one fluid, so here, and the other one goes to the second phase of the fluid, and in between the interface. Obviously now sometimes volume of fluid can be coupled with the level set or things like that, so that you capture this interface. Typically volume of fluid has that kind of a issues where the interface you may not be able to capture at a very sharp way. So you essentially get a diffused kind of an interface capturing. So that's an issue that always you have associated with volume of fluid, but people sometimes couple that with the level set to kind of eliminate that problem, or one can use some different kind of algorithm to, that's you can skip. So again, these are the same thing that taking the equations in the volume of fluid, where you take the different terms and then you take it. But what here we are going to probably show you in the demo, and the issue is that you use the fundamentals of the volume of fluid, but slightly different way. You try to handle in a isoadvector approach. So what isoadvector does is that you capture that or track that surface. So that's sort of an, I mean, simple way to look at it, that it uses the both the capability of the view method and the level set kind of method. So uses some sort of an blending approach which captures that surface very precisely. So here also again those, I mean, the alpha equations you discretize, so discretization pattern is same. So and then once you get this discretized pattern, so you get this coefficient. But obviously because of your two fluid system, the mathematics become little bit involved, but eventually you get those terms, AP, AC and all those terms, and then finally you use them in the. So how this typical that isoadvector based solver works? So you go to the, here is the pseudo algorithm so that you can understand how it goes. So essentially you initialize your variable and then try to go around that and solve the, this is the outer loop here. So you solve, if your mesh is changing, then you try to take care of that. If not changing, it's fine. Then you correct the alpha, okay, and then you solve all your U equation, and then from there you get to solve the pressure Poisson equation. So all I have is that the similar way, my continuity equation, momentum equation, obviously pressure Poisson to correct the P, but then for the capturing of these two different phases, I solve another equation extra, which is the alpha equation. So here still I am not talking about the energy equations, all this. So more and more governing equation you bring in, so those equations you need to solve that. So this block structure is, I mean, you talk about the flow variable, then essentially once you solve the momentum, you try to construct the surface and then you solve the pressure loop and then go out. These are so small actually. So these are some of the glimpses of those equations, which you can see that alpha equations where this advector, which is when you do this operator, it's essentially taking care of that convection part, and then you use that alpha to calculate your mixture density and all these things. And this is where the isoadvector equations, which looks like that. So this is how you solve that equation. Again, I mean, this right now I'm not getting into the detail of these. These are all coming the way typically you get again that AP is, I mean AP, PP and that equation. So if you do that mathematics, you end of the day get those things only. So only that is the final discretized fashion that you get and you solve that. It's the only syntax how you program that, that's how it differs. And obviously the momentum equations, where if you have the moving frame of reference, that can be taken care of, and this is where your pressure velocity coupling is done. Okay. So all the different parameters of those equations that you solve, and then you bring them in finally. So once you finish that pressure correction, you look back the mesh conservation, go back to the continuity loop. Okay, these are again same way your case directory should have those things like discretization parameter, solution parameters and input parameters. And you are going to solve this two-phase system where it's essentially one is the air, other case is the liquid, and how you track the surface. So that's going to be again put it in the demo. So yeah, I will kind of stop here if you have any specific questions, so that these things again you can see in the lab session. Then right now I can answer, then in the lab session you would see how you can actually solve those equations. Any questions or anything? So this data is visualized in time.
It will be taught that here.
Yes, they will try to show you how you download the data and load it in Paramount, right? Yeah, Paramount will also know. So if you have a laptop, that will be easier so that you can. So that's the idea. That's what I wanted to keep it short so that you go, because it's not only how you learn. So essentially, you have to also visualize. See, I mean, all this process would take time. It starts from a completely when you connect to the main server, how you run the job. Basically set up the job. That's another stage. Run the job. Once you run the job, how you get back the data to your local terminal, then the post processing. Because your HPC system won't allow you to do that post processing. So all this would take some time. And obviously, you will have some advantage if you know basic Linux. Obviously, these TAs are going to help you, but let's see. Any other question? This one I shall. So it's a volume of fluid coupled with your capture of the surface tracking. So it's not pure volume of fluid. It's a flavor, blending flavor of volume of fluid with level set kind of thing. So here geometrically we reconstruct and parallel you solve the alpha equation to make sure that the surface is sharply tracked. Typical volume of fluid, always surface would be diffused. It's not a. Okay, so then if you don't have further questions, so basically you can take the staircase and go upstairs their computer lab. So you may take your laptop and things like that from here. So we'll finish there and then move to the dinner to the same place where we had lunch.
I'll show you the way that that is.
I'm not a trained computer scientist, so I will only explain the stuff which is required in CFT the way I have learned it. So it's all, one makes all self-learned. You are not a trained person from computer science department. Parallelization is mainly parallelization is our kind of application, CFT application. The main objective is to speed up the calculation. All by now you all are very much aware. In our kind of application, it runs for days, months, and years also. If it runs on serial, that means if only a single processor takes the load of all calculation, then it runs into, maybe it can run into years also if the computation size is very large. The only purpose over here is to speed up the calculation. Basically, parallelization works with two different modes. One is called, you should know these two. One is called shared memory. And another is distributed memory. These two basic understanding you should have. Every processor, physical chip has an accessible memory. It is called contiguous memory. Contiguous memory means when you are allocating memory location, it comes sequentially from a memory and the chip has access to this memory. Nowadays, most of the chips are multi-core. There is a difference between multi-core and many-core. Multi-core is the, usually we have a single chip which contains 8 cores. A physical chip has 8 cores. Also there are threads, I will discuss threads also later.
Excuse me sir, it is not visible.
Is it because of the light or it is? Black marker. Can you change it? I plan to start there, but one of you, one of your friends said partly that board is not visible. That's why I secretly here. Should I go there? And you can see this side.
How many of you are favoring this board?
Okay, overwhelmingly
That will be better.
he started from
I think that is better.
Serial memory and distributed. Simply speaking, the chip that we have, chip is the processor. Typical processor may have multiple core or many core. The desktops, laptops, regular used computing devices generally have one chip, which we generally have 4, 6, 8, at most 8 cores. These are called multi-core environment. These cores are designed for multitasking, different tasks at the same time. While if you put them together, suppose if you put 10 such processors, now it becomes 80 cores. So 80 core environment we call it as many core environment. Multi-core versus many core. Multi-core is the usual multitasking environment. Many core is for number crunching. For huge number crunching is many core. Now every chip has access to a continuous memory. Simply RAM. You can access to this. Let me suppose a shared memory. Suppose if you have 10 cores, all the 10 cores have an access to a continuous memory. So whatever data you have stored over here, all the cores can access this. And drawing this as cores. But basically, these cores are embossed into a single chip. So all the cores have access to this chip. That means if you have a data over here in the memory and if it is changed, then all the cores have the knowledge of that changed new data. That is shared memory architecture. OpenMP works on this. Naturally, since it is working with only a few, because since it works with a couple of chips, then in a die, generally OpenMP environments are limited to cores. Bigger blade die servers may have up to 128, but 128 cores OpenMP or shared memory is the, if not the highest, but nearly the highest level of OpenMP execution. That means a single machine has 128 cores, and all the 128 cores have access to the same memory. So whatever your data is, that is accessible to all the cores. In contrast to this, what is distributed memory? Now if you have, consider this one as a single computer, single machine. Now if you join such machines together, say hundreds of such machines, each of them has say 4 or 8 cores, each of them has something. This one has access to this. This one has access to this. These have access to this. So there are many such computers, put them together. That is what is cluster is. All processors put together, but they are standalone unless we join them together by network. That is called network switch. This is called network switch. What is the purpose of the network switch? Yes.
White chalk, can you please read the
White chalk. Distributed. We have, these are the chips, suppose 8 core chips. Each of them has a name. And so on. All the cores have access to this name. So is this. they will act as a standalone machine unless you join them together through a network. This is the network switch. All of them are joined together by this switch. So these cores through the memory can talk with each other only through this communication. Naturally, better the switch or better the communication network is, better will be the crosstalk. Yesterday, during one of the lectures, also already mentioned that one of the bottleneck is networking. In parallel computations or parallelization, there are only two things which is actually primary. One is grammar branching, that is calculations, floating point operation, blocks that we call. Floating point operation, another is communication. Suppose you are doing certain calculations, some certain scientific calculations, it will have some part of number crunching, and that number crunching, whatever the result is, partly that should be made accessible to other cores. There comes the communication. I will explain why that communication is required in distributed. That communication is not required in case of OpenMP. Why? Because shared memory. Because all cores, all participating computing units, each core is a participating computing core. Each core has access to a memory. So naturally there is no need for communication. All the cores, participating cores has access to the same memory. So whatever is being changed, all the cores can know it immediately. But in case of distributed, unless if something changes in this memory, unless you made it accessible to this memory, this cores will not come to you. That is what is distributed memory is. In shared memory, it is only about number crunching, but there are difficulties in shared memory also. But in distributed memory, communication is a factor which may slow down your calculation. Sometimes, so during the talk also this word was used, concurrency. Concurrency is a simple word if you understand it. Concurrency is in parallelization, most of the parallel algorithm, it is our objective that all the participating cores should remain busy nearly in the same. Say for instance, generally in the clusters or many core environment we use homogeneous cores, SMP, simultaneous multi-processor environment where all the processors are nearly same capability. If generally we do not use it like this. Suppose we have a machine whose clock speed is x, another one is suppose x by 2. It can be 0.98x. Still it is not favored, but generally we tend to use all the cores of same capability. Otherwise, they should have same ability. Because we are assigning calculations to them, one should not do it faster than the other. If one processor does a job faster than the other processor, then what this faster processor will do when the other processor has not finished its job. So the concurrency is very important that all the processors should be given the task. The load should be as equal as possible. Although in many situations it is not possible. I will give you a couple of examples. It is not possible, but that is one of the aim of parallel algorithm. So it is clear to you what is shared memory and distributed memory. In one of the methods that I am aware of in distributed is what domain decomposition. Suppose if you have these domains, computational domain, one of the best way is partitioning. In a partition. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 divisions. Each of these divisions are actually assigned to a particular one processor at a time. So that means it is a 16 core calculation. All the processors will simultaneously calculate one of these domains. And a single processor does not care about all the other processors are doing in other calculations. Its only job is to calculate the domain is given to it. Popularly this is known as domain decomposition. While obviously, if this domain is a rectangular one, it is much easier to partition it and much easier to allocate to a processor. Suppose this one is a domain, naturally this domain cannot be filled with rectangles. This domain has to be filled with triangles only. On the other hand, suppose if you have a domain like this, which can be filled with constant x and constant y lines, that is Cartesian or cylindrical mesh. Naturally, there is no reward guessing. Here, the partitioning is much easier because you can count the cells in x and y direction. Suppose there are 10,000 cells, 100 in x, 100 in y, that gives you 10,000 cells. You have 10 processors in your hand, 10,000 by 100, job done. So that means you know that how many computing cells should be assigned to each processor. That is called partitioning. That is also called load balancing. Load balancing is the load, calculation load prescribed to each processor should be as equal as possible. That is what we do the balancing. But in complex situation, many a times it is not possible to assign the same number of computing cells to each processor. Then we try to do a trade-off so that the balancing between different processors become as reasonable as possible. That is called load balancing. But by now it's clear to you that such a geometry, constant x and constant y and Cartesian geometries are far more easier to handle as far as partitioning is concerned. You do not need a sophisticated, specialized, specially able software. I know one that is called aegis. Aegis, you provide mesh to a metis and you prescribe the number of partitions you need, and metis is a software which actually creates a partition of that. It may create a partition like this. This is one partition, this is another partition, this is one partition. It may create 4 partitions if you are asking for. Based on the load balance. You start, it's a very big process. You start with a partition, you calculate the load, the addition in load in different partitions, and you try to balance as much as possible. But that is not required in case it is a Cartesian mesh. Because in Cartesian mesh we know how many are in x, how many are in y, and r theta also. Then partition is extremely simple. Suppose in order to keep the number of computational cells same in each processor, if you have to use 100 grid points, 100 cells in x direction instead of 105, there is no problem doing that. Basically, the number of cells has to be an integer multiple of the number of processors. So this is partitioning. Once the partitioning is done, then calculation proceeds. Now I will explain to you where the communication is coming and how we are. Consider a typical computing cell. Suppose this is a interprocessor boundary, a partition. This is a partition. One side processor 1, another side processor 2. Yesterday, by now you know, in local type of calculations, we know the neighboring information. To compute over here, this is not a physical boundary. This is a virtual interprocessor boundary. Processor P1 will compute until this point, and processor P2 will start calculation from here. Processor P1 does not care about this, processor P2 does not care about this. Its only job is to calculate up to this, P2's job is starting from here. Now to calculate at P1, its east neighbor is in P2. And to compute over here in P2, its west neighbor is in P1. Naturally, to compute in this cell, you need processor P1 needs the information from P2. And to compute at this cell, processor P2 requires the information from P1. This creates the communication box. You need to communicate the data. Wherever there is an interprocessor boundary, one layer of cell, layer in the sense in 2 dimension is only a vertical line of cells. You can imagine. In 3 dimension it is a plane. Interprocessor boundary is going to be a plane. In 3D it is a plane. So one side of the plane, one layer, one plane of that layer is one plane. So we have to transfer it to its right boundary processor. And on the right, one layer of cells has to be communicated to the left boundary. This will continue in all directions. This is happening in X direction. This should also happen in Y direction. Suppose this is the interposer boundary between P1 and P3. Now to compute over here, in P3, each cell will require the information from its south neighbor. And to compute over here, function P1 will require the information from its north neighbor. So naturally, in each direction, one layer of cells has to be communicated to its immediate left or right neighbor. It does not end here. Now, another communication call is required, which is not like this, left or right neighbor. Think of it. When in a calculation, in a geometric operation situation, when this communication call is required, all processor has to do it. Every processor has to send one layer to its right and one layer to its left. Naturally, every processor should accept the data from its right and accept the data from its left. So that means every processor is sending one layer in the left and right to its right and left neighbors and accepting the same data from the right and left. Similarly, in Y direction, top and bottom. So in each direction, two layers are communicated to the neighbor and two layers are accepted from the neighbors. Send, receive. This is how API works. In 3 dimensions, both in X, Y and Z direction. But you can see there is a organization. Every processor simultaneously is sending its data to its right neighbor. Every processor is receiving data from its right neighbor. Every processor is at the same time sending the data to its left neighbor, accepting the data from the left neighbor. Similarly in Y direction also. Now think, if suppose one processor has 10,000 cells, another processor has say 500 cells. That means that processor is sending 1,000 communication calls, but is receiving only 5. So there is a mismatch. Expectedly there is a mismatch in communication. All the communication loads in all the processors are not same. Naturally the time required will not also be same. So we will call this one loosely as asynchronous call. It's not synchronized, because if all the processors have same ability, thousands calls for each processor should take same amount of time theoretically. If the number of cells, number of communication calls are different, time will be different, we call it asynchronous, because one processor will finish its job and it has to sit idle before the another processor finishes its job. So those are the things we try to avoid as much as possible. That situation was pretty simple, or rather straightforward, that if all processors are actually communicating the same way, left and right, top, bottom and the Z direction. But there are situations, there are exceptions which is not happening. Say for instance, this is a physical boundary. This is a physical boundary. Some processor has started calculation from here. If this is the physical boundary, this processor does not send anything to its left neighbor, because its left stands the physical boundary. There is no need to transfer this data to any processor. That means the processor which stands near adjacent to a physical boundary, in one side it does not need to communicate anything. So this is one processor and this is another P2. So there is a difference. In P2 it sends left and right, but P1 does not send anything to the left. So there is a asynchronous communications or asynchronous calculations anyway present in the power system. So there are no systematic or thumb rule to address that. Definitely we do not want that processor P1 should sit idle before P2 finishes its job. But that's bound to happen. There are no remedy for it, there are no thumb rule for it, different rules, different people actually adopt different things. One of the ways which is definitely not a thumb rule but can be done is like, let's P1 send the same data, this data to any other processor, to the processor which is not accepting anything from its right. This is another situation where this processor is not accepting anything from its right. So that means if one of the communication is void, that means this processor can send the data to its left, is not required. Let this processor send the data to this processor, and this processor receives the data. In that way, all the communications are absolutely synchronous. But now it's up to you whether that data should be used or not. It is saved and received, but you do not access, do not use it. In that way, all the calls or the communication is synchronous. Distributed calculation is, as I mentioned to you, domain decomposition is basically first. MPI is, full form of MPI is message passing interface. Message passing interface is basically collection of directories. It gives you ample library functions. These are for all library functions. There are plenty of library functions. Using them, you can create a parallel environment. What is a parallel environment? Parallel environment is a group of processors where each group will have an identifier. That very environment will also have a name. In a particular computation, because of certain applications or utilities or certain needs, we make a different computing environment. Suppose we have created this. Here there are 4. 1, 2, 3, 4 processors. That's it. MPI environment. You can create another environment. It's a different name. The identifier can also be different. MPI calculation always starts with few protocols. You can look at the actual syntax, but it always starts with MPI INI. It is slightly different from Python and C. I will not go into the detailed arguments. There will be arguments. So MPI INI. Most of the situations, the arguments I will explain. This argument may contain an integer which will return you whether the process is successful or not. If it is 1 successful, it is 0, it is not successful. MPI INIT starts the calculation, and before that you have to input MPI.h that contains all the description of MPI directory. MPI INIT starts initializes all the MPI directories. Then we have MPI COM1. We must, I don't exactly remember, something like this. MPI COM1 means you have to define the communication. So communicating processors, their names can be anything. Alpha, beta, gamma. The usual practice is to give them the rank as rank 0, rank 1, rank 2, and so on. Here we describe what are the numbers, what are the names of processors, and what is the name of the communicating. It's a, as I told you, MPI communication word is a collection of processors. It can have different names. If you are creating different communication words, they can have different names. But each entity of them can have rank 0, rank 1. It can have alpha 0, alpha 1, alpha 2 also. Because later on, you have to call them by their name. Once that is done, then you are good to start. In MPI, in our kind of application, there are only, I would say, 5 to 6 directives that is good enough to execute most of the applications. As already I have given you one example, MPI send and receive. These are called one-to-one communication. One processor is another one processor. This is called one-to-one communication. One processor is sending, another processor is receiving. The syntax goes like MPI send. Then there are arguments. What are those arguments? Naturally, what is the entity that you are sending? It can be an integer, it can be a real float, scalar. It can be an array, 1D array. In most of the books, you will find, majority of the books, if not a advanced model, most of the books will find examples of only 1D array. But 2D and 3D array, these are the advanced applications. So you have to find out papers, applications, monograph of the advanced open source and so on. The arguments are basically what is the entity that you are sending, what is its size, what is its data type. Because that is something that has to be mentioned, that I am sending an integer, its size is this, and its data type is an integer. Its it's a one-dimensional array, or two-dimensional array, or three-dimensional array. It is sent to which processor that I have to mention, under which communication block. This much information is required, otherwise it will become ambiguous. What I am sending, what it is data type, what it is site, whom I am sending, that belongs to which communication block. And a flag, whether that send is successful or not, because you need to know if that is unsuccessful, you should have a flag coming out of it. So these are the flow of arguments we find inside the packet. Every MPI sent in one-to-one communication, if you can send something, but that task is not complete until it is received by its destination. You have given where the data is sent, that processor should receive it. Then only this MPI communication is complete. Received, received. Quite obviously, the argument over here is what is coming, what it is data type, what it is size, where it is coming from, in which communication mode, and whether the receive is successful or failed. So these are the flow of, this is called one-to-one. Source input. Whatever data you want to transfer, send and receive. MPI codes are generally written a same code, single instruction, multiple objects. Single instruction, multiple objects. I am writing a single instruction, but all processors can follow. It is not that MPI codes are written for different processors differently. It is not. A single instruction is written. Suppose I know that, as I have mentioned in MPI calculation, in send receive, every processor should send its one layer to its right boundary, one to its left boundary. Already we have agreed. And also the same processor should receive from its left and right neighbor and y and z. That means if I give a MPI send and receive, right processor, all the processors are simultaneously executing this. So processor 1 is sending to 2, 3 is sending to 4, but don't go by these numbers. These numbers you do not have to control. What do I mean? Suppose in a geometry composition, you have only created 4 domains. That does not mean this one is 1, this one is 2, this one is 3, this one is 4. They can have any number. They can have any number depending on how the API communication model has created. You only know, you can know what if the, you only know rank 0, rank 1, rank 2, rank 3. It is not necessary that this is rank 0 and this is rank 3. It is not. This can also be rank 0. There is no thumb rule for creating which one. Anyone can be rank 0. But you should have a control over who is the left and who is the right. That can be, that you have to create beforehand. These are the required data that you have to know beforehand, before the communication. Yes.
Sir, how will you know that this is the rank 0? Because you write 1 there. If that is rank 3, how will you know that that is the rank?
There is no need to know which one is rank 0. That is the beauty of it. Anything can be rank 0. You are not interested about which one is rank 0. You are only interested about what the rank 0 is supposed to do. You will instruct rank 0 to do some work. You are not interested which one is rank 0. That depends upon many complex situations. Scheduler also. What are the other jobs are present? Which node is how much loaded? That depends upon many other factors. You should know what rank 0 is supposed to do. Rank 0 is expecting task from you. It's not expecting that you will decide that this is the rank 0. Now, these are what, this is an example of single instruction multiple. Here you are giving a single instruction, all the processor can follow it. Every processor knows that I have to send this data to my right neighbor. Every processor knows that I have to send this layer to my left neighbor. And he also knows that I have to receive one layer of data from my left neighbor and from my right neighbor. So you see, these are all single instruction, multiple SIMD. With single instruction, you are making all the processor work together. But there are multiple instructions, multiple data also. Say for instance, as I told you, the left boundary, here there is nothing to send beyond it. You are, for the sake of keeping the synchronicity, you are sending the data. Because all processors are sending, let this processor also send, so that the communication calls in all the processors remain identically same. So this processor can send to anybody. which is not overloaded, and while doing it, do not overload any processor. To send this data to a processor which is not receiving. So receive it, do not use it. So in that case, this processor is not systematically sending the data to anyone. So this is a multiple instruction. You have to specifically instruct this processor for this task. Similarly, on the right boundary, you have to instruct this processor specifically to send this data to another processor. These are multiple instructions, multiple data. And because of your need, you are giving multiple instructions, separate instructions to separate processors. Although we generally avoid it, but sometimes it is required. API send receive. These are one-to-one communication. It is possible to have one-to-all communication. That's called broadcast. A particular processor, generally it is in API terminology, is called processes. One process can broadcast one data. Suppose, example, say if you have calculated a maximum in an array, that maximum is single value, all the processors should know it, but it is lying on a particular process. So that process should broadcast that minimum or maximum value to all the processors. You cannot use a one-to-one communication. If you use one-to-one communication, it will only send to a single processor, but it should broadcast to all the processors. It is called API recast, broadcast. Broadcast is properties. Again, the arguments are what is the data type, what is its size, and which processor you are sending, which communication part. Because you are sending all the processors in a particular communication. Of course, a flag which will give you whether it is successful or not. This is one-to-all broadcast. They are all-to-all communications also, but they are seldom used. Those are directives which are seldom used. This is good enough for communications. Then there are the next item can be one of the most important is reduce type of operation. Reduce in the sense, suppose you are calculating RMS. RMS means you have a single value or average. You suppose it is 5 minus 5 square among all the cells in the room. That is what you require. So all 5s are not in the same processor, but 5 first you have to calculate 5 That 5 has to be communicated to all the processors. That means it equals broadcast, or you can compute that 5 in all the processors simultaneously. 5 is known. Now every processor will calculate its partial sum. This processor will calculate 5 minus 5 is square. So this processor will have its partial sum. You can sum them up in a particular. All the processors are simultaneously calculating this. That you can call them as partial sum. This one will have a partial sum. This one will have a partial sum, and so on. So all the processors have some partial sums. Now we have to add them up. This is called reduction procedure. All the processors can go into a reduction job. Reduction job can be multiplication. It can be addition also. Here we need an addition. So individually each processor has already calculated its part. 5 minus 5 square. Now these are called, these we can call partial sum. Now these partial sums can be put together as API reduce. API reduce is again a reduction procedure in a single processor. It can be also all reduce. All reduce in the sense the reduction procedure will be executed in all the processors. That means the final RMS value or these calculations will be known to all the processors. But if you use only reduce, it is only in a particular processor. Naturally, when you are using reduce, you have to mention on which processor. But when you are using all reduce, the communication word is sufficient because you are asking API communication word that in all the processors under such and such communication word should carry out this reduction procedure. I would say these are the directives that is good enough for nearly 70% of CPL. API send, receive, broadcast, reduce or reduce. Gather altogether is also required at some special situation. These are good enough. Another point I should mention, API barrier. Although it's a is available, but that directive generally many times we avoid. What is MPI barrier? MPI barrier is, suppose in your parallel algorithm, no matter how you try, you cannot bring in synchronicity. That means different processors have different loads. Certain part of the calculation, you cannot make it homogeneous. All the processors are doing the same calculation. Suppose that is not possible. That is quite possible in different type of statistics or different calculations. Say for instance, if you have a domain like this, computational domain, but you want to calculate some statistics only in a region, specified region. That means in this region, whatever the processors are, they are only taking part in the calculation. They are not supposed to take part in the calculation. Technically, as I have already said, that you should make concurrency. That means these processors, suppose there are two processors, only this is the processor. So these processors are not taking part in the calculation. Only these parts are taking part. So one of the easier ways is calculating all the processors, but don't make use of it. Calculate it, jump. Basically you are calculating something which is not required, but you don't do it. A time will come when this person is actually working, this person is not doing anything sitting idle. That we should avoid. That can create unnecessary difficulty in parallel. So we can anyway we calculate it, but we don't use it, because during that time when this person is carrying out its own part, what this person is doing is of none of what, because it has nothing to do. This is the where the parallel algorithm brings in efficiency. But that's what I am saying, that there are situations you cannot get. There are set of processors which will only be active, rest are actually is not doing much. Yes.
Let's say they are calculating junk, and what if they communicate to each other and contaminate?
Don't communicate it. Communicate it, but don't use it. Your solution variable is file. A processor which is not required to communicate, let it communicate. It communicates as X, but X never becomes 5. Problem solved. Don't use it. These are done. These are not complex, as I told you. You can devise your own ways, but these are done in order to keep the calculation and communication as homogeneous as possible. That something is our mind that we will make all the processors do the same thing. Whether that is required or not, that's different. But we will make them work same and communicate same, so that the synchronicity is always maintained. This, in order to avoid this, there are situations where you cannot help. There are processors which are easier than the other. Here we use MPI barrier. MPI barrier is something which enforces synchronicity. Whatever is done until this point, all will be synchronized unless when you hit these directives, the control of the program does not go beyond this line until all the processors are ready for further calculation. This is what is known as MPI barrier. It will block all the calculations till all the processors come to a stage where they can start doing this calculation. This is MPI barrier. This is required to synchronize different calculations. It is advisable to use this one also, because suppose it is not necessary that, suppose you are running a job, a calculation on suppose 20 cores. Those 20 cores come from suppose 3 different nodes, and on those 3 nodes some other jobs are also running, each have a different memory requirement, different computation level. So naturally those cores are not equally loaded. Naturally it's possible that in your application your memory requirement is much lesser than the other one. So in order to avoid any difficulties at certain points, we generally use MPI barrier at some critical location, so that the calculation always remains synchronous. So as I said, point to point communication, you start with MPI init, then define MPI communication point, you are good to start. Then whenever required, we use MPI send receive, one-to-one, one-to-all as broadcast, gather, all gather, that is also communication call, and reduction process. These are good enough to start with any MPI calculation. As I said, these programs of script codes are written as single instruction, can be SIMD, it can be MIMD also. Single instruction multiple data, it can be multiple instruction multiple data. We write only one code, but it's all logic. The entire control is on hand. Now I am moving to open shared memory. Now think of it. In the distributed memory, we started that there are different memory sets for different cores, and we are connecting them through switches. We are part of independent switch, that is the base possible switch these days, very high speed switch. If the switch is not in miniband, if the bandwidth of communication is much lower, then you will not feel much, only the calculation time will overall CPU time will increase, because your number crunching time will become smaller than the communication. Anyway, so now I'll move to the OpenMP. As I said, in the distributed memory, it has separated memories stitched together by a high-speed network, and the computing elements, each core are actually communicating with each other the equal amount of data. One may think that can create a bottleneck. Before going to the OpenMP, there are two parameters. Practically, there are two parameters which actually measures our performance. One is called speed up, another is efficiency. Speed up is naturally the time required in the serial computation divided by time required in the parallel computation. Ideally, it should be the number of processes. Suppose your calculation, you have calculated in serial mode, you have calculated in 8 processors in one. Naturally, what do you expect? It should be 8 times speed up, because if you have spent 1 hour in the 8 processor mode, you should get 60 by 8, 1/8 of an hour. But actually, that does not happen. That is speed up. Speed up is generally not equal to the number of processes. And efficiency is speed up divided by the efficiency. So if your speed up is n, which is equal to the processor, your efficiency is 100%. Generally, we do not achieve because of several other factors. Some of them I already have mentioned. Because communication will drop down your, bring down your efficiency, speed up both. Quite obviously, lesser your communication calls are, more will be your speed up and efficiency, because the calculations, the processors are only made busy in number crunching, not communication. So speed up and efficiency different. It is a established practice whenever we install a new cluster, new computing servers in parallel environment. We benchmark it using different applications that is accessible to us by what is the peak efficiency that it can gain among different processes. That is also called scaling. Suppose if you use some application at 4 cores, your cluster is at 1000, your cluster has 1000 cores. You have run a job at 4 cores, you got a speed up of say 2.4, 60% efficiency. You cannot, without any further test, you cannot say that, so I do not need to test if I use 1000 processors. Naturally 1000 into 60 into, so that much 60% efficiency are getting 1000 processors. You cannot assume that. We have to show that the scale up remains nearly uniform. Scale up means I can get a scaling of 2.6 in the 4 processor situation. I am getting nearly same scaling for the 1000 processor situation. Because both these two situations are different. Because since a single calculation is distributed among 4 and 1000, naturally the number crunching, floating point operations and communication calls are entirely different. A 1 core mesh divided into 4 processors is, each processor is handling 25 lakhs, 2.5 million. But when it is split into 100 processors, each processor handles much more lesser floating point operation. Now its communication increases. Suppose if you have 4 processors, so how many communications in each direction? 2. 1, 2. This side to this side, this side to this side. 2 layers. But if the number of processors are 4, the number of communications calls are 4. That means the number of increasing number of processors, in one hand, the number of cells handled by each processor is reducing. That means floating point operation is going down, communication call is increasing. Number of communications are is not the same at two different parallel environment you compute. It's not same. That's why we go for testing and benchmarking of certain clusters. Now I move to the OpenMP part. OpenMP part is shared memory. Shared memory means there are no different memories for each computing units, and there is no you do not need any communications. OpenMP can be executed in a single desktop. And one of the interesting or the important feature of OpenMP is to know what is known as optional comparison. Optional comparison always starts with this. Optional comparison means you write OMP. OMP means shared memory architecture, and the directives, unlike in MPI where we write MPI same MPI underscore DC, in OpenMP type of script we start with OMP. What is the syntax is like this. It makes sense. When you have written a serial code, normal code that you are writing, there you add this. What does it mean? Whatever is inside this loop will be only executed if you ask the compiler to do so. That is optional. That is called optional compilation. You may not compile it. When will you compile? When you want to use OpenMP. When you don't want to compile, when you don't want to use OpenMP. You do not write separate codes for serial and OpenMP. You do not write it. You do not write separate codes for MPI, OpenMP, and so on. We write the same code, and we keep options inside the script so that some part of the code will be compiled depending upon what is the option we are giving in the compiler. This practice is different in Python and different in C, but the principle is same. In the comparison, you have to prescribe which of the parts has to be open. You can enable the OpenMP's parts in the comparison, you can disable. That means if you disable it, the things which is written inside it will never be compiled at all. It is skipped. It will be taken as comment. The compiler will only read it as comments because you do not need OpenMP. That is how OpenMP works, and it is popularly known as fork join. What is fork join? You have heard of that what is very popular, hyper-threading. Hyper-threading is basically each core, these are physical cores. Your machine has 8 cores. That those 8 computing cores are embossed in a single chip. You see only one processor, but it has 8 computing cores. But threads are logical cores. Each core, hyper-threading means each core can subdivide into 2 threads. Threads are logical computing devices, and these logical computing units, they are fundamentally created to enable you multitasking. Suppose you are doing 10 different things: transferring job, copying a large size file, executing a code, editing some material, you are downloading something from the internet. These are all different type of tasks. Each of them has different characteristics. Each of them have different CPU requirement, memory requirement. So these two handle or address this multitasking, threads are introduced. Threads are logical computing unit which starts logically from a core. If we enable multi-threading or hyper-threading, each core will divide into threads, as many threads as you want. But in hyper-threading, what happens? The hyper-threading generally each core are divided into 2 threads. That means if your machine is 8 core, you can create 16 threads if the hyper-threading is enabled. If hyper-threading is not enabled, 8 core only will produce 8 threads. It cannot subdivide into different threads. Now in OpenMP, the control is only serial. The control is serial. Everything is done by single thread core. Remember this. But we do not call it core in OpenMP, we call it thread because it is the thread which creates it. Like OpenMPI at the beginning we start with certain directives, we start the OpenMP and we declare the number of things. Very well. Now what is pop join? Certain part of the domain, certain part of the code, you want to do it serially. There is no need for OpenMP. So that is called join. Say for read, you are writing a code where there is a read part. There is no need for separate threads to read the same data. Why? It is not required. Why? Because all the threads in OpenMP has access to the same memory. Why you should read from separate threads? Because threads already has a access to the same memory. So you can read it serially. So you read it. That is serial. Now you start a loop or do or whatever loop. Suppose you are running a loop of 1000. Naturally, you would like to split it into several parts so that calculation speeds up. Suppose you want to in multiple threads you want to split it. That is called for. Now you give such a directive. If you give such a directive, immediately it will form into as many threads as you want. So now you do the calculation. Now calculation is expectedly faster. In a serial mode, a loop has 100 counts. Now if you use 8 threads, one of the beauty of OpenMP is, beauty or rather say easier part is 1000 divided by 8 need not be an integer. It is up to in many of the situations in OpenMP, actually the compiler actually takes care of it. 1000 by 8, if it is not an integer, it will automatically settle down the division among different threads. So if you, all you have to do is you have to ask, in case of MPI, the full control is in your hand. How many cores, how many partitions you are going to use, each partition, how many computing cells are going to be present, everything is in your hand. Who sends what data to what receiver, whether that data is received or not, whether that data is further used or not, that everything is in your hand. All control is in your hand. But OpenMP, you have to ask it just parallel the loop. Inside it, you write something like OMP loop or for. That means you are asking the multiple threads to carry out their own. So that means 1000 counters will be calculated by 8 different threads divided among each other. That is for. So we have divided all the tasks into different threads. This is join. That means all the threads are joined together and doing a task. Now when it is required, you have made them work as single threads. You have for. This is called for process. For. Now the calculation is done. You have a single value. Suppose you are calculating RMS. So the RMS is a single value. Once all the threads are calculated single value, then join all of them. Again next task. Suppose the next certain series of tasks can be joined in a serial environment. Again it's a join. Again when you need to for the calculation, again for. So OpenMP is generally, philosophically it is known as for jointer type of algorithm. Exactly works as MPI as far as directives are concerned, but MPI directives are not optional comparison. Here it is an optional comparison. During your comparison, you can enable the OpenMP part, you can disable the OpenMP. If you disable it, these parts will not be there. There are other critical features of OpenMP also. I will just mention one factor. Yes, popularly that is known as racing criteria. Racing criteria is one thing which makes OpenMP or OpenMP algorithm competitive. What is racing criteria? As I told you, all the threads have shared to a single contiguous memory. Now suppose you do not have control which threads are handling which computing cells. Now suppose one particular thread is handling that this data is changing, and that might be required by another thread. Now the problem is racing. Think of these two threads. this thread is changing one data and this thread is accessing their data. Now there is a racing problem. Racing between these two threads. This thread, should it access that data before it changes it or after it changes? So that creates a racing between it. If this thread access this data before the change, your purpose is not served. That means you are working with the data which is calculated before the accuracy. On the other hand, if you are able to use that data through this thread after the iteration, that is what you want, but you cannot make sure of it because you have no control over this thread will read this data before this one calculates, that you do not have control over. That's called racing criteria. In certain situations like this, you have to use certain directives which again makes it synchronous. OMP critical. It is called OMP critical. There are other ones. OMP critical in the sense all threads are sequential. One thread completes its job, next thread starts its job, and so on. These are called OMP critical. There are other OpenMP directives also which work with the same principle. But you should know the main difficulties that arise in OpenMP script is you should figure out which are the situations when there is a racing condition which can start. For instance, you are using possible iteration. Possible iteration is very prone to racing condition because at every iteration you are updating all the values. Since you do not know which cells are actually handled by which thread, it is possible that one thread is accessing one data which is being not updated yet. That's why in parallel algorithm, parallel environment, both OpenMP and MPI, multi-core environment or multi-thread environment, we generally resort to what is known as checkerboard type of relaxation method. Relaxation method where we use red and black. One cell is red, other is black. Or multi-colors are also possible. And separate colors cells are handled separate. They are not mixed with each other so that the data dependency and the racing conditions are actually addressed properly. So I have given you a flavor of the shared and distributed memory. In both the situations, you write a sequence code. In MPI, either it can be SIMD or MIMD. All the processor will follow instruction. You can make any processor follow any particular instruction. Others can skip that one. In a way, MPI codes, MPI programs are actually, you have nearly 100% control over them. What you want to do, that the processor is waiting for your instruction. But in case of shared memory OpenMP, there are things which is not in your hand. I have given you a couple of examples. You can only ask an OpenMP compiler to make a for or do loop parallelize. You do not have any control. You may have a control, but that's complicated. That's generally not done. That will actually take away the advantages of OpenMP. You just ask OMP do or OMP for. It will automatically distribute among the threads. The balancing will not be there if the number of cells is such. But that is the easier way of OpenMP. You do not need to do much as it is required for MPI. In OpenMP, you just add few directives which is supposed to speed up the calculation by fork and join. That's not it.
Yeah, we'll
yes,
sir. There is lack of communication between the codes. If you look maybe in the results simulation.
Lack of communication.
Lack of
What do you mean by lack of communication?
Suppose one code is transferring to the other code and it is not transferring in that frequent manner as this particular second code is transferring to the fourth code. So does this cause any difference in the outcome of the result?
My experience says it will create a very easy thing which you are very popular, very familiar with. Segmentation fault. It will create segmentation fault at the very easy. You don't need to worry.
Is not complete before this.
Yes. That we should avoid it. We should at any cost we should avoid it. And this is very natural in API environment. Many times data is sent because try to imagine there are millions of times in one cause it may go wrong, and it goes wrong. Not all the time it goes wrong. There is nothing wrong with your program, but it may go wrong for several other reasons. Broken pipe, segmentation faults, wrong data, NAN also. These are all possible. Yes, as I given you that every MPI directives are coupled with a flag. That flag is used to know whether that process is successful or failure. Anyone here? But my suggestion is to learn this you write books. Yes. Books. See, I use Fortran regularly. There is a book on Chapman. It gives you flavor of OpenAPI API both. But instead of
for OpenAPI scientific computing, there is a book by Michael Quinn.
Michael Quinn. Fortran C directives are given.
Both is C. There is one book.
You can read the books.
But Michael Quinn, QUI. You will find the PDF of that.
But internet materials are also available, because as I told you, only you need 8 to 10 directives in API for 80% of your needs. So if you know how to use those directives, then you can start using it. But you can get, as is mentioned in doing so, you can get a lot of given examples. But as I told you before, and remember that in majority of the books you will find the examples at most using 1 DI.
Okay, so we have after 10 minutes break, then we'll come back. Some of you are looking for the DA form. We collect during the lab session. Get this ready. Just please. So we'll continue with this session. So where what we plan to do is that some glimpse of the compressible flow modeling, and then we'll go to the lab for your lab session. Couple of announcements. So one is that regarding your TA bill, that you can during the lab session the TS they would collect it, and also probably they are preparing your certificate. So whatever name you have registered, based on that only they are preparing the certificate. If there is any correction which is needed, then before going to the lab, go to the registration desk and intimate that if there is any correction that is required. Otherwise, by lunch they would get all your certificates ready. So that time if you say that, okay, my name is wrong, spelling mistake is there, then that would be difficult. Is that clear? And TA bill will all collect in during the lab session. Okay, so now when we talk about the compressible, again it goes back to the conservation equation. Now in a finite volume context, so we'll try to now write things little bit more comprehensive fashion. So in a way that you can think about it little bit mathematically involved. So these are exactly what I've been talking about, all your continuity, momentum and everything. So now everything is brought back in one single equation to represent. So if you look at that one single equation, obviously you have the momentum component, energy, density from the continuity. Now one of the biggest difference between your compressible and incompressible is that here density you cannot kind of take it out from your variable. So they would sit together. In an incompressible flow, somehow with some assumption you can take that out, so that makes things easier. Now then these are your all surface integral term of your complete fluxes, which includes two components. One is this convection component. so which includes your the velocity and the pressure, and then there is a V stands for here the viscous component, so that stands for your stress tension and things like that. So, and then finally you come to the source term if you have something. So there is a, I mean, kind of it is more intentionally that we are trying to write that, why I am coming in a few minutes. We try to, in a compressible flow, what you need to do, you need to actually capture the sharp gradients, especially if you have shock and things like that. So how well you can capture that gradient, that is something going to dictate the accuracy of the solution technique that you have adopted. And how you are going to do that, that would depend on how you model this term which are there in this convection component especially and the viscous component. Now if you see that equation, so one term which is there is the unsteady term. So the, if you look at the unsteady term, so I will go little bit term by term capture of the so this unsteady term, then you modify that and then it comes to your complete equation. Then this term you try to evaluate, which will get you some sort of an essentially the rest of the viscous and the convection and the source term, you take it to the other side of the equation. So this is how you are going to solve the on equation. Now there one extra term which would appear is this term. So that essentially one can think about, if it is a three-dimensional element, it corresponds to the cell volume. Okay, and if it is two-dimensional, then it would be the, so that's how you try to estimate that. So let's not go in the deep of all this how you estimate, but essentially if you look at this, this is a two-dimensional cell and this is three-dimensional cell. So essentially that omega term that you estimate to calculate the volume which will go in your this side of the equation. So then rest of the term that you have kind of taken into the one component R, but I will come to that. Now important component, that how are you going to discretize the convective term. So you can adopt different kind of techniques. One simple thing to do is the central differencing to do that, or you can actually do some sort of a splitting because it's a convection term. So why you need to do that splitting, I'll come to that. Or you can have some sort of an TBD based scheme which are variational diminishing scheme. So these are very common in your convection term discretization in the compressible flow. Now this is something slightly different from your incompressible set of equation, where you can actually kind of do things with the pressure velocity coupling, but here since the density is coupled there, so and also you are encountered with the sharp gradient due to shock or things like that, so you have to capture those gradient, which is very unlikely to happen in incompressible situation. So the treatment is slightly different. So here whole set of equations of the parametric space or the variables, they are solved simultaneously. So you don't try to segregate them. Now one important, before we go to the thing, that if you look at this, this is a one-dimensional stencil, so this gives you an idea. These are your cell centers which are demarcated as I plus 1, I minus 1 or things like that. So what you try to capture is that every cell will have a phase. So if it is I, then this you can think about, let's say if I uniformly think about it, then it's at the I plus half, the other one could be I minus half. So every phase I need to calculate, because that's one of the basic criteria for finite volume. When the volume integral, using the divergence theorem, you transform to the surface integral. So once you transform them to a surface integral, you need to calculate the fluxes at the face, interface. That's very, very important. So now how I calculate the fluxes? When you look at the incompressible situation, you still have to calculate the fluxes, but that was much straightforward. You don't have the problem, but here calculating the fluxes, you have to be careful, because I can have a shock there. So to take care of that, you calculate the characteristics on the right moving wave, because in a compressible flow you always have this sound wave which are propagating, so you try to calculate the right moving wave and the left moving wave. So if I consider this particular surface, then you try to estimate the right side characteristics, which is U1, and the left side characteristic. It could be for any variable. Okay, and then, so there is a wave. I mean, let's see, if you look at this particular way of representation, so there are some parameters which are kappa and epsilon. They would actually, generic terms, what they do, they can give you a blend of different kind of schemes or way of getting this splitting also in the right moving and left moving characteristics. So if I change these parameters, the kappa and epsilon, so that depends which one you would like to add up, and then accordingly if you use that, they can give you different type of characteristics. But what you need to get is this left and right side characteristics. So obviously, why, I mean, when you just come back to the stencil again, so this 2D cell, you have all these other indices which would be involved, and when you go to 3-dimensional, these are the indices, they will come into the picture. Now if you go to the splitting operator, this, the convection term if you see. So this is a particularly Van Lee scheme, how they do that. This is an example. As I said, there are other also. So now this convection term, I split it into, so convection term, what it consists of is consists of my U component, momentum component, and the pressure component. So I split in two characteristics. One is the plus of the right moving characteristics, one is the left moving characteristics, because compressible situation locally, so the flows are what kind of, I mean, what is the nature of the flow? It is parabolic, elliptic, or hyperbolic? Anybody? What is the nature of the flow? I mean, it could be wild guess. It's a hyperbolic in nature. So what is the basic characteristics of a hyperbolic system? So the characteristics propagates in the, exactly, so two directions. So that's what we are trying to split that to kind of incorporate the physical nature of the system. So that's what you try to do that. Now these are set of mathematical expression. Let's not get into that. End of the day, what you need to calculate is that left and right moving characteristics, but it also take into account of local Mach number, because now when you go from move from incompressible to compressible flow, effectively your Mach number becomes an important parameter. So it also takes care of the local Mach number issue. So there are, I mean, this is how the Van Leer actually does it. But end of the day, this is my important parameter to calculate both the left and right moving characteristics. So these are nothing but my set of floating point calculations. That's how I look at it. I mean, this expression and why they are taken into account. So you just, now similar way you can do that for advection upstream splitting method, which is called AUSM. Then AUSM has a different variation of the family, AUSM plus, AUSM. I mean, all they do, effectively the convection flux, which is FC, is split into two components, FC plus and FC minus. That's what end of the day I am trying to calculate. How am I going to do that? Either I can use Van Leer, I can use AUSM, I can use Van Alvada, I can use Quickby, I mean, whatever different kind of approach, you have muscle. So here it also incorporates some special treatment for the pressure term also, which was slightly not there in a different way treated in the this thing. So that, I mean, other components are like the Mach number components are treated similarly, but the pressure is also brought in here to calculate that. As I written here, convective, rest of the terms are like Van Lee. So only extra treatment that you do here is the, but end of the day what you get is that this treatment, what you have to do. So just rather than going into the, I mean, that's a kind of a table which will give you, so there are central based schemes which can do different kind of blending. There are first order flux vector splitting or Goodenough based scheme. There are second order TBD kind of scheme. So different kind of things which are there. Now when we move ahead, so what we are going to do, this is again a basically Kant solver that you have in the open form, which is a density based solver, row central form. But again, that's a very, very elementary stage solver. One can definitely use that. You can develop top of that to a different kind of solver. So typically that works for finite volume based staggered collocated system. So other schemes which could be important is that, especially to get the convection term discretization, which are higher order and obviously proven to be more accurate. So you can have piecewise parabolic method kind of scheme, you can have Eno based scheme, you can have Winos based scheme. So these are well documented in literature, but obviously I am not going to talk here. The reason is that they are not even available directly in the open form, but one can definitely bring them in like we do. In the lab we have a Wino kind of things, we use it ourselves. So you can do that. But obviously this requires more involved mathematics and you have to do some kind of a calculation, extra bit of calculation that you have to do to get those things going. Now when I move ahead with the row central, so that essentially uses two different splitting operator. One is the Krugerov-Tadmor kind of base, another is the KNP Krugerov-Noelle-Petrova. So how, again, the equation system that you deal with, so you see the continuity equation, that's what your density appears. You have the momentum equation and then you have the energy equation. Here, mind it, the energy equation is not only the temperature equation. Here energy is total energy. That means I will have the kinetic energy component and the sensible energy component also. Okay. So that's how you can, and then finally you have the equation of state which takes care of that. So now this is typically, if you see a unstructured kind of cell, so you need to calculate all these different components, not only keeping tag of the neighboring cell information, you need to calculate these normals and the surface vector, because these are important to calculate my all fluxes at the interface. When you look at the staggered interface, it's much more ordered and defined, but in an unstructured, these extra normals, and that's what it makes it more complex compared to the structured finite volume. So you need to calculate the distance between these two cell center. So you need to calculate multiple normals. So if they are non-orthogonal, then the correction needs to be incorporated. So it makes it a bit involved. But these are all doable, and say that it's already built, taken care of in the open form. So how do you do that? So the simple algorithm, you start the calculation, you calculate your fluxes, and solve your momentum energy equation. Usually you first solve the momentum equation, then you solve the energy equation. You don't need to, unlike your incompressible cases, you don't need to do any pressure provision because pressure is now solved simultaneously. So it's coupled. Now the system is coupled. So you are not doing segregation. And then finally you update the system. So just quickly, so if you look at this convection term, that's our volume integral, then you bring it down to the surface integral. Whatever, let's say if you have two-dimensional surface, you have 4 surface, go to 3-dimensional, you have 6 surface. If it is an unstructured element, then depending on the element type, you have so many surface, so you get the surface calculation. And then if you use one of these methods, so you calculate, these are again floating point calculation, there is nothing. But what important here to note here is that you are calculating these characteristics in the this plus and minus, which is left and right moving characteristics, so that you get back those information. Similarly, the gradient term, which is again, if you go back, so this is how you represent that. So you have that alpha, so alpha is calculated here. So depending on that what alpha you use, so it can give you the KT based algorithm or it could be KNP based algorithm. Okay. And then coming to the Laplacian term, that again you the volume integral, you bring it down to the surface integral, and then you, if it is a non-orthogonal, then do some corrections, but you can. So this is how the whole algorithm actually works. So you solve for the density, which is a continuity equation, then pass that density to solve the momentum equation, then you solve the energy equation. Obviously you connect everything back to the state equation, and then you can have the viscous term corrected. Now depends on how your time loop is behaving, implicit or explicit, you update the system and go back. Okay. But internally, this is the how you calculate. You calculate each of them in one. Now, how you implement that thing, if you look at the file, so these are some of the variables. So here this pos and neg, what you see, this is again positive is the plus characteristics, neg represents the negative characteristics. So all these are calculated for each of these variables. So it is rho, that means for density also I am doing that rho plus rho minus. Rho u stands for rho multiplied with u, so I am doing rho u plus rho u minus. This is 1 by psi, that is 1 by rho u, so that is also plus minus. That internal energy plus and minus. Similar way rest of the all the variables, and then I calculate the surface field also plus and minus. So all these left and right characteristics I have interpolated. So this is exactly when you go to the lab, if you see the file, you exactly see this. Now some other calculations you do, which is basically which algorithm you are going to use, whether KT or KNP. So that alpha, I showed you the equation, so that alpha calculation is here. Both considering the positive and negative, if you Tadmor. So this Tadmor information, whether I want to use the Tadmor based algorithm or the KNP based algorithm, that could be user defined. So like in your control dict file, if you say that, it would be read, and once it is read, then the flux scheme, when you say that it's Tadmor based or something, it does that calculation, so it overrides that alpha calculation. So accordingly alpha is taken care of. Okay. So that means one single solver can take care of that. Now here is the, in the governing equation, that how you calculate that all this term. This is your total surface flux of the energy. This is surface flux for the u, and this is u rho u. So you can see this calculating all plus and minus. So whatever that equation I have showed you, splitting between using the alpha, that psi plus and psi minus, these are all taken into account. Now that's how the .c file will look like. So here you solve the density equation. Okay, exactly similar syntax. This is your unsteady term, the divergence of the that feed contains rho u. Then you solve the momentum equation, essentially rho u, But here again, as I said, rho is always sitting with the variable, and then the divergence term, and then right hand side you can give the source term. Then you calculate the viscous term, whether laminar or turbulent. Then you solve the energy equation. Then you update everything and goes back. And this is where pressure field using the state equation that P equals to rho RT, you update the pressure field of the system. Okay. So this is how you update things and then go back. You have any questions on this part? So okay, so we are going to solve, depends on the time or something like that. You are going to use this row central probe and the files that you are going to see. But you can see what kind of, when we talk about this capturing. So some quick example I will like, I mean, when you look at this structure, essentially you see the shock structure, all this. So you need lot of accuracy to capture this. Then again, you see this wedge where you have flows which are at the high Mach number, hypersonic region flows. So then you can handle this kind of sharp edges even in the compressible situations where it can be other way, rigid body or moving body situation. So all these encounters a lot of shock and all these things. So you need very, very accurate shock capturing scheme in the compressible flow. Okay, so these are some examples which the problem that probably you are going to do. One is the very simple problem what one compressible flow one can do is the shock tube problem. So one side you have a low pressure, another side is a high pressure. So these are the conditions that you have. So once the diaphragm ruptures, then you have a shock propagation, which one can always validate with the 1D compressible, I mean, analytical expression, which is one can do. I mean, standard book also give you that, you can always verify. So then the second problem that you are going to do is this kind of a forward facing scale. So that's slightly tricky because you have a sharp edge here. So when the shock propagates and the high speed flow, then you see this bow shock which will form, and when the shock takes a turn, you have a expansion corner there. And the third one, again, time permits this kind of a corner which has an angle. So these problems are very canonical in nature. One can always compare with the analytical solution, which are readily available, or one can compute that through the expression, mathematical expression, I mean, compressible flow book by Anderson. Okay. So that's the beauty, and once you develop a solver and try to see the accuracy of the solver, you can always go back to this kind of a fundamental problems where you have the analytical solutions available, or one can compute that the analytical solution so that you can. So these are the problem that is targeted from your lab. So if you have any questions, feel free to ask me, or otherwise we'll move back to the computer lab. Good. So we'll head to the computer lab in the upstairs. Okay. So these are the problems that you are going to see.
I will explain once more how will you load your data into GNU plot. Data underscore 1. Right? This is the command that you are looking for. Then we can you are in that the plot is ready in that module. 4.7. Only for what? Okay, I'm moving further. What the next case?
So everyone here is see this case and just go for the basic origin. If you haven't stay completed,
So basically, there is an obstacle right over here. Beside the domain, there is super solid is occurring from the ground. So this is also an such that the velocity is specified with the Mach number. So the other case is a Mach number of 3, and you have symmetry on the top and bottom, and on the obstacle you have the strip boundary condition. The outlet is inlet outlet which switches to 0 gradient and fixed boundary condition based on the flow diagram. Right. So I don't have this is the present computation results that can be obtained by us if we make the computation correct. So this is the expected. I'll go one step back and I'll try to simulate this form of fixed.
That's what. Just I have to check. Yes, I will check again.
But thing is, you don't need the circuits over here. You can just visualize the domain with the application condition. Right? So if you open it, let's say x direction 0 and y and 0 and z. If you want to give angle of incidence, you can give accordingly. Since this is a compressible case, we need to set the temperature over here as well, instead of just pressure as compared to the pressure pipe. So again, so our boundary condition, initial condition are set. Just need to run the solver row control. We will start executing the calculation.
We had a lot of discussions on parallelization of CFD software solvers. Here I briefly go over something which has already been discussed in the OpenMP. Very briefly I covered that. I will try to go to a new platform which is relatively new in parallelization domain, that is GPU, the graphics cards, to show how we can parallelize things. And after that we have a lab in which there will be one example in what Professor Gray has discussed, nuclear-based parallelization of conduction equation solver, and then there will be a couple of demonstrations on this. So we try to see these two aspects, that what is the difference between GPU versus a CPU. We use a programming API called CUDA. What is that for GPUs? And then how we can use GPU for CUDA matrix operations. Then we will see something similar than CUDA, which in many cases, especially in our group, my students there use OpenSSL that which is more similarity with OpenAPI, and therefore it is easy that you can code your already developed code on GPU using OpenAPI. And then you will find applications some of the performance standards. However, I started with something much simpler. That how does because we probably need to go to some part of the architecture of GPUs. We'll start with CPU architecture. And this is mostly known to us. We are feeling sleepy after lunch. I am feeling sleepy. We are feeling sleepy. So we start with something which is very immediately already known to start. What do we have in a simulation or a simple computer? We have a CPU in which there is an arithmetic logical unit. There are registers and control units which is connected to the RAM memory, and this is connected to the input output controller. This is the basic architectural schematic of the CPU. And when you have an input instruction stream, through that instruction stream, some memory is placed into the CPU, from IO the instruction stream goes to the CPU, and over that, when the instruction goes, CPU fetches some memory from there, and over that memory is loaded to the register, and on that CPU operates over the instructions, register runs the chip, and they are again copied back to the main memory or device dynamically. So if we see what is the performance metrics of a computer, if we try to buy a computer, we see what is the speed of the CPU, how many cycles of electricity passes to the CPU, and based on that electronic gates will operate and it will calculate numbers. That is basically what CPU is doing. Electricity passes to the CPU, some pulses of electricity passes to the CPU, during this pulse some of the AND or NOT gates are operated, and CPU takes some number and then takes the logical does it. So if we see a 1 gigahertz processor, that means one cycle will take 10 to the power minus 9 seconds. If we think that 4 operations, 4 floating point operations, 4 operations with numbers, real numbers can be done in one cycle, therefore CPU is supposed to give 4 gigaflop speed. That means 4 into 10 to the power 9 operations should be done in a second. However, we do not get that speed. In a single CPU, we do not get that speed. Why? I will come into it later. There is something else that is called RAM band. CPU needs to read the data from RAM, that will come to the register, and CPU will work over that. So, and you know that RAMs, everybody know about the RAMs, they are rotating devices. A RAM is identified. If you go to buy a RAM, how many thousand RPMs revolution will be the revolution speed. So when data is being read from the RAM, it depends on the rotational speed of the RAM. And this is much smaller than this gigahertz speed. This is 10,000 RPM, 20,000 RPM, etc. Therefore, in order to operate over one data, CPU needs to read that data from the RAM, load it to the register, and that will be done not based on the CPU speed, but it will be done based on the RAM speed. So this we know as latency, that what is the time taken by the CPU to read data from RAM. So I'll do a simple calculation. Well, you can of course see that we are not getting CPU speed because we are dependent on the RAM speed. So 1 gigahertz processor with 4 operations in a cycle, and the RAM has a latency of 100 nanoseconds. And this, ideally the processor should have 4 gigaflop speed, but if we see that every operation needs to read the data from RAM, so the frequency of each operation goes to 10 megaflops. However, we actually get better speed than 10 megaflops. Why? Because some data is preemptively fetched from the RAM and sits close to the CPU. That part is known as cache. So we use caches which are low bandwidth memory units, and they are placed, they improves the latency, they are placed in between the RAM and CPU. So compiler has its own way of prefetching the data. Compiler doesn't know that whether you will use which data in the next operation. But based on the general use in different applications, compiler designers specify that when you are reading a matrix or when you are reading an array, maybe next 100 elements you can bring into the RAM from that array. If you utilize those data, then you are utilizing from RAM, you are not utilizing from the CPU, not utilizing from the memory, and therefore your performance is improved. And these are different levels of caches here. So in order to obtain an efficient implementation, it is important that you see that how you are using your data structure, whether that is friendly, the way you are calling your data, whether that is friendly to the compiler's vision on how to capture data from, how to take data from main memory or RAM and put it into the cache. So if you use cache data very frequently, then we say that we have a very high cache hit ratio, and that is a good program. The program execution will be good. High cache hit ratio will be better program. So this goes on the basic of architecture of a CPU, and based on that, if you are consciously developing your program, you probably at some point of time keep this thing into your mind that you are having good cache hit ratio and your performance is coming. Now we have discussed about parallel computing. What we discussed earlier is known as a single instruction, single data, single instruction, single data stream architecture. There is one instruction, CPU is taking one data stream from the RAM and processing instruction over that. When you come into parallelization, there can be different aspects like single instruction, multiple data architecture. There is only one instruction and different data elements are being operated. The other one which we do not use much is multiple instruction, single data. There is multiple instruction. For example, when income tax department is processing processing against your PAN, they are taking information from several sources. But sorry, they are taking instruction from they are operating different instruction that what is your against your PAN entire data is available. But they are checking what is your foreign exchange, what is your different tax payment, what is your savings, etc., and coming into the final. So that is on the same instruction, many processors can operate over multiple data, and the other one is where we have entire flexibility. There are different data instructions, different data streams, different instructions, and everything is getting processed together. This is our simply uniprocessor or single processor system. Here we have vector processor or array processors. In general, in vector processor, there is one information, one vector, and the instruction is same that you add to vector. So each processor is taking one element of the vector and adding it with another corresponding element of the vector. And instead of operation being over a scalar, the entire operation is being over a vector. In multiple instruction, multiple data, there can be two different modules which Professor Dey has already discussed. One is shared memory space, another is distributed memory architecture. In shared memory, the entire data may belong to one contiguous memory space and many processors can operate over it, or they may be in different computers but virtually they are mapped to the single data space. These are symmetric multiprocessor, NUM, etc. And distributed memory, different processors have their own memory space. They work independently in each element, there is only local memory. However, as and when required through MPI code, they communicate among themselves. So now we again come to our main concern that we need to solve Navier-Stokes equation. If we look into incompressible Navier-Stokes equation, the issues are the equation is itself nonlinear, so something has to be done to handle nonlinearity. There are issues with pressure coupling, which has already been discussed, and some methods are there. In one case, stream function vorticity, you can eliminate the pressure from the equation. In other cases, simple family or Markov-Ansel algorithm, you have to solve a separate equation, which is a Laplace equation for a Poisson equation for pressure or pressure correction. And if it is unsteady problem, then you have to solve for every time step. That means in every time step, you need to solve that
pressure coupling part. So end of the day, this pressure equation being a second order linear differential equation, or it is a Poisson equation, end of the day you have to solve Poisson equation using some computer method, and that will give you a matrix equation. You have to solve a matrix A x is equal to B. If it is an unsteady problem, then every time iteration you have to solve that matrix A x is equal to B. So matrix solution becomes the most expensive part of an incompressible Navier-Stokes solver. If you may have a very large, and we know that from the accuracy perspective, in order to reduce our discretization and truncation errors, we need to use a large matrix, a large number of grid points. So grid points in today's slightly moderately complex CFD problem goes from 10 to 100 million cells. Therefore, your matrix will have 10 to 100 million rows. Each cell has at least one variable. So you end up in getting a 100 million by 100 million matrix, which you have to solve. If we use Gauss elimination or LU decomposition, there are total n cube operations. So in a 100 million means 10 to the power 8 row matrix problem, the number of operations are 10 to the power 20. Now compared with your typical computer speed, you can say that for one iteration how much computing time it is going to take. Computer speed you can find out from the RAM or cache bandwidth. That drives the speed of the computer. But on top of that, if we use a Gauss elimination type of solver, in each step there is some round of error. As we are having 10 to the power 8 operations, round of error of 10 to the power 8 steps may get piled up. And therefore, you can get a very high round of error. Probably you are solving a non-dimensional problem between 0 to 1 and your round of error is 1000. So the entire solution can get killed. Therefore, we use iterative solvers, and in order to reduce round of error, we use iterative solvers, but that also takes very large number of iterations. So if we think of using an iterative solver is based on matrix vector multiplication. In an n by n system, there are n square operations for one matrix vector multiplication. At least n iterations are required for an n by n system. So in n cube operations will be required. So what are the number of operations are like? And that's why we need to use parallel computing. And there are two different models widely available, utilized for parallel computing. One is a shared memory model, in which you have a main memory and many CPUs are connected to the memory. Each CPU looks into one particular memory location and operates over that. And another is a domain decomposition method, where you divide the domain into multiple subdomains, give each domain to each of the processor. It works on that, and as and when required to ensure continuity, it takes interchanges the inter-domain boundary condition. This is already discussed. So we get two models: shared memory model, where all processors see whole memory which is available, and it typically we use as a multi-core system with a single memory space. So it doesn't depend whether I have only one RAM or I have 4 RAMs connected to the same motherboard. The address space virtually must be a same address space. If I may say A, the variable A will have same meaning for all the processors. Then it's a shared memory. But in the other case, which is a distributed memory, this is typical shared memory, which is a distributed memory. Each processor sees only a local limited memory and operates on it. This is a distributed memory algorithm, that each processor has its own memory and they are connected via switch. So in a shared memory, the entire problem is on a same table, and many people are looking into the problem and solving different parts of the puzzle. In a distributed memory, everybody got part of the puzzle. So the kids play that puzzle. You have to make map of India by connecting all the states. So someone is looking into northern India, someone is looking into southern India, someone northeast, etc. And they are making their own puzzle complete, and finally they will communicate. And that is known as distributed memory system. And there is a hybrid memory system where you divide northern India and southern India to two different groups, and each of them is seeing the entire North India and trying to bring this together. So each distributed domain, each subdomain is being operated by number of processors using a shared memory. The fourth one which I will discuss is a CPU-GPU model. You have the puzzle, you ask a CPU, you ask an ordinary computer to solve the puzzle. Now while solving the puzzle, there are many involved steps. These steps can run in parallel. So what the computer will do? Computer will identify those steps and the associated data and offload it to a GPU. GPU will work on that offloaded part, what computer is asking it to do. And GPU has thousands of cores, so it can actually operate over a massively parallel environment. So the idea of coprocessors or accelerator, GPU falls in this class, is that they improve the performance of a computer CPU by augmenting the processing unit. So basically we are still using a CPU. Whenever we are writing a program, we are writing a CPU based program. But part of the CPU code will go to some processing units which is helping the CPU to improve its performance. One of the idea was coprocessors, that there are similar processing units connected to the processor, like a vector processor. When the processor is getting the job, it is putting that part, a vector addition part, to the coprocessor. This was brought into by Intel. Intel Xeon Phi was a very popular coprocessor unit. However, due to market reasons, Intel has discontinued. The other idea is accelerator, where it's an independent device. Accelerator is not part of the processor. Coprocessor was part of the processor. Accelerator is an independent device. So what do we do with the device like a printer? We plug it with the computer. So when you have an accelerator, we plug through a bridge, we plug it with our main motherboard, and some part of the job goes to the accelerator, is solved in an accelerated manner. GPUs are known as accelerator. They have their independent I/O devices. They are connected through programmable interface to the main CPU motherboard. Graphics processing units are accelerator. As the name suggests, these are graphics cards. These units were not initially developed to help you in solving your CFD program. These were developed to visualize. Why do you need processing to visualize? Processing needs some visualization, but that is very limited. Why do you need high-end processors to visualize? Why do you need a massively parallel system to visualize? The idea came from playing games, strategic computer games. Think of Rise of Nations or Age of Empires. I think nowadays you probably not play Age of Empires, Rise of Nations. So in one part of my computer screen, Roman army is building a barrack. Another part, a priest is coming and taking relics and putting it into the chest of the king to get some money out of it. In another part, some farmers are doing something, and from another part, Gauls are coming. As the army will go to stop the Gauls, by that time Gauls will probably come and break down the temple and take away the relics. So number of operations are happening at the same time. And the entire operation based on your input is happening in a parallel mode. The time Gauls are attacking and destroying the temple, at the same time some army people are coming down and trying to fight with the Gauls, and some of the farmers are pushing back. Everything is happening at the same time. So there are many cores. Each core is responsible for different parts of the computer system to produce the graphics. However, they also can be used for matrix calculation, and this is maybe 5 to 10 years back performance. They can somehow accelerate your CFD calculations. Now the accelerations are much better. This was 5 years back. So GPU is a very emerging and continuously developing technology. So performance, do not go by this performance. Today's performances are better, and we can get more than 100 times speed up now. So when we have a matrix vector multiplication, the matrix can be assumed as different parts of the computer screen, and different GPU cores are active and looking into that. Why we focus on GPUs? Because over years GPUs have outperformed CPUs, and initially they were developed for game design, but around 2000 it is found out that GPU can be very well utilized for number crunching, and then instead of GPUs, a group of similar architecture came, which the manufacturer termed as GPGPU, General Purpose Graphics Processing. So apart from graphics, you can do other calculations easily. And this is how in recent years, again recent means almost 10 years back, GPUs and co-processors, the blue one is a CPU, green one is a GPU, and the black one is a co-processor, green and red are GPUs. They have outperformed CPUs by a huge factor, by a factor almost close to 100 in their terms of peak performance. And now I say now it is more. And one can see that what is the performance of a GPU card, which is say for example 7.8 teraflops, one GPU card is giving, which is probably close to a lab-based or a small cluster, small CPU cluster, probably more than that. And that you get in a desktop, in a desktop workstation. In a workstation which can sit here, you can put the GPU card and get 7.8 teraflops. And if you go for single precision, you can get better speed. And therefore, in many AI-based calculations, people are used, but they do not always need double precision. They can compromise with the precision. They do mixed precision calculations. The other part is that GPUs are energy efficient also, which we should keep in mind when we run any parallel application, that when you run a processor, it requires energy. When you run a processor, you do not utilize the entire energy to crunch numbers, you lose a lot of energy, you dissipate a lot of heat because it's electricity passing through electronic gates. You further need energy to cool it down. So overall, all the data centers are known as energy sinks. They take too much of electricity to operate. So in that sense, because GPUs are small architectures, they require less amount of energy, and floating point operation per second, in that term also GPUs have outperformed CPUs.
We can completely replace CPU with GPU.
No, CPU cannot run on its own. GPU is a device which has to be connected to the CPU.
We can give many of the computing jobs from CPU to GPU and utilize the CPU less. We can reduce the number of CPU utilization, number as well as utilization percentage of CPU, and put things. So how does a GPU look? It is connected to the CPU through a bridge. Inside that there are GPU RAMs. These DRAMs are RAMs of the GPU. So GPUs are independent units. They have their own memory. They cannot directly read from CPU memory and operate over that data. They need data to be copied to their memory and operate over that. And the entire very complex architecture is due to the fact that GPUs are not designed to initially not designed to help you in getting your CFD job done. GPUs were designed to help you or to provoke you to play more computer games. So you can see that vertex works distribution, pixel work distribution, all these elements are there which are coming mainly from the graphics purpose. Now inside a GPU there are many TPC or texture processing clusters. Again, this name dates to a graphic application. Inside a texture processing cluster there is streaming multiprocessor. Inside each streaming multiprocessor there are number of streaming processors or GPU cores. These cores are transistors which are designed only to add numbers or only to do logical operations, mainly to add numbers. If you put something which is very complex, which your CPU can do, say calculation of a factorial and then taking a decision whether this factorial is being very large, then approximating it to something with 10 raised to the power 8, etc. If you give some instruction to a GPU, it cannot work because the architecture is that there are
transistors which are only given to add numbers, just to add numbers or subtract numbers, etc. So these small computing units in a very large number is present inside each GPU. But the number is very high. If we can see in the newest version is A100, but before that B100 was there. There are 40 texture processing clusters. Each texture processing cluster has 2 streaming multiprocessors, total 80 streaming multiprocessors. Each streaming multiprocessor has somehow it's not coming here. I think I have to. Each streaming multiprocessor has 64 cores. Therefore, 40 into 64, total number of cores becomes 5120. In one GPU card, you get 5000 cores. But these cores will do single precision calculation. If you have to do double precision calculation, you have to use 2 of the transistors. Therefore, for CFD applications where you need precise calculation, you get around 2500 cores in the card. Now this comes with another problem. There was a discussion on OpenMP, critical statements, synchronization, etc. If we have so large number of cores, so many instructions going together, it is difficult to synchronize among them. That will take a lot of effort. And probably if you take any application and try to run it in 280, maybe you will get to 280 to 60 cores in the same box. You try to run it there, you will see that your performance is coming close to the sequential performance, because sequential overhead is synchronization overhead is very high. So when going into the GPUs, some effort has gone into scheduling the tasks so that they actually can go over 2500 cores without seeing very high drop in performance due to synchronization. So that scalability of the application, that is also a very, very important aspect. The ordinary GPUs are designed for graphics rendering. Then we came with general purpose GPUs, and today's essentially all modern GPUs are GPUs. GPUs can be programmed to deploy processing power towards addressing scientific computing needs. GPUs are connected to a CPU which offloads the compute heavy jobs in terms of concurrent instructions to the CPUs. GPUs are in market for nearly 50 years, but over last 20 years they are being utilized in calculation. And now we can do matrix multiplication using GPUs, which is the key factor that using GPU we can do CFD calculation. I will give you some example and you will work with a code also. So how does a GPU look in comparison to a CPU? GPU has a CPU, for example, a quad-core CPU. There are 4 cores. Each core there are different levels of cache. Each core has its own L1 cache, some memory which is sitting very close to the registers. Each core has substantial control unit. There are multiple instructions going to a core. Like when I am showing my PowerPoint slide here, at the same time probably operating system is also doing something. I am downloading some file. Something is playing in YouTube, many things are happening together. So there is a control system which inside a CPU core which shares different jobs among the CPUs. That is not our parallel processing, but this is the scheduling of a CPU. But inside GPU, these controls are less. Inside GPU there is the GPU RAM, one L2 cache. Then almost all the architectures of GPU are utilized for providing number crunching facility, for giving you CPU core like benefits. There are very small amount of transistors which are dedicated for L1 cache, the lowest level of cache, as well as for controls. There is almost no control. You cannot do any scheduling apart from what your GPU has already done inside the GPU core. You cannot run a complex job where the job may have to take some if-else loop, some of the codes will go follow an if, some of the codes will follow an else. You cannot do it in GPU. You will try to do it in GPU, GPU will perform off. You have to find out operations which are very much concurrent in nature, extremely granular, and then you have to offload them to the GPUs.
Most of the transistors in CPU are dedicated for data caching and controlling. However, in GPU they are dedicated for calculation. Typically GPUs have small cache but large number of cores. Large number of, this is another interesting thing, that within core memory, within the core the memory is registered from which the operands are in the registers and operators operate over them. The amount of operand memory available in GPU is very high, and it does certain things with that. Newer GPUs have more flexibility. There are higher. Initially there was no L1, but now there are L1. There, sorry, initially there was no L1. That's not L1, but now there are L1 cache, etc. Some terminology what we use in GPU programming is a GPU is an outside agency, outside device which has been connected to the motherboard. It is known as a device. GPU is a device. Like if you search in your computer what are the devices, GPU card is similarly a device. Printer, keyboard, they are devices. GPU card is similarly a device. The CPU which hosts the GPU is named as host. So in GPU programming, when you say host, that means the CPU. This will be run by host, this will be run by CPU. This will go to the GPU, that means it will go to the device. The part of the code that runs in a GPU, this is known as a kernel. Kernels are basically the functions which are operated from CPU, but the function will run in a GPU. The memory that is available to all the threads in a GPU, which is basically the GPU memory, is called global memory. There is another term, shared memory, in context with GPUs. When we talk about GPU, they are anyway using shared memory architecture. But in GPU, if we talk about shared memory, that means some memory which is available to all cores inside a device. That has a different connotation. And device RAM is known as, DRAM is known as GPU RAM. So when we say DRAM, we must not confuse that we are talking about dynamic RAM. In context with GPU, if we say DRAM, it is GPU's RAM. Shared memory parallel computers and GPUs provide the system of execution of multiple independent instructions. These are threads. So GPUs operate in a thread-based system, in a threaded paradigm. These instruction sets which use common data strip from a common address space are known as threads. Threads are part of the main program and they can go in SIMD or MIMD, but in GPU they run in SIMD architecture. And the threads can run parallelly among different processors, but they need to synchronize due to the fact that if many threads are operating on the same data, once a thread has operated, it changes its cache. So we talked about caches. Some memory is prefetched and sits into the cache. If one thread changes the main memory, the cache value of the other threads must have changed. Otherwise, there will be a conflict in terms of the correctness of the value. So they often need to do synchronize for cache coherency, or they often need to put barriers. MPI barriers are used. Similarly, in OpenMP or GPU, there are barriers. In shared memory, there are barriers. That you synchronize. Everybody has come up to here. Everybody knows that the shared variables are equally updated for uniformly updated. Then you go for the next step. So this synchronization is important. And thread-based parallelization is alternative of message-based parallelization. For example, I have to multiply, just to give a small example, I have to multiply a matrix and vector. First vector will be multiplied, the row vector will be multiplied with the matrix. So what will I do? I will first take these elements, take its dot with this, find this product, take these elements, take its dot product with this and find this product. They are two independent calculations. They are using same data, but two completely independent calculations. From the output matrix, the first element and second element can be calculated independently. I can ask two different processes to do that. Therefore, I can launch, I can say thread 1 will calculate for 58, thread 2 will calculate for 64. They can run in parallel. So in GPUs or in OpenMP based shared memory system, we use this idea that from the same data set, identify which operations can be done in parallel, ask different processors to execute different. So if we, there is a mistake. If we run in a CPU, we can run at most 4 threads. There are 4 threads. In a GPU, we can run thousands of threads altogether because there are thousands of threads. So limited number of complex tasks can go to GPU. GPU can run, CPU can run very complex tasks because it has its own control, large caches. The GPU can run very simple tasks, but they are of limited number. Initially, there was when we were studying about GPUs, I did not find many good textbooks also in GPUs, but there were some slides prepared by somebody who is famous, but I forgot his name. So it was that you can have 4 horses to draw a carriage, and GPU is like using 4 million ants to draw the same carriage. So it has to be brought down to very small, very simple work, but you have a very large number of codes for doing that. Programmer cannot directly run a job in a GPU, which is a very common misconception in general CFD or scientific computing community who have not got their hands dirty with GPU, that you have a GPU and you can run job in a GPU. No, you cannot run a job directly on a GPU. You need a host CPU which will offload the part of the job to a GPU. And another thing is that though all the GPUs are GPGPUs, there are specifically developed GPGPUs, which is Volta or Pascal or Ampere architecture, which are good for double precision calculations. Any GPU you can use and get done with single precision calculation. But the performance in terms of double precision calculation, that 2 single precision codes are giving 1 double precision calculation, that is very specific to some of the GPUs. GPU jobs require more granularity, that means there has to be large number of concurrent instructions which is possible. Memory access in GPU is different than CPU due to small, or in earlier GPUs there are no L1 cache, small or no cache, and small off-chip memory. So small off-chip memory means even if we go for the GPU RAM, this memory is smaller than CPU. Nowadays we talk about 1 terabyte CPU RAM, but the highest memory in GPU RAM is found out to be 80 gigabyte, and in general many other GPUs the memory is much smaller, 16 gig or so. So in today when we talk about very large 512 gig to 56 gig CPU RAMs, GPU RAM is much smaller. GPU threads are scheduled at streaming multiprocessor. I will not come into this part here. As the GPUs provide thousands of cores, there is always a requirement that we need to have a programming interface which will help us to run job in these thousands of cores, that will scale the job over thousands of cores also. At many cores, that much synchronization will not completely kill the performance. As well as it's a new architecture, so we need to have a programming interface which helps us with little learning to utilize this new architecture. For example, cache, memory, etc. We do not talk about these things when you go to discuss about any CFD programming. We learn it ourselves and that is sufficient. But when we go for GPUs, we cannot avoid learning about the architecture. So learning something about the hardware, which usually we mechanical engineer, mathematicians, physicists do not need to know. So in GPUs you need to know little lower level programming terminologies, but as well as this learning should not be very difficult for us. Without very dedicated computer science background, somebody should be also be able to pick up this. So there is a lower, one of the ideas is that, and based on that in 2006, NVIDIA, this is the largest manufacturer of GPUs, they came up with programming API and programming model and API, which was named as Compute Unified Device Architecture. This was an architecture specification as well as it has certain syntax and semantics over which you can modify a C or C++ program and write part of the program to be executed in GPU. But later they observed that this is not an architecture, but this is a programming model itself. So they stopped using this full name and used only the abbreviation as the specification CUDA. This was later named as CUDA programming paradigm. So at the code there are 3 instructions There is a shared memory over which a group of threads are working, and as and when required there are barriers to synchronize the shared memory operation. If we see that we basically have to start with a integrated CPU plus GPU code, maybe a C code, C++ code or program. This code has two compilers, one compiler for the C, C++ or Fortran part, another compiler which is in CUDA, that is inside CUDA, another compiler which will give you compilation for the GPU. Now, NVIDIA C compiler is there, that is CUDA compiler. It will make an assembly language program using CUDA to run in the GPU. In parallel, it will take the other part and use a standard compiler to run in C. CPU will call a function which is supposed to run in GPU, and the GPU compile function will be applied. But along with that, there are already CUDA optimized libraries which you do not have to write any CUDA program. You have your own C program or Fortran program, but you can use CUDA libraries, CUDA optimized libraries, which will directly go and run in GPU. That facility is also there. So, how does this program run? That the serial or modestly parallel means there are 4 threads, 8 threads, 16 threads. This part runs only in the CPU. Now, highly parallel part runs as a kernel C code, single program, multiple data. Same program will go, but they will launch many threads and operate over different data. That will run as a kernel C code in the GPU. And it is supported by Fortran, Python, etc. So you have your general application CPU code that runs in a single thread in a CPU. Then you call the CUDA kernel. From the CPU code, you write a function like this. Do a function name, specify how many blocks are there or what are the arguments. This function with this many blocks goes into the GPUs and run in a GPU in massively parallel. Once the GPU part is over, once CPU, and this is an asynchronous manner. That means once CPU offloads that function to the GPU, CPU is free, CPU does its own work. Again, when CPU finds that this job has to be run on the GPU, it executes another kernel and puts the next part into the GPU. Kernels are the functions that are called from CPU code and executed in GPU. Kernels return void. Why? I will come to it later. CUDA launches threads in blocks and grids. So when we call a CUDA function, we say a grid of threads is launched. A grid contains a number of blocks. Inside block, there are certain number of threads. There is a particular arrangement of threads. So what is a thread and block? So when we launch the threads, each thread has a specific ID, which there are functions to determine the ID. Based on the ID, thread knows on which data it is supposed to operate. And it is like in OpenMP, you write it pragma, parallel, for. Compiler knows that thread will operate over which data. Compiler sets it. In GPUs, compiler cannot set it. Programmer has to find out the thread ID and say in which memory location that thread will operate. Threads belongs to a block. So when you launch a thread, the entire thread is launched in terms of a 3D arrangement of thread, which is known as block. All the blocks are again form a 3D arrangement of block, which is known as grid. So threads are part of block and blocks are part of a grid. When you launch a kernel function, you launch a grid of thread, which has many blocks in the 3D arrangement, 3D matrix arrangement, Cartesian arrangement. Each block has many threads in a Cartesian arrangement. That is done taking care of the scheduling, which is done itself by CUDA. There are something which is slightly of higher abstraction. So this is a grid in which many blocks are there. Inside one block, the threads are arranged like this. And now you have a local ID of a thread within a block. Considering all the block, you can find the global ID of a thread. You have to say that with this global ID, this thread will operate over this data. That is the programmer's job. They follow Cartesian structure. And this is done, typically this rectangular arrangement is done because you want to work with matrices. The thread ID inside a particular block is mapped to the matrix data structure. not coming into it, there is this known as thread algebra, that how will you point to a memory using the thread algebra. So CUDA provides functions. Now, as a programmer, you cannot do anything in a GPU directly. Whatever you are doing in CPU. You have to ask CPU that, hey, allocate this memory in GPU. Use these variables in GPU. So CUDA provides a function by which CPU can specify some memory locations in the GPU. That is known as CUDA malloc and CUDA free. In Fortran, these are CUDA allocate and CUDA deallocate. This is how the memory is allocated, and they are comparable to that. CUDA program now also GPU cannot do direct I/O. GPU cannot directly read from a file. GPU cannot directly read from. What a GPU can do? GPU can take data from CPU. So in any CUDA program, before you execute a GPU kernel, first part will be that you take some data from CPU and put it into the GPU. Operate over that GPU during the CUDA kernel. After the kernel is over, again take that data and copy it back to the CPU. So the workflow is that this is a typical C programming module, that CPU will read, RAM will read from I/O user, CPU will read from RAM, CPU will write back to RAM, and RAM will write to RAM. In a CUDA programming model, the idea is that from RAM, some data will be copied to the GPU's RAM or device RAM, and GPU will operate only over that data. Once the operation is done, GPU will write it back to the RAM, and then it will be written back to the RAM. So the workflow is that before you start any operation in GPU, allocate some data in GPU, then copy data from CPU to GPU. Now your instruction stream goes to the GPU core. So from the data, GPU cores operate over the data and modifies the data in the RAM of the GPU RAM. Once the GPU kernel is over, this data is copied back to the CPU RAM, and now you can utilize it. You cannot directly access it. And then these are the structures that first you have a serial code part of, then you call a kernel. Inside a kernel, there are multiple threads. All the threads are mapped to a thread block which uses per block memory. And then all the blocks are mapped to a grid which uses the memory. This memory is global memory, means this is the GPU memory. The blocks cannot use CPU memory directly. Then you have to, so therefore before calling the kernel, you have to copy data from host to device, CPU to GPU. After the kernel, you have to again copy back data from device. So here is one example. I'll give you, you'll see the slide examples later. This program is with you, vector addition, not with you. Just show them. But the idea is that you have a general CPU program. This program is a CPU program. Inside the CPU program, there are allocation of GPU variables, copy of the GPU variables, the CPU variables to the GPU variables. CUDA mem copy, it copies the from host to device, from CPU to GPU. Then you define the block size, grid size, to add two vectors using a kernel. That kernel is another function. This function will be operated inside the CPU. Once this is done, it will run to the location C. What is C? C is D underscore C in GPU memory. So from D underscore C, again data will be copied from device to host to H underscore C, which is in CPU, and then you can utilize it. So this part is executed by CPU, and the global void vacat function, this vacat function is the kernel which is executed by the GPU. This is the copying of data. CUDA alloc will allocate memory, copying of data. This function is called by CPU and executed in GPU. And then after that, you have to again, you operate over D underscore B, D underscore C, which are inside the GPU. It operates over that data. After that, D underscore C is modified, and that is copied back to the host. So this definition is for a kernel definition with a function which starts with this execution configuration is a kernel function. This is called from CPU should run in a GPU, and this is the declaration of a kernel. So this is the kernel function. Each thread that executes the kernel is a unique thread ID within the kernel. So we can see here that we have used 1024 threads in each block and total number of operations divided by block size number of grids. So for each grid thread there is a thread ID inside the block and there is a block ID to the block the thread belongs. Based on that we have calculated the global thread ID and the GPU thread works on the main data corresponding to the global thread ID. So this point is written. I think I'll skip through this, but this is basically how a GPU code works. And there are specification of what should be the grid size, block size. You can define it using certain variables. What is the grid size, block size? So overall, the idea is that each GPU thread will operate over a GPU core. The block of a thread will go to a streaming multiprocessor. Remember when we have shown the GPU architecture, if I go back, if I go back, there are streaming multiprocessors. There are streaming multiprocessors. There are streaming multiprocessors in which there are many cores. So when we put a block, this block goes to the streaming multiprocessor. That is the scheduling of a inside a GPU. All the threads in that block works in the course of the streaming multiprocessor. Now in many cases the number of threads are more than the number of cores available. So a block of thread, a group of thread will come, they will be operated. Once this group is done, then the next group of threads will come and they will be operated. That's why the block and thread level parallelization is there. Blocks will go to streaming multiprocessor, threads inside the block will operate it over the course of streaming. So thread will go to a core. The group of threads which are the group of pointer is here, but it's not coming. The group of threads, there is some problem in the pointer. The group of threads will go to the block and the entire grid which controls all the blocks will finally the kernel which will go to the GPU. So there can be one block assigned to one GPU scheduling of threads. This is on the scheduling, but I'll come to that there is a basic execution unit in a GPU, that what is the maximum amount of parallelization. One is that as many blocks are there, as many group of threads can be. All the blocks can work in parallel. So there are 40 streaming multiprocessor, 40 blocks of threads can work. In each block, depending on the number of cores available, that many threads will come and they will operate over in parallel. So in each block at a go, there are 32 cores, for example. 32 threads will operate over a parallel and then blocks are working over a parallel. So the basic unit of parallelization is the warp size of 32, which is usually 32. And block is that what will map in a code. So usually we prefer that our blocks have threads which are more than 32, otherwise some of the codes will go empty. And this is a multiple of 32. And we can specify what should be the block size, etc. What should be the thread size. One can show, and if But what is very important is that one group of threads which is going to a block, GPUs have no very less control unit. If they execute one particular instruction, some of the codes that instance cannot execute another instruction. So if you have an if-else loop, only the if part will be activated. So if among 30 to 20 is following one if condition, only these 20 threads will be active. Once they are done, rest 12 threads will be active. You will not get the effect of that. So in a GPU code, inside a kernel, it is no, do not write an if-else statement. Then you will not get the effect of parallelization. This is known as warp divergence. So number of threads in a block will be multiple of warp size, and one can show that based on the block size, you get different performance for the same program. How are you choosing the block size? Block size must be multiple of warp size. Block size must be something like that. It utilizes all the memory. Once it goes to a latent state, all the threads are going to latent state, and some new threads can come and be scheduled there. So one does an experiment based on the problem size, that what is our optimum warp size, what is our optimum block size. And as the problem size changes in different cases, we can see different block size. Usually higher block sizes gives you better scalability. And the thread divergence has to be avoided. That means threads in the same block must not have any if-else loop. If there is an if-else loop, GPU performance. Therefore, you need to have algorithmic modifications when you are using avoid if-else statement. So I will probably remove this, but one important part is that compute to global memory access. As much you are computing and how much memory you are utilizing. This ratio is an important ratio. If using small memory you can do good amount of computing, your performance will be better. So CGMA, or compute to global memory access, is an important term here. So if CGMA ratio is 1, then you are not getting the clock processor speed, but rather you are getting the memory speed right. So this is a matrix vector subroutine. What is important is that because GPUs access memory from the RAM, and this access is, each thread points to a different memory. This access, and you need to copy data from CPU to GPU. It will be good if the entire data is packed as a 1D array. The overall access, coalesced memory, the overall access is good. So in a matrix vector multiplication, when we write the CUDA kernel, we try to compile that, this is inside the CUDA kernel, we try to coalesce the matrix from a 2D arrangement to a 1D array. And then based on the thread ID, this is the local thread ID, based on the thread ID, each thread works on different elements of the matrix. And we can see that this was taking, CPU was taking 0.44 seconds, this is a small matrix. GPU is taking 0.38 seconds. Some improvement, but really not an improvement justifies thousands of processes. Because here the memory was, the overall operations are small, and compute to global memory ratio is very low. Now if we use these methods and go for matrix solver in a conjugate gradient matrix, where for a small matrix serial code was taking 19 times, GPU was taking 0.8 times. But for a large matrix it is more important, where CPU was taking 42 seconds, GPU is taking 42 seconds. So you are getting close to 100. If you increase the matrix size, you will get better performance. Similarly, for an unstructured matrix, because the memory access is more complex, the speed up is not not as comparable to a structured matrix, but still you get good amount of speed up. Some 50 times of speed up you get in a structured matrix. GPU code gives better speed up for large matrices, and massively parallel systems are only meaningful when you are working with a massively large matrix. So GPUs can give potentially high scalability. This is matrix, row, number of rows. this is number of rows, this is time taken in second in CUDA, and this is time taken in second in this one. These are different solvers. Size is, this is unstructured matrix, 144 by 144, the number of rows. But I think there is also another important aspect. What I am running in 790 seconds in serial code, using CUDA I am getting in 18 seconds, but if I use an efficient matrix solver, it will anyway come down. So it is also important that you first see your serial code is efficient enough, then go for parallel. Unstructured matrix. Unstructured matrix. Yes, sir. This is diagonal, this is must be CSR. And in GPU, as you mentioned about CSR, storage algorithm is extremely important in GPU, because if you try to store the entire matrix, you cannot run anything. So what we have seen is that GPUs can give you very good scalability. But in order to work in GPUs, you need to learn a lot of things. CUDA is a altogether new programming paradigm. If you have to utilize CUDA, you probably have to rewrite your program, because if you program in developer, for example, I have shown that the memory matrices must be in a 1 year. Memory must be coalesced in 1 year. And you have written your program differently. You have written your program probably keeping in mind the memory access pattern of the cache of the compiler you are using in the CPU. But when you go to GPU, it is very different. Therefore, CUDA you have to do a lot of things. So there is another platform called OpenACC, where similar to OpenMP, many groups came together and tried to develop open APIs for accelerators, which helps you to use CUDA in the background. In the foreground, you will use something very similar to OpenMP. So this is known as OpenACC. It is a directive-based parallel program. What Anubda has shown, that you have to identify the locations which will be parallelized, and you write the directive which will make it parallel. In the background, compiler is putting things in CUDA. There are some overhead. Some cases performance is not as good as CUDA, because of course there is another level of abstraction which has its own overhead, and it's probably not doing it in the best way which you have used doing it in CUDA. But if you have a legacy code, a 10,000, 20,000 lines code, rewriting the entire code to CUDA would have been difficult. Rather, you use OpenACC, which works very similar to OpenMP and can parallelize. So it has its libraries, compiler directives, it works with many programming languages, and similar to CPU, multi-CPU program, you have to identify that this will go in a parallel and specify OpenMP type of constructs there. But in CUDA, there something has to be kept in mind, that how you are accessing memories, how you are updating memories, because if you update some memory to your CPU, that means copying from CPU. You are not using any if-else statement. If-else statement will anyway give you out of divergence. Some of the CUDA concepts have to be kept in mind. But this is again maintained by a non-profit organization like OpenMP and developed by a group of developers. And you have to find out, you see a loop and say that it's parallel. And it start working with the sequential code, identify the locations and parallelize it, and check that the results are correct. So it is similar, that you find out which part has to be parallelized. You give a compiler the hint that it will go be parallelized, and compiler will work accordingly. In the low level details of hardware which you require to learn in CUDA, you do not require to learn. What is the warp size? This is known as, what is the block size? This is known as gang size here. You may specify it. If you do not specify it, compiler will itself make it a multiplier of 32 of warp size. So we come back to our reverse boundary algorithm. To go it really fast now. Find out what are the solid cells, what are the fluid cells, what are the intercepted cells, do a reconstruction here. And there are two parts. One part is searching for the intercepted or immersed cell, another part is interpolation. So when we took this code and solving using Markson method and profiled it, we saw that 74% time is taken by Poisson equation, 13% time is taken by surface tracking. We are tracking say 10 to the power 5 surface points in a million cell platform, and momentum equation took place around 6%. So first is that in OpenSSE parallelization, analyze which part is taking more time. Poisson equation is taking more time, surface boundary condition is taking more time. It is difficult to parallelize also because we have to use if-else condition to find out where the normal is going, whether it's cutting a cell or not, etc. So reconstruction parameter, it has many memory overhead. We need to store all the weights, etc. And we are earlier solving a mass conservation equation that also put a difficulty. So GPUs are inefficient in code complexity. There cannot be conditional looping and has small cache. So what we did, we have did something to reduce the memory size of the matrix, coalesce the matrix so that the memory size is reduced. Group the points, internal points, immerse points, and fluid points separately. And separate groups will go to the GPUs as a separate instruction, separate kernel, so that we do not fall in an if-else loop. And then you use the red, did the red-black. So this is the matrix storage. We have reduced the matrix storage using a linearized storage method, which is also required because GPUs does not have much memory. Instead of the previous mass optimization, we are using a field extension, so you have to do algorithmic changes which are suitable for GPU. Not all algorithm you can directly take to GPU and parallelize it, because GPUs are not good in some part of it. Then some of the steps like dynamic allocations, explicit forcing, you cannot do any implicit step in GPU. These things are included. So we can see that in grouping of the methods, we start getting around 30 times of speed up. And then this is after many iterations, this is what came, that in 8 million cells the speed up is 112 times. In 26 million cells the speed up is 140 times, using a 140 times of a single CPU code. And different components, how much time it is taking. Also there will be an overhead which is unavoidable, which is copying data from CPU to GPU and GPU to CPU. That is unavoidable in any GPU. So overall 150 times or more performance speed up is obtained. And when this was in V100 GPU, as GPUs are improving, their flexibilities are improving more. When from V100 we go to A100 GPU, we can see another 1.5 times of speed up. So overall, there are something on the search also which requires the speed up. Then we go for multi-GPU. We have distributed the domains using MPI, and here GPUs work in an asynchronous manner. So MPI call is not synchronous MPI or blocking MPI call. They are asynchronous MPI call, where you have to use some point of time barrier to ensure correctness. And then we can see that the speed up with respect to GPUs, say when we go from 2.5 million cells, 1 GPU to 4 GPU, there is 1.9 speed up. But when you go from 100 million cells, 1 GPU to 4 GPU, there is more than 4 times speed up. So you have improved because local memory size has reduced. Each GPU is taking less amount of memory. So CPU to GPU memory transfer time, that has reduced. That increases speed up. So you can improve speed up in GPU applications in some cases. These are some applications in which up to 8 GPU we are can get nearly 8 times of speed. Also, how the memory is being transferred using which architecture, that also, which hardware, that also determines the speed. There are some advanced GPU platforms which are dedicated for multi-GPU computing where you will get better speed. Then multi-GPU can also be utilized by a OpenMP instruction. That there are 2 OpenMP instructions. One OpenMP instruction is for one group of rows, inside which you call a GPU. Another group of instruction is for another group, another set of rows, where you can avoid data transfer. So there are some codes which shows that GPU scaling, the throughput of GPU nearly remains constant even when you can 512 GPUs. You can go to very large number of GPUs. You can keep it possible. There are some calculations of 500 million cells where it is showing over 32 GPU it is coming similar to RWL flow. There are people have done calculations up to few billions. This goes up a billion cell calculation for multi-GPU hemodynamics. So billion cell calculation is possible using multi-GPU platform. 1.4 million cell, 4 billion cell GPU they have done using around 10 GPUs. So you can really take very large problem and go into the GPUs. But yes, it has its own issues. You need to rewrite the algorithm substantially. You need to know some part of the hardware. For 330 million, these are usually the large GPU calculations go for a few hundred million. FSI over 220 million at bulk. And one can show that the clock time, as we are increasing the GPU clock time per time step, that initially remains constant, but then it increases as we are using higher GPU because the amount of data copy from CPU to GPU increases. So these are something we have looked into very large scale scientific computing applications which you can do using GPUs. And hybrid parallelization where you have MPI or OpenMP to distribute among different CPUs and each CPU is calling another GPU. That's a hybrid parallelization. That works, that actually works and can help you to go to exascale, very large computing. Say 10 to the power 12, 10 to the power 12 flops per second. Questions? You will get a GPU code to work. No question. Okay. Yes.
My question is about accuracy for CPU and GPU for a very complex case.
If it's very complex, it will not have. So if you have a very complex in terms of computational complexity, in terms of algorithmic complexity, if it's a complex algorithm, you have to see how you can simplify it, bring it down to the most explicit, most rudimentary manner, which in a CPU probably someone will throw out. No use this. Something which can run in a GPU.
Even if we can change the GPU architecture or the GPU,
we cannot change GPU architecture.
Even the GPU model, does it have a significant impact on the results?
Oh, sure. As we are getting newer GPUs, the internal scheduling, internal data transfer, these things are improving by a large factor. As shown, 800 to V100 calculation somewhere I have. You can see what was taking 20 seconds in V100, that takes 18 seconds in 800. So which is newer architecture. So all newer architecture will be
the result like acquisition or the result is almost
results. So this is a very important, very important question, but probably little difficult to appreciate at this stage. When we do a thread-based allocation in GPU, each thread knows on which data it should run, but no one knows which code will run which thread. In CPU, you can pin it, which code will run which part. In GPU, cannot do that. So there are 3,000s of ports, and you do not know which thread is operated by which code. So you do not know when you finally compile the results, which was previously operated, which was later operated. If you have any sort of implicitness, it will not work. It will give you wrong result. Even if you do not have any implicitness, because the calculations are done in a different manner, in the machine accuracy precision level, in the round of error level, there will be differences. No two GPU calculations for the same code, you run it twice in GPUs, after the double precision is the accuracy it is trying to make. After that, the values will be different in two calculations. So when you add them, the compiled effect of the calculation will make some changes at some level, 10 to the power minus 10, minus 11 level, there will be differences. Cannot. Okay, anything else? Okay, so I think you can go for the lab session.
say anything? They have not come there. Ketan is also not here.
Quite a good experience. As I am a worker in the field of computational fluid dynamics for some time now, there were several sessions on which I haven't yet worked on, and they were, and then these kinds of platform actually, they don't give you the background story which you have to work and you have to toil hard to get to that, but at least they give you the roadmap, how you should proceed and what all gap you need to analyze yourself in order to get to some point, right? And apart from myself, I have my student out here with whom I am presently involved in several tasks of computation. He is essentially from computer science background, but with a huge amount of interest in applied physics, right? So I am really blessed to have students like Kanpur and Nodal in my very institute, and with whom I am actually involved in several fields of computational research presently. But all said and done, it has been a fantastic experience for me. Not only just, and especially I would like to emphasize the session which I enjoyed the most was a chalk and talk session delivered by, I actually don't know your names, Arnold. So Arnold sir was really fantastic, and also the other presenters, including Somnath sir. They were really excellent, but frankly speaking, I couldn't follow beyond a point. The rudimentaries were, but Arnold sir was fantastic, so to speak, because he was dealing with physics and computational techniques of physical processes nearly through the entire session through his lecture. So I could relate myself, and the one delivered by Shundi, that was also on the occasion of the dinner session, I was in fact complimenting him because that was the only lecture which I followed thoroughly, right? so having a background of Patankar and Varstage actually enabled someone to follow the whole thing at one shot. So all said and done, and not to forget the sumptuous lunch, the dinner, as also the lunch that we had today, the beautiful registration kit with all its, the two lunches, okay, fine, and the dinner. So all said and done, we look forward to see more such workshops in the near future.
Maybe we can have answer, but if you follow, you should.
Thank you, sir. Myself, Jadavpur. I am associate professor in IIT Kharagpur, civil department. So my journey for CFD was accidental, not my profession, because I think this is the right platform to say that. Because my guide during my PhD in NSM Bangalore, I was doing experimental work, only experimental. Then once I finished my experiments, then my guide got some consultancy project where we had to model the pump sum. Then he asked me, Ajay, can you do, because you have finished? And I said, okay sir. So he gave me 3-4 months time. Let's try, give it a try, and then do it. So fortunately we had ANSYS software there. So we
I learned it something, and then I was able to do some work on that, and I was able to get the results to the client. He was happy, and things went well. Then with that results, he gave us like a 3 more consistencies. So then I improved on those things, and then I got a little bit more comfortable with CFD, particularly software part. Okay. Then I got an opportunity to in NIT Warangal. So then I thought, let's take it into the research level. Then since then, last 10 years, I'm doing my work in CFD. So that's how I got into computational fluid dynamics. So as far as because all these things which I got over here were at the back of my mind, and every time it used to bug me how to things are happening behind the things, because I am using a commercial code. Okay, and I was also trying to migrate to this open form also, but that was not very smooth till now. But this workshop has given me a lot of confidence that okay, I can move on and start to launch myself into open source. And all the background behind that is how the computer architecture is helping us to accelerate this thing, and how it helps. All those basics I could get now. So now it is really nice that I could get all those things in one workshop. Now I can just enrich myself and then move forward. So thank you very much. All of these lectures were really very nice and enriching. It has broadened my horizon, and it has encouraged me to move forward into this. Till now I was very fearful where to go, how to move forward, how to get this information, how to get that information. Now I have got some structure. Okay. With this structure I can move forward. That is what is really helpful. Thank you very much. And besides that, hospitality, lunch, dinner were very nice. And I look forward for similar kind of workshops.